Nothing. It is a word we use so casually every day, yet its true meaning remains one of the greatest mysteries. What exactly is nothing? Can it truly exist? And if so, what is it made of? Join us today as we embark on a journey that will transform your understanding of everything and nothing. In the scientific world, nothing is often defined as the complete absence of matter, the total lack of anything that has mass or volume. On the surface, this seems straightforward. We might picture nothing as simply empty space. However, the reality is far more complex, especially when we dive into the realms of cosmology and quantum physics. Everyday intuition tells us that empty space is just that, empty. But scientists have uncovered a surprising truth. What looks empty to us is anything but. Even the most barren vacuum holds properties and phenomena that challenge our common sense. Quantum physics reveals a strange and fascinating idea. Inside what we call a vacuum, tiny particles called virtual particles spontaneously pop into and out of existence. This constant flickering means that true nothingness, a state where absolutely nothing exists, might never actually be achieved. Beneath the surface, a restless sea of energy and fields buzzes invisibly at the quantum level, showing us that emptiness is not truly empty. Looking up into the vastness of space, the concept of nothing takes on cosmic significance. According to the Big Bang Theory, everything we know, every star, planet, and galaxy burst forth from a single point, often described as nothing. But this nothing was not a simple void. Instead, it was a state of incredibly high energy, a tiny, dense point from which the universe expanded. This reveals that nothing, on a cosmic scale, is far from simple. It is charged with potential, the very seed of existence itself. Exploring the idea of nothing also leads us into the realm of philosophy. Can true nothingness ever really exist? This question bridges the gap between science and deep philosophical inquiry, showing that the more we learn, the more complicated the idea of nothing becomes. Nothing is not just the absence of something. It is a profound concept that tests the boundaries of our understanding and invites us to rethink the very nature of reality. Physicists distinguish between empty space and true nothingness by studying the properties of each. Empty space or vacuum seems devoid of matter, but is alive with fundamental forces, energy fluctuations, and those fleeting virtual particles. This space is a dynamic arena where quantum events continuously unfold, influencing the behavior of everything around us. True nothingness, on the other hand, would mean the total absence of everything. No matter, no energy, no forces, no space, and no time. According to current science, such a state may be impossible to find. The universe's fabric is woven from quantum fields, making the idea of absolute nothing more of a philosophical concept than a physical reality. Even the most empty regions of space obey physical laws, carrying properties like gravity and energy that shape our universe. In the end, nothing is not just emptiness. It is a deep, rich, and intricate part of existence itself, an enigma that continues to captivate scientists and philosophers alike, urging us to explore the fundamental nature of everything around us. Additionally, physicists use advanced devices called particle accelerators to explore the true nature of what we often think of as empty space. When tiny particles are sped up to incredibly high energies and then smashed together, they can briefly produce particles that seem to appear out of nowhere, almost as if materializing from a vacuum. This surprising effect reveals that what appears to be empty is actually full of energy and potential, capable of giving rise to matter under the right circumstances. This challenges the common idea of emptiness as simply nothing. Instead, it shows that empty space is alive with activity, fundamentally different from the concept of absolute nothingness, where no such events could happen. The contrast between empty space and true nothingness becomes even more profound when we look at the cosmos itself. Scientists studying the universe's origins argue that the Big Bang, the event that sparked the birth of everything, did not come from nothing in the purest sense. Instead, it emerged from an unimaginably hot and dense state. This state might seem like nothingness at first glance, but it was actually packed with energy and fundamental particles. So the line between empty space and true nothingness is not only about what we can see or measure, but also about deep theoretical ideas that continue to puzzle and inspire cosmologists. The concept of absolute nothingness, especially within our universe, raises profound questions that blend physics with philosophy. Absolute nothingness would mean a complete absence of everything. No matter, no energy, no space, no time. Yet our current scientific understanding suggests that such a state might not even be possible. According to quantum field theory, what we call a perfect vacuum is never truly empty. Instead, it is filled with fluctuating quantum fields that constantly ripple and change. These fluctuations produce virtual particles that appear and vanish almost instantly, indicating that empty space itself is an active participant in the universe's dynamics. Even if all matter were somehow removed, these underlying quantum fields would remain, making true nothingness impossible. When considering the universe's birth, cosmologists point to the Big Bang as the beginning of everything we know. This event started from an extremely hot, dense point, a singularity bursting with energy and particles. Before this moment, the idea of absolute nothingness likely did not apply. The universe's origin involved complex states of energy and matter, not a sudden creation from nothing. This understanding challenges the possibility of any state resembling absolute nothingness within our physical universe, as it contradicts the laws of physics that govern cosmic evolution. The philosophical implications of absolute nothingness add even more layers of complexity. If true nothingness were to exist, it would lack anything that could be observed or interacted with. Without matter, energy, space, or time, the very tools science uses to understand reality would be absent, making it almost impossible to conceptualize within any scientific framework. This means that while pondering absolute nothingness is a fascinating intellectual exercise, it remains mostly an abstract concept rather than a practical reality in our universe. This journey into the nature of nothingness reflects a long history of human thought and scientific discovery. Ancient philosophers like Aristotle wrestled with the idea of nothing, famously rejecting the existence of a vacuum and proposing that nature abhors a vacuum. For centuries, this belief that something cannot come from nothing shaped the foundations of both philosophy and early science. However, as science advanced through the Enlightenment and into modern physics, our understanding of nothingness evolved dramatically. Newton's laws of motion and gravity described a universe filled with matter and forces, reinforcing the idea that space was a tangible, filled realm, not an empty void. Today, the exploration of empty space, quantum fields, and the origins of the cosmos continues to deepen our grasp of the universe's mysteries. It invites us to question what it truly means for something to exist or to be nothing, pushing the boundaries of knowledge and imagination. This ongoing inquiry remains one of the most fascinating scientific and philosophical journeys humanity has ever undertaken. However, Newton's vision of the universe also opened the door to pondering what might exist beyond the reach of observable matter. Although pure emptiness remained largely unexplored at that time, the advent of quantum mechanics in the early 20th century transformed our understanding of nothingness in profound and unexpected ways. Scientists discovered that even what seemed to be empty space was anything but inert. This vacuum state, once believed to be completely void, was revealed to be teeming with fluctuating energy levels and ephemeral virtual particles, constantly popping in and out of existence. This groundbreaking insight shifted the idea of nothingness from a simple absence to a dynamic and active entity with its own unique properties. In modern cosmology, our comprehension of nothingness has deepened even further, shaped by revelations from the Big Bang Theory. The early universe is no longer imagined as a cold, empty void, but as an unimaginably dense and hot singularity, bursting with untapped potential. This singularity was the seed from which everything emerged, a state brimming with possibilities rather than emptiness. More recent scientific theories about dark energy and the very fabric of space-time continue to challenge and refine our definitions of nothingness, pushing the boundaries of knowledge and revealing how intricately connected nothing is to existence itself. This ongoing evolution in the concept of nothingness reflects humanity's relentless quest to understand the universe. Far from being a mere philosophical curiosity, the idea of nothingness lies at the heart of the laws of physics that govern reality. One of the most crucial tools in grasping this concept is the number zero. In both mathematics and physics, zero symbolizes the absence of quantity, the precise point at which there is nothing to count. This seemingly simple idea provides a way to express and analyze nothingness systematically, bridging the gap between abstract philosophy and concrete scientific inquiry. In mathematics, zero is far more than a placeholder. It is a fundamental component of arithmetic and algebra. It enables operations involving absence, allowing equations to reflect balance and equivalence. For instance, in an equation representing equilibrium, both sides may add up to zero, illustrating how zero can signify a state of rest or balance. By offering a numerical representation of nothingness, zero clarifies the boundary between presence and absence, giving us a clearer framework to explore existence itself. In the realm of physics, zero takes on even deeper meanings. It describes states where energy, temperature, or motion vanish completely. For example, absolute zero represents a theoretical temperature at which all molecular motion stops entirely. This concept shows how zero marks the boundary between activity and complete stillness, helping us understand the fundamental limits of physical behavior. Through zero, scientists can define and explore the delicate thresholds that separate being from non-being, shedding light on the underlying rules that shape our universe. Moreover, as scientific discussions about quantum mechanics have unfolded, they have revealed an astonishing truth. Even in what we consider a perfect vacuum, an emptiness where nothing seems to exist, the number of particles and the amount of energy are never truly zero. Instead, they fluctuate around zero, creating a dynamic state known as the quantum vacuum. This phenomenon challenges our everyday understanding of nothingness by demonstrating that absence is never absolute. The very concept of zero thus serves as a profound reminder that nothingness and existence are deeply intertwined. Absence itself carries meaning and presence within it. The idea of zero highlights this intricate relationship, showing that even when something appears to be missing, that emptiness holds significant importance in scientific exploration. This interplay between nothing and something sparks profound questions, bridging the physical with the philosophical. Across the world, different cultures interpret the concept of nothingness through their unique philosophical, spiritual, and scientific lenses. For instance, in Eastern philosophies like Buddhism, nothingness is intimately connected with the idea of emptiness, or sunyata. Here, emptiness is not simply the lack of existence. It reflects a deeper truth about the interconnectedness of all life and the impermanence of all things. This emptiness is not a void to fear, but rather an opportunity for enlightenment, a doorway to realizing the true nature of reality, where the boundaries of self and identity dissolve. In stark contrast, ancient Greek philosophers approached nothingness with skepticism. Thinkers such as Parmenides famously argued that nothing cannot come from nothing, insisting that being is the fundamental reality. For them, the idea of nothingness was often paradoxical or confusing, something to be questioned and doubted. This skepticism shaped Western philosophy for centuries, where debates around existence and non-existence remained central. Later philosophers like Jean-Paul Sartre explored these themes further, associating nothingness with existential dread and the human struggle to find meaning in a world that can feel empty. Indigenous cultures also offer unique perspectives on emptiness and nothingness, often integrating these ideas into their spiritual worldviews. Many Native American traditions, for example, embrace a harmonious relationship with nature, where emptiness is not a loss but a space full of potential. The absence of material things, or the emptiness found in the natural world, is seen as a fertile ground for creation, regeneration, and the ongoing cycle of life. It is a celebration of renewal rather than a symbol of finality. In modern times, particularly in art, literature, and psychology, nothingness has become a rich theme symbolizing hope, despair, or possibility. Writers and artists explore emptiness to probe existential questions, portraying it as a complex state that can evoke both fear and inspiration. As these cultural interpretations evolve, they reveal a diverse and vibrant tapestry of meanings, reflecting humanity's broad and ever-changing relationship with the idea of nothingness. At the heart of these scientific and philosophical explorations lies the concept of the quantum vacuum, a cornerstone of quantum field theory. This vacuum is often described as the field's lowest energy state, a place devoid of real particles. Yet, this description can be misleading if we equate it with pure nothingness. Far from being empty, the quantum vacuum is a seething arena of activity, filled with dynamic fluctuations and virtual particles that spontaneously pop into and out of existence. These fleeting particles create an ever-changing energy landscape, challenging classical notions of a void. The quantum vacuum possesses intrinsic properties such as vacuum energy, which influence physical phenomena in measurable ways. A striking example is the Casimir effect, where vacuum fluctuations produce a measurable force between two objects placed extremely close together. This effect powerfully demonstrates that even empty space is loaded with energy and potential. The relationship between the quantum vacuum and nothingness also extends to the origins of the universe. Some cosmological theories propose that the universe began from a state dominated by vacuum energy. Although this quantum vacuum lacks matter, its energy content suggests a capacity for creation and transformation, prompting deep questions about whether true nothingness can ever exist. In this light, the quantum vacuum reveals a nuanced and complex form of absence, one that is vibrant and full of possibility rather than empty. Quantum mechanics, through the study of the quantum vacuum, continuously reshapes our understanding of reality, blurring the line between being and non-being. Virtual particles, in particular, pose a fundamental challenge to our traditional views of empty space. These particles are temporary quantum fluctuations that exist for unimaginably brief moments, never directly observed, but whose effects are experimentally confirmed. Their presence means that empty space is not a lifeless void, but a dynamic stage where energy constantly fluctuates. These quantum fluctuations allow virtual particles to mediate forces and interactions between real particles. In quantum electrodynamics, for example, virtual particles serve as messengers of electromagnetic forces, enabling charged particles like electrons to interact. This remarkable insight reveals that what we once thought of as empty space is actually rich with potential and activity, constantly shaping the fundamental interactions of the universe, even if hidden from direct sight. In summary, our journey from philosophical reflections to cutting-edge quantum physics unveils a profound truth. Nothingness is never truly empty. It is a dynamic, living concept that carries within it the seeds of existence, creativity, and transformation, challenging and expanding the very way we understand reality itself. One of the most remarkable and thought-provoking phenomena in modern physics is the Casimir effect, a vivid demonstration of how the invisible world of virtual particles can produce tangible forces in what we often consider empty space. Imagine two perfectly smooth, uncharged metal plates placed parallel to each other, incredibly close, yet without any direct physical connection. According to classical intuition, nothing should pull these plates together. Yet when examined through the lens of quantum mechanics, these plates experience a mysterious attraction. This force arises because the space between them restricts the types of virtual particles that can spontaneously appear and disappear, a fundamental consequence of the quantum vacuum. The Casimir effect is much more than a curious oddity. It provides powerful experimental proof that empty space is not truly empty. Instead, it is filled with fluctuating energy fields, where virtual particles, tiny momentary blips of energy, constantly pop in and out of existence. These virtual particles create pressure differences between the inside space between the plates and the outside environment, effectively pushing the plates together. This is a direct, measurable force emerging from what we once thought was nothing. Discovered in the mid-20th century by the Dutch physicist Hendrik Casimir, this phenomenon fundamentally changes how we perceive the vacuum. The vacuum, once considered a barren void, reveals itself as a dynamic entity with properties that influence the physical world. The Casimir effect challenges the long-held notion that nothingness means the absolute absence of matter and energy. Instead, it invites us to view the vacuum as a seething, restless medium with a hidden complexity woven into the fabric of reality. More profoundly, virtual part and the Casimir effect push us to rethink the nature of existence itself. They suggest that much of the universe's behavior unfolds beyond the reach of our direct observations, in a realm governed by probabilities and fluctuations. This challenges the idea that reality must always be made up of tangible, observable things. Instead, it hints that what we call empty space is deeply connected to the workings of the universe, acting as a stage where quantum forces shape matter and energy in ways we are only beginning to understand. The significance of the Casimir effect goes beyond physics. It touches on philosophical questions about what it means for something to exist or not exist. It forces us to reconsider the boundary between something and nothing, showing that nothingness is not inert or empty, but a realm buzzing with activity and potential. The vacuum is not a passive backdrop, but an active participant in the cosmic dance, capable of exerting real forces and influencing physical objects. Beyond this, the Casimir effect has wide-reaching implications for theoretical physics, encouraging scientists to revisit assumptions about space itself. It compels us to expand our understanding of the vacuum from a simple emptiness to a dynamic, energetic medium where quantum fluctuations play a crucial role. This shift in perspective has ripple effects throughout physics, cosmology, and even philosophy, offering a new way to explore the deep mysteries of existence. In a related but even more cosmic scale, the discovery of dark energy adds another layer to our understanding of empty space. Dark energy is a mysterious form of energy that fills the universe and makes up about 70% of its total energy content. It was discovered through observations showing that the universe is not just expanding, but accelerating in its expansion. This unexpected acceleration suggests that empty space itself possesses a form of energy that drives the universe apart, working against the familiar force of gravity. Unlike the Casimir effect, which creates an attractive force at very small scales, dark energy produces a repulsive force on a cosmic scale. It pushes galaxies away from each other, speeding up the expansion of the universe and reshaping our understanding of cosmology. This discovery overturns earlier models that pictured the cosmos as static or slowing down, revealing instead a dynamic, ever-growing universe energized by what seems to be an invisible force permeating all of space. Taken together, the Casimir effect and dark energy show us that empty space is far from being a simple void. Instead, it is a complex arena filled with subtle energies and forces that shape the universe at every level, from the tiniest quantum fluctuations to the vast cosmic expansion. Our traditional view of nothingness is transformed into a rich tapestry of activity, reminding us that the universe operates in ways that defy everyday intuition and invite us to explore deeper truths about reality itself. Additionally, the influence of dark energy on what we consider empty space raises profound and intriguing questions about the very nature of the vacuum itself, especially when examined through the lens of quantum field theory and our evolving understanding of the quantum vacuum. By exploring dark energy, scientists uncover potential connections between this mysterious force and vacuum energy, which may hold the key to explaining the observed acceleration of the universe's expansion. Quantum fluctuations, which are tiny, spontaneous variations occurring even in seemingly empty space, characterize the quantum vacuum. Yet, dark energy adds another layer of complexity. It introduces a persistent energy density that pervades space and influences the universe on the grandest scales. This realization compels us to reconsider our notion of nothingness. Far from being an inert void, empty space is dynamic and filled with active forces that shape cosmic evolution. This developing understanding of empty space, reshaped by the presence of dark energy, challenges long-standing assumptions in cosmology. Instead of viewing the universe as a static backdrop against which events unfold, we now recognize space itself as a living, evolving entity, constantly influenced by powerful forces that we are only beginning to grasp. The intricate dance between dark energy and the vacuum of space opens a window into the deeper complexities of the cosmos, inviting us to continue investigating the fundamental nature of existence and the very fabric of reality. Attempting to truly visualize or grasp the concept of absolute nothingness is an inherently difficult task. Our minds are naturally conditioned to think in terms of existence, presence, and tangible experiences. One way to approach this enigma is to define nothingness as a fundamental absence, an utter lack of matter, energy, space, and even time. However, this definition quickly becomes abstract, slipping through the fingers of our understanding. Even the absence of everything stirs questions about how we perceive reality. To make this concept more accessible, we often turn to analogy and abstraction. Imagine a perfect void, a place without light, sound, or any physical presence whatsoever. This is akin to the idea of absolute darkness, where not even the faintest glimmer of light or hint of color exists. In this state, all our familiar sensory perceptions fail us, and we face a conceptual space stripped of every characteristic that we usually associate with being or presence. Philosophical explorations deepen this inquiry. Thinkers such as Martin Heidegger and Jean-Paul Sartre have examined the existential dimensions of nothingness, often linking it to the human experience. For them, nothingness is not just a void, but a profound state with deep implications. It is connected to feelings of emptiness or the void that can emerge during moments of profound reflection. These perspectives suggest that nothingness, paradoxically, can illuminate our understanding of existence itself, revealing hidden layers of meaning. Visualizing nothingness also prompts us to contemplate the boundaries of our universe. The observable universe, limited as it is, defines the edge of what we can see and measure. Beyond these boundaries lies a conceptual realm of incomprehensible emptiness. Yet even this emptiness remains tied to our notions of space, time, and energy, making the idea of true nothingness a paradox wrapped in the fabric of our cosmic understanding. Ultimately, engaging with the concept of absolute nothingness reveals that our cognitive frameworks are deeply rooted in the phenomena of existence. This makes the idea of pure absolute void a unique conceptual challenge, one that invites us to explore the unknown, pushing the limits of human thought and imagination. To approach this difficult concept, mental exercises can be valuable tools. They encourage abstract thinking and help challenge our conventional perceptions of reality. One such exercise is the practice of emptying the mind. By finding a quiet space and engaging in meditation or mindfulness, individuals consciously let go of sensory input and internal dialogue. As thoughts fade and mental silence deepens, participants may begin to sense a state of emptiness, resembling the characteristics of an absolute void. Another exercise involves visualizing layers of existence. Start by imagining the physical elements surrounding you, people, objects, and the environment. Then gradually strip away each layer, picturing them disappearing one by one. First the people, then the objects, then familiar sounds. The goal is to reach a perception of vast emptiness. Far from causing distress, this visualization can foster openness to the idea of an unfilled space, inviting profound reflection on the nature of absence and what it truly means to encounter nothingness. Paradox can serve as a powerful tool for exploring the profound and elusive concept of nothingness. Consider this. To define something as nothing inherently involves the use of language and thought, both of which are firmly rooted in existence itself. This means that the very act of naming or understanding nothingness paradoxically relies on the presence of something. Reflecting on this contradiction invites an empathetic acknowledgement of nothingness, positioning it squarely within the realm of being. By wrestling with these opposing ideas, the mind embarks on a journey toward a richer and more nuanced understanding of the delicate balance between existence and non-existence. Delving deeper, one can expand this intellectual exercise by engaging with philosophical texts that explore the nature of the void. The works of thinkers like Martin Heidegger and Jean-Paul Sartre offer penetrating insights into existential questions surrounding nothingness. Meanwhile, Eastern philosophies such as Buddhism present contemplative approaches to emptiness, inviting meditation on the impermanence and interconnectedness of all things. Immersing oneself in these diverse perspectives encourages reflection and opens new pathways for grappling with the abstract and often unsettling concept of the void. This mental exploration serves not just as an academic endeavor, but as a means of confronting and processing the profound existential questions that nothingness raises. Together, these exercises guide the individual toward approaching the idea of absolute void, gradually expanding the mind's capacity to engage with a concept that is at once challenging and intriguingly mysterious. Understanding complete nothingness poses immense challenges for the human mind, primarily because of how our cognition and senses are wired. Our perceptions are fundamentally anchored in the existence of things. As beings shaped by experience, we interact constantly with a world full of matter, energy, and sensory stimuli. From the earliest stages of life, we learn to make sense of reality through these interactions, making it extremely difficult to truly conceive of a state entirely devoid of existence. Moreover, our brains are naturally inclined to recognize, categorize, and interpret what surrounds us. This means the concept of nothingness, a total absence, pushes cognitive boundaries, often feeling like a paradox or even an impossibility. Language compounds this difficulty. Most languages evolve to describe objects, sensations, and experiences grounded in existence. When attempting to express nothingness, we run into linguistic limitations, as the words we use inherently reference something rather than nothing. This leads to confusion and inconsistencies when trying to fully grasp the idea of an absolute void. Philosophical inquiry further complicates our relationship with nothingness. Many traditions probe the nature of existence and non-existence, often arriving at profound, unresolved questions. Such exploration forces us to face existential dilemmas related to meaning, purpose, and reality itself. Confronting the notion of complete nothingness can provoke deep anxiety, as it challenges fundamental assumptions about life and the universe. In addition, the concept of nothingness often stirs existential dread. The prospect of a state completely devoid of life, meaning, or structure confronts us with our mortality and raises unsettling questions about the finality and significance of existence. These emotional responses can inhibit our ability to engage with nothingness purely on an intellectual level, creating a complex interplay between thought and feeling. Together, these cognitive, linguistic, philosophical, and emotional dimensions form a multifaceted barrier to comprehending absolute nothingness. Yet, experimental approaches such as sensory deprivation provide a fascinating window into this experience. In controlled settings like flotation tanks or soundproof, darkened rooms, sensory inputs such as sight and sound are drastically reduced or removed. These environments encourage intense introspection and alter how participants perceive reality. With external distractions minimized, individuals often report a heightened awareness of their internal thoughts, emotions, and bodily sensations. This unique state can evoke feelings of profound emptiness, or paradoxically, a surge of mental activity and emotional flood. Some describe these experiences as disquieting, while others find them profoundly liberating. This diversity of responses highlights the complexity and subjective nature of encountering nothingness when stripped of external influences. Through paradox, philosophical reflection, and sensory experimentation, the human mind gradually probes the profound enigma of nothingness. While complete understanding may remain elusive, the process expands our capacity to engage with one of the most fundamental and challenging concepts in existence. Moreover, sensory deprivation can lead to profound altered states of consciousness where the boundaries of time, self-identity, and reality begin to blur. Participants often enter realms where the usual markers of existence seem to dissolve, experiencing deep relaxation, dissociation, or even vivid hallucinations. These extraordinary states challenge our conventional understanding of existence and non-existence, as the awareness of one's own consciousness persists even without external stimuli. In this way, sensory deprivation experiments reveal that nothingness is not merely an empty void, but a complex, nuanced state that exists alongside consciousness itself. These experiments illuminate the intricate relationship between perception and the concept of nothingness. They demonstrate that the experience of emptiness can evoke a wide spectrum of emotional and cognitive responses. Individuals are pushed to confront what it truly means to exist when stripped of external influences. Through these explorations, participants gain valuable insights into the nature of reality, presence, and the human experience, enriching our understanding of nothingness beyond abstract theory. Consciousness plays a pivotal role in shaping how we comprehend nothingness. When we face the concept of nothingness, it is our consciousness that allows us to recognize the absence of things, rather than perceiving a mere void without definition. This awareness is essential. Without consciousness, we would have no insight into anything, neither the presence of objects nor the notion of emptiness itself. Our minds are constantly interpreting sensory information, constructing realities filled with meaning and sensation. Considering nothingness involves engaging with a state defined by the absence of these interpretations. It is consciousness that enables us to question and reflect on our experiences, to contemplate scenarios without matter or form, states that are often difficult to grasp or beyond our typical experience. Through the lens of consciousness, we explore and examine existence's boundaries, provoking curiosity and deeper philosophical inquiry. The concept of nothingness extends beyond philosophy into the realms of physics and cosmology. For example, scientists study the vacuum of space, often mistakenly considered simply empty. In reality, even the emptiest regions of space teem with quantum fluctuations, suggesting hidden potential energy. Consciousness allows us to navigate these complex theories, challenging our perceptions and broadening our understanding of reality far beyond everyday experience. This interplay between consciousness and nothingness sparks discussions in both scientific and philosophical fields. Our unique ability to conceptualize nothingness illustrates how deeply we can ponder existence itself. While grappling with the true nature of nothingness may seem elusive, our conscious experience equips us with the tools to engage these profound questions, deepening our appreciation of the universe and our place within it. Artists and creators have long grappled with the concept of nothingness through innovative expressions. In visual art, for example, blank canvases or vast empty spaces are often used to symbolize nothingness. This minimalist approach challenges viewers to confront their own thoughts and emotions about emptiness, inviting them to fill the void with personal interpretation. The deliberate choice of color, or the absence of it, becomes a powerful statement about absence and the spaces between existence. In literature, themes of nothingness frequently emerge in existential narratives where characters wrestle with life's meaning, identity, and the void between experiences. Writers use language to evoke feelings of alienation and desolation, crafting passages that emphasize what is missing or absent. This exploration invites readers on an introspective journey, reflecting on their own encounters with nothingness through the dilemmas and philosophical questions posed by the characters. In music, nothingness takes on an auditory dimension. Composers often incorporate silence, pauses, or sparse instrumentation to evoke a sense of emptiness or void. By weaving silence into their compositions, they transform absence into a powerful part of the musical experience. This interplay creates emotional contrasts that highlight feelings of isolation, contemplation, or suspense, deepening the listener's connection to the concept of nothingness. These artistic interpretations of nothingness across visual art, literature, and music transcend traditional boundaries. They invite audiences to explore existence's complexities, challenging us to confront uncomfortable truths and develop a richer understanding of the human experience. Through this engagement, we are encouraged to reflect on our own lives and the spaces that define them. Mathematics offers its own intriguing frameworks for examining nothingness, providing tools that deepen our understanding of absence and void. The concept of zero, for instance, represents a state of having no quantity. Far from being a mere placeholder, zero serves as a foundational element in countless mathematical operations, illustrating transitions between existence and non-existence. It shows how something can emerge from nothing. Set theory introduces the idea of the empty set, an entity containing no elements yet fundamental for discussing collections and operations in mathematics. This abstraction demonstrates how nothingness can still hold value and meaning, emphasizing that even absence exists within a structured framework. Beyond pure mathematics, fractals reveal how complexity can arise from seemingly empty spaces. Infinite patterns emerge from simple geometric rules, reinforcing the notion that nothingness can harbor infinite possibilities. These hidden structures within the void invite deeper philosophical inquiry into the nature of existence and the cosmos. In physics, theories involving vacuums and quantum mechanics further intertwine with these mathematical ideas. The vacuum of space is not truly empty, but a dynamic field filled with quantum activity. Mathematical tools help scientists describe particle behaviors and energy fluctuations that challenge traditional notions of emptiness. By applying mathematics, we transform nothingness from an abstract idea into a subject of rigorous scientific inquiry. This shift enriches our understanding of the universe and our role within it, showing that the void is far from simple. It is a rich, dynamic, and essential part of reality itself. The relationship between nothingness and the philosophical concept of non-existence is both profound and intricate, serving as a central theme in some of the deepest explorations of human thought. Nothingness is commonly understood as a condition or state completely devoid of any entities, a kind of absolute emptiness. Non-existence, however, points more specifically to the idea of something that simply does not exist or has never existed in any form. This subtle but important difference opens a wide gateway to philosophical inquiry, that inviting us to question the very nature of reality and the foundational fabric that makes existence possible. One major philosophical approach to nothingness comes from existentialism, a school of thought that grapples directly with the human condition. Thinkers such as Jean-Paul Sartre and Martin Heidegger delved into how nothingness shapes our awareness and being. For these philosophers, nothingness is not merely an empty void. It is intimately linked to freedom and choice. It is the absence that allows consciousness to step back and reflect on itself, questioning its own significance in the vastness of existence. This journey into understanding nothingness challenges individuals to face some of the most profound questions about life's purpose and meaning, especially when set against the backdrop of a universe that may seem indifferent or silent. Turning to non-existence, philosophical inquiry often confronts the puzzle of what it means for something to not be. Can we truly understand or imagine something that has never existed? This leads to complex questions about the nature of absence itself. Does non-existence hold any qualities or properties, or is it simply an impenetrable void beyond human comprehension? These questions push the boundaries of traditional ideas about reality, forcing us to rethink our assumptions about perception, existence, and even the cosmos as a whole. These concepts of nothingness and non-existence are not mere abstract theories confined to academic debate. They reach into the core of human experience, influencing how we view our place in the universe and the very limits of what is real. This philosophical contemplation has ripple effects beyond thought alone, impacting artistic creation, scientific exploration, and spiritual reflection. By deeply engaging with the ideas of nothingness and non-existence, we unlock new ways of seeing existence itself, confronting both the presence of being and the void that surrounds it. Dreams and meditative states offer particularly unique windows into the experience of nothingness. When dreaming, especially during lucid or deeply profound dreams, our minds can enter realms where the usual boundaries of time, space, and logic dissolve. These surreal experiences may feel like stepping directly into nothingness, allowing us to explore the inner depths of consciousness and the more unstructured, mysterious aspects of our minds. Dreams thus provide a vivid, though often fleeting, encounter with states beyond ordinary perception, opening a door to insights about existence and absence. Meditation, by contrast, is a more intentional practice that guides individuals towards stillness and mindfulness. Through quieting thoughts and sensory distractions, practitioners can enter states that resemble nothingness. In these moments of profound calm, feelings of separation from the self and the external world often arise, creating a sensation of merging with an all-encompassing void. Meditation invites us to release attachments, desires, and the noise of daily life, revealing the deep peace inherent in the absence of thought and chaos. Both dreams and meditation reveal that nothingness is far from being an empty void. Instead, it is a rich, fertile ground for exploration. These experiences challenge our usual notions of presence and absence, allowing us to form deeper connections with our emotions, thoughts, and even the universe itself. In dreams, the lack of structure may bring fears or unresolved issues to the surface, offering opportunities for personal insight. In meditation, the stillness can lead to profound revelations that expand one's perspective beyond the ordinary limits of the mind. Engaging with nothingness through these altered states cultivates awareness and introspection. It helps us see beyond the surface of reality, encouraging a deeper understanding of what it means to exist. In this way, the exploration of nothingness and non-existence becomes a transformative journey, inviting us to reconsider the essence of being and the silent void that frames our existence. Dreams and meditation open extraordinary doorways into the vast and mysterious realms of consciousness. Through these inner journeys, experiences of emptiness emerge, not as mere voids, but as fertile grounds for clarity and profound insight. They reveal the delicate dance between being and non-being, inviting individuals to explore the subtle dimensions where existence blurs into absence. As people navigate these territories, they often discover that what seems like nothingness actually harbors immense potential. A space rich with opportunities for personal growth, deeper understanding, and a renewed appreciation for the complex and beautiful fabric of life itself. Across various scientific fields, the concept of nothingness is visualized and understood in remarkably diverse and captivating ways. Each discipline, guided by its own tools and methodologies, offers a unique lens through which to view the elusive nature of emptiness. In the realm of physics, especially within quantum mechanics, researchers confront the enigmatic vacuum of space. While commonly imagined as an empty void, this vacuum is anything but vacant. Instead, it is a restless sea teeming with energy and fleeting particles that spontaneously appear and disappear. Advanced mathematical models and visual simulations bring these quantum fluctuations to life, challenging long-held ideas about emptiness and transforming the vacuum into a dynamic, energetic field where the fabric of reality is continuously in flux. In cosmology, scientists peer into the immense expanse of the universe, seeking to visualize phenomena such as cosmic background radiation, a faint glow left over from the universe's fiery birth, the Big Bang. This radiation acts as a subtle but powerful reminder that from what appears to be nothing emerged everything we know. By creating detailed simulations and cosmic maps, cosmologists trace the universe's evolution from an unimaginably dense and hot origin to the vast cosmos we observe today. Their visualizations depict nothingness not as emptiness, but as a realm bursting with potential and transformation, essential for grasping the story of our universe's beginnings and ongoing expansion. Philosophy of science intersects intriguingly with these scientific pursuits, probing the deeper implications of what these discoveries mean for our understanding of nothingness. Philosophers craft thought experiments and conceptual models designed to stretch the boundaries of how we perceive absence. Using diagrams and abstract visual tools, they attempt to bridge the intangible gap between theoretical ideas and lived experience. These intellectual explorations invite us to rethink what it means to be, to not be, and to exist within a space that seems empty, but is full of meaning and possibility. In the field of psychology, visualization techniques serve as powerful therapeutic tools, enabling individuals to confront and navigate their inner sense of emptiness or void. Therapists often guide clients through exercises that transform feelings of nothingness into vivid mental images. This process helps to make abstract emotional states more concrete and approachable, fostering healing, self-awareness, and emotional resilience. Here, nothingness becomes a personal landscape, a place to be explored and understood rather than feared or avoided. Together, these varied disciplines reveal that nothingness is far from a simple or static concept. Whether through the precise calculations of physicists, the sweeping vistas of cosmologists, the reflective musings of philosophers, or the intimate work of therapists, nothingness is visualized and experienced in countless deeply human ways. It becomes a bridge linking scientific inquiry with the profound questions of human existence. One fascinating idea emerging from modern cosmology is the theory of the Big Bounce. This model challenges the traditional view of the universe's origin as a singular event, the Big Bang, that occurred roughly 13.8 billion years ago. Instead, the Big Bounce suggests a cyclical nature of the cosmos. The universe undergoes endless phases of contraction followed by expansion. According to this view, the universe we inhabit today is the result of a rebound from a previous cosmos that collapsed in on itself. This cyclic process could have repeated infinitely into the past and will continue indefinitely into the future, implying a cosmos without a definitive beginning or end, but a continuous rhythm of cosmic birth, death, and rebirth. The Big Bounce offers a radical and poetic vision of existence, one where nothingness is not a final state, but a moment in an eternal cosmic dance, a pause before the universe bursts forth once again. Through this lens, emptiness becomes a dynamic, generative force, deeply woven into the very nature of reality itself. One of the most profound challenges that the Big Bounce theory poses to the traditional Big Bang theory lies in how each explains the origins of our universe. The Big Bang theory, which has dominated cosmology for nearly a century, describes the universe as beginning from a single, infinitely dense point, a singularity, from which space and time themselves emerged and expanded. Yet, this theory leaves unanswered some of the most fundamental questions, especially what, if anything, came before that initial explosion. According to the Big Bang view, time itself began with that event, making any notion of a before meaningless or impossible to define. In striking contrast, the Big Bounce offers a more dynamic and cyclic perspective. Instead of imagining the universe as springing from a one-time singular beginning, the Big Bounce proposes that our universe's current expansion is just one phase in an eternal cycle of cosmic contractions and expansions. Before our universe expanded, it underwent a contraction, collapsing inward until it reached an extreme density before bouncing back and starting to expand again. This cyclical model sidesteps some of the deep philosophical and scientific puzzles surrounding the absolute beginning of everything, suggesting instead a universe without a true beginning or end, but one that eternally cycles through phases of collapse and rebirth. The Big Bounce idea is deeply rooted in cutting-edge developments in theoretical physics, especially in areas like quantum gravity and string theory. These fields aim to unify general relativity, which governs the cosmos at large scales, with quantum mechanics, which explains the behavior of the tiniest particles. One notable model, loop quantum gravity, predicts that as the universe contracts, it reaches an ultra-dense state where classical notions of space and time break down and quantum effects take over. At this critical point, the universe doesn't collapse into a singularity, but instead undergoes a bounce, transitioning into a new phase of expansion. This shift in perspective could potentially answer some perplexing mysteries about the cosmos, such as what happens at the very beginning and end of the universe, and the nature of singularities predicted by the classic Big Bang scenario. The Big Bounce theory is still a hot topic in cosmological research and debate, pushing scientists to rethink accepted ideas about how the universe began and how it might evolve in the future. It opens the door to exploring countless possibilities about our universe's past and future, reflecting the ever-changing dynamic process of scientific discovery itself. Alongside the Big Bounce, another influential theory known as eternal inflation offers a fascinating way to understand what might have preceded our universe. Eternal inflation expands upon the inflationary model, which describes a brief period of extremely rapid expansion right after the Big Bang. However, unlike the traditional inflation model that describes a single, one-time event, eternal inflation proposes that this rapid inflationary process never truly stops. Instead, it continues indefinitely in different regions of an enormous multiverse, a vast cosmic landscape containing countless bubble universes. In this scenario, our observable universe is just one of many bubbles where inflation ended, allowing matter to cool and structures like galaxies, stars, and planets to form. Meanwhile, in other parts of the multiverse, inflation goes on, generating new bubble universes with their own unique physical laws and constants. This idea paints a picture of a cosmos where space and time themselves are in a constant state of flux, with new universes continuously budding off from the eternal inflationary sea. Before our universe as we know it came into being, conditions were marked by intense chaos, rapid expansion, incredibly high energy densities, and quantum fluctuations. These fluctuations were crucial because they sowed the seeds for the large-scale structures we see today, like galaxy clusters and cosmic filaments. Both the Big Bounce and eternal inflation challenge traditional views, inviting scientists to look beyond the singular event of the Big Bang and imagine a universe far more complex, mysterious, and infinite than previously thought. One of the most captivating ideas emerging from the theory of eternal inflation is its potential to unravel some of cosmology's deepest mysteries, especially concerning the initial conditions of our universe. Rather than starting from a simple, singular point, this theory suggests the pre-universe was a rich and intricate landscape teeming with possibilities. Within this vast cosmic terrain, causality stretches far beyond what we can observe today. Events occurring in distant regions that continue to inflate can subtly shape the cosmic microwave background we detect, leaving behind faint imprints of their influence. Eternal inflation also introduces a profound concept known as the multiverse. In this vision, our universe is merely one bubble among countless others, each potentially possessing its own unique set of physical laws and constants. This staggering possibility invites deep philosophical reflection about the very nature of reality. Could our universe be just one of an infinite collection of cosmic bubbles, each with its own story and character? This reshapes our understanding of existence itself, transforming the universe from a singular stage into part of an ever-expanding cosmic mosaic. Stepping beyond this, the renowned physicist Stephen Hawking, along with his collaborator James Hartle, proposed the groundbreaking no-boundary proposal. This idea challenges traditional notions of the universe's origin by suggesting there is no defined starting point in space or time. Imagine the universe not as a line with a beginning, but as the surface of a sphere. Just as a sphere has no edge, the universe, according to this model, has no temporal boundary, rendering the question, what happened before the Big Bang, meaningless. Time, in this sense, does not begin, but rather behaves like another dimension, blending seamlessly without a distinct origin. The heart of the no-boundary proposal lies in the idea that the universe originated from a quantum state that lacks classical properties. Instead of beginning at a singularity, an infinitely dense and chaotic point, the universe began as a smooth, finite state governed by the laws of quantum mechanics intertwined with general relativity. This state is described by complex mathematical constructs known as the Wheeler-DeWitt equations, which illustrate how the early universe can be viewed through the lens of quantum geometry. Practically, this means the initial conditions of our cosmos were shaped by quantum fluctuations, giving rise to a boundless variety of possible universes, each with its own evolutionary path. As the universe expanded from this quantum cradle, it smoothed out and developed according to familiar physical laws. This elegant framework allows physicists to sidestep difficult questions about what preceded the Big Bang or how time functions at the very edge of reality. The no-boundary proposal radically changes our cosmic perspective, suggesting that instead of emerging from a violent singularity, the universe blossomed gently from a quantum landscape where the concepts of origin and boundary lose their conventional meaning. This theory continues to inspire both scientific investigation and philosophical debate, embodying the innovative spirit at the heart of modern theoretical physics. Alongside these ideas, string theory offers another fascinating avenue for exploring the universe's earliest moments. Unlike traditional physics that treats particles as point-like dots, string theory envisions them as tiny, vibrating one-dimensional strings. These strings oscillate at various frequencies, each mode corresponding to a different fundamental particle or force. This elegant framework has profound consequences for our understanding of the cosmos, especially in scenarios describing what came before the Big Bang. According to string theory, our universe might be one among many existing in a larger multidimensional space called the bulk. Before the Big Bang, it's possible that the universe existed in a highly energetic and dense string gas state where countless strings interacted dynamically. These primordial interactions could have led to the formation of our universe as one bubble, emerging from the complex vibrations and settling patterns of these fundamental strings. This vision hints at a cosmos far richer and more intricate than previously imagined, where multiple universes with diverse physical laws coexist in an expansive multidimensional arena. String theory opens a window into a pre-Big Bang reality filled with energy, tension, and possibility, challenging our understanding of space, time, and the very fabric of existence. Together, the theories of eternal inflation, the no-boundary proposal, and string theory offer bold, complementary perspectives on the universe's mysterious beginnings. Each invites us to reconsider not only how the cosmos came to be, but also the vast, dynamic context in which our universe is just one remarkable part of an ever-evolving cosmic story. Furthermore, string theory introduces captivating concepts that push the boundaries of how we understand the cosmos. Among these ideas is the brain world scenario, which envisions our universe as a three-dimensional brain embedded within a higher dimensional space. According to this model, cosmic events, including the Big Bang, could have been triggered by interactions or collisions between these branes within the larger bulk of higher dimensions. Such collisions would release enormous amounts of energy, potentially sparking the expansion of our universe and creating a dramatic transformation from a pre-Big Bang state into the cosmos we inhabit today. This view challenges the traditional idea that the Big Bang was a singular, definitive beginning. Instead, string theory suggests that it might be just one event in a continuous cycle of interactions among strings and higher dimensional branes. This perspective encourages scientists to rethink the origins of the universe, proposing that the Big Bang could be a transitional phase driven by complex string dynamics rather than an absolute starting point. Although still deeply theoretical and mathematically intricate, string theory opens new horizons in cosmology, inviting exciting possibilities about what existed before the Big Bang and what may lie beyond it. Building on these themes, the cyclic model of the universe, proposed by physicists Paul Steinhardt and Neil Turok, offers a fascinating alternative to the conventional view of a singular cosmic beginning. This innovative theory suggests that the universe experiences an eternal sequence of expansions and contractions. Each cycle starts with a Big Bang-like phase, followed by a gradual expansion, eventually leading to another contraction, and then the next Big Bang. In this view, our universe is not a one-time occurrence, but part of an ongoing cycle of cosmic rebirth. Central to the cyclic model is the idea that the universe is made up of higher dimensional branes, a notion inspired by string theory. Our familiar three-dimensional universe is seen as one such brane that periodically collides with another, triggering a bounce or new phase of expansion. Each collision releases vast energy akin to a Big Bang, setting off a fresh cycle of cosmic evolution. This process could continue indefinitely, painting a picture of a universe that is ageless, constantly evolving through endless cycles. One of the major strengths of the cyclic model is its ability to address unresolved questions in cosmology. Traditional theories struggle to explain certain puzzling features, like why the universe appears so finely tuned or why it is currently expanding at an accelerating rate. Steinhardt and Turok's model integrates insights from both quantum physics and cosmology to offer solutions. For example, during the contraction phase of each cycle, irregularities in the universe could be smoothed out, preparing the cosmos for a new, more orderly expansion. This self-regulating mechanism provides a compelling way to understand the universe's large-scale structure and behavior. The implications of the cyclic model extend beyond physics, touching on deep philosophical questions about the nature of time and existence. By proposing that the universe undergoes infinite cycles of birth, death, and rebirth, this theory challenges the traditional narrative of a single beginning. It invites us to see cosmic history as an ongoing, never-ending process, one that transcends the limitations of conventional cosmological stories. Though still under active scientific investigation, this model opens new pathways to explore the mysteries of time, the origins of reality, and the laws that govern the vast cyclical dance of creation and destruction on a cosmic scale. Adding another layer to these explorations, loop quantum cosmology offers a unique perspective on what might have preceded the Big Bang. This approach draws from loop quantum gravity, a theoretical framework striving to unify general relativity and quantum mechanics. It radically changes our understanding of the universe's beginnings by suggesting that space-time itself is not continuous, but made up of discrete quantized units. In this framework, the universe did not emerge from a singular point of infinite density. Instead, it passed through a quantum bounce. Prior to the Big Bang, the universe existed in a highly dense state dominated by quantum fluctuations. As it approached this critical phase, the cosmos contracted to a point where the usual laws of physics no longer applied, but then rebounded, avoiding the traditional concept of a singularity. Gravity, within this quantum regime, plays a crucial role in guiding this cosmic rebound. Together, these cutting-edge theories, string theory, the cyclic model, and loop quantum cosmology, offer rich and dynamic visions of the universe. They invite us to reconsider not only how the cosmos began, but also how it might endlessly transform, evolve, and renew itself in ways that challenge our deepest assumptions about time, space, and existence itself. as the quantization of space-time prevents the formation of singularities that have long troubled traditional cosmological models, the implications of this approach are truly profound. Instead of the Big Bang representing the absolute beginning of time and space, loop quantum cosmology offers a revolutionary idea. The universe may have existed in a prior state characterized by contraction. This means that what we call the Big Bang is not a singular starting point, but a bounce, a transition from contraction to the expansion we observe today. This concept reshapes some of the deepest philosophical questions about time itself. Rather than time beginning at the Big Bang, loop quantum cosmology implies that time extends beyond it. New cycles of expansion could emerge following previous collapses, suggesting an eternal rhythm to cosmic evolution. By addressing the thorny issue of singularities, this framework not only removes a critical barrier in understanding the universe's origins, but also provides a powerful lens to analyze the early universe's dynamics. Emphasizing the quantum nature of space-time, scientists can explore how the universe evolved through different phases, potentially unlocking new insights into its structure and longevity. This vibrant area of theoretical physics continues to inspire research and debate, offering a captivating glimpse into the fundamental nature of reality and the events that shaped our cosmic origins. Another groundbreaking cosmological model that challenges conventional views of the Big Bang is the ekpyrotic universe theory. Developed by theorists including Paul Steinhardt and Neil Turok, this model proposes that the universe's evolution began not with a singular explosive event, but from the collision of two three-dimensional brains within a higher dimensional space. Instead of imagining the Big Bang as a sudden burst, the ekpyrotic theory suggests that our universe was born from the energy and dynamics created by this collision. In this framework, the pre-Big Bang state is not a void or singularity, but a realm filled with physical structures and energy existing in the higher dimensional space. Before the collision, the brains might have been closely aligned, with their interactions influencing the very fabric of space-time in ways that affect what we observe today. The collision produces the hot, dense conditions that match the early universe's characteristics, showing how the Big Bang can be seen as a natural consequence of these complex interactions, not an isolated beginning. One of the ekpyrotic model's remarkable features is its ability to resolve some of the long-standing problems of the traditional Big Bang theory, such as the flatness and horizon problems. By proposing a gradual transition from one state to another, this theory provides a new mechanism for the formation of cosmic structures. Density fluctuations, vital for the development of galaxies and stars, can arise from quantum perturbations occurring before the collision. This shifts the cosmological narrative from a simple explosive expansion to a nuanced dance of higher dimensional forces shaping the universe. The ekpyrotic theory also envisions a cyclical cosmos, allowing for multiple collisions and therefore multiple universes. This idea expands our understanding of cosmic origins and existence itself, suggesting that interconnected forces in higher dimensions govern the boundaries of our own universe. It invites us to rethink the nature of reality, where our universe is but one chapter in an ongoing dynamic story. Beyond these models, the concept of the multiverse opens an even broader perspective. It suggests that our universe may be just one of many, coexisting within a vast, interconnected framework. This idea challenges our understanding of what existed before the Big Bang and offers a wider stage for exploring cosmic origins. Different theoretical frameworks propose unique forms of the multiverse, each with its own implications for pre-Big Bang states. Inflationary cosmology envisions a multiverse formed by regions of space undergoing inflation at varying rates, creating countless bubble universes. Each bubble may have distinct physical laws and characteristics. Our universe could be one such bubble, formed by the decay of an inflating field, surrounded by endless regions still inflating, implying an infinite sea of universes. String theory offers another perspective on the multiverse through different configurations of brains and dimensions. Interactions between these brains could generate various universes, each with unique physical properties. In this view, the pre-Big Bang state might not just precede our universe, but coexist among a vast expanse of other cosmos, all intertwined yet separate. Together, these ideas suggest that existence transcends our usual understanding, encompassing countless realities that defy traditional boundaries. They challenge us to expand our imagination and scientific inquiry toward a universe far more complex and interconnected than ever imagined. Moreover, the epirotic model offers a striking vision that supports the multiverse hypothesis, presenting a universe born not from a singular event, but from the collision of brains, higher dimensional surfaces within realms beyond our everyday perception. Imagine countless such collisions, each sparking the birth of a distinct universe. In this grand picture, what we have traditionally called the Big Bang is merely a local event within a vast and intricate multiverse structure. This challenges the classical view of a singular origin and opens the door to an infinite array of universes, each with its own unique characteristics and laws. The concept of the multiverse pushes us to rethink fundamental cosmological ideas. It suggests multiple pathways for understanding the origins of our universe and invites deep philosophical questions about the very nature of existence. It calls us to explore the invisible boundaries that may separate these universes, to reconsider what time and space really mean, and to reflect on what it truly means to exist within a constantly expanding cosmos filled with endless possibilities. Adding to this cosmic tapestry, the theory of conformal cyclic cosmology, proposed by the eminent physicist Roger Penrose, presents an equally fascinating alternative perspective on the universe's evolution and the essence of cosmic time. Instead of viewing the Big Bang as a singular, absolute beginning, Penrose's model suggests that the universe undergoes an endless sequence of cycles, known as eons. Each eon evolves from the remnants of the previous one, creating a continuous, eternal process of cosmic rebirth. At the heart of this model lies the idea of conformality. Penrose argues that as the universe grows older and expands, its structure simplifies. Matter and energy dissipate, leading to a uniform state where the usual distinctions between time and space begin to fade. In this stretched-out, low-energy phase, the universe's geometry can be transformed mathematically through a process called conformal mapping. This transformation allows the end of one eon to blend smoothly into the start of the next, preserving the fundamental structure of space-time, while erasing the details that would identify past cycles. This elegant framework challenges the traditional narrative that the Big Bang marks the universe's absolute start. Instead, the Big Bang becomes a transitional phase, a bridge between the end of one cosmic cycle and the birth of another. The transition between eons is like a gradual fading of complexity, where remnants of earlier cosmic structures influence the new cycle but leave no direct memory behind. Penrose's conformal cyclic cosmology thus paints a picture of a universe without a true beginning or end, engaged in an endless cosmic dance, where each cycle leads naturally to the next. Though still debated within the scientific community, Penrose's theory offers profound insights into the nature of time, existence, and the fate of the cosmos. It challenges us to rethink reality itself and invites us to explore the universe's story across infinite spans of time. Meanwhile, the chaotic inflation theory adds yet another layer to our understanding of the cosmos, offering a mesmerizing glimpse into the universe's earliest moments before the Big Bang as we know it. According to this theory, the universe began as a vast expanse filled with energy undergoing rapid and random fluctuations. This inflationary phase wasn't uniform. Instead, it created a patchwork of regions inflating at different rates. Each bubble of inflation could develop into its own separate universe, complete with unique physical laws and constants. In this scenario, our observable universe, the one filled with galaxies, stars, and planets, is but a small part of a far larger, more diverse multiverse. Different regions might have followed different paths, creating an astonishing variety of universes within the same grand cosmic fabric. This picture challenges our place in the cosmos, showing us that the universe we know is just one manifestation among potentially infinite diverse realities. The chaotic inflation theory encourages us to look beyond the limits of what we can observe, prompting us to ask profound questions about the nature of reality itself. It reveals the unpredictable and often chaotic forces that shaped the early cosmos, deepening our understanding of how the universe evolved from its earliest fractions of a second. Together, these theories, the epirotic model, conformal cyclic cosmology, and chaotic inflation offer powerful imaginative frameworks for exploring the mysteries of existence. They invite us not only to rethink the origins and fate of the universe, but also to marvel at the vastness, complexity, and profound wonder of the cosmos. The concept of time before the Big Bang is among the most fascinating and puzzling mysteries in the field of cosmology. According to the standard model of the Big Bang theory, both time and space began together at the exact moment of the Big Bang, which occurred roughly 13.8 billion years ago. This means that asking what happened before the Big Bang might be a question that does not actually make sense because the very idea of time as we know it did not exist before that event. In essence, the Big Bang represents the birth of time itself. Some physicists propose the existence of a timeless state, a phase where our usual understanding of time simply does not apply. In such a timeless state, the normal sequence of events that depend on time flowing from past to future would be impossible because time itself was absent. This opens up fascinating discussions about alternative timelines or forms of existence, where the laws and rules that govern our universe today might not have held true. Other scientific theories explore the possibility of a cyclic universe, one that continuously undergoes cycles of expansion and contraction. In this model, the Big Bang is not the absolute beginning, but rather a transitional moment within an infinite loop of creation and destruction. This idea encourages us to think about what might have come before our current universe, even though such ideas remain speculative and difficult to prove. These explorations push the limits of our knowledge, inviting us to question the very nature of reality and the boundaries of scientific investigation. Our desire to understand what happened before the Big Bang reflects a deep human curiosity, not just about how the universe began, but about the essence of existence itself. It raises profound philosophical questions. How do we define time? What does before mean when time did not exist? What is the nature of reality in the absence of time? As we approach the moment known as the Big Bang singularity, our familiar concepts of time start to break down in dramatic ways. At this singularity, the equations that describe gravity and spacetime, based on Einstein's theory of general relativity, predict an infinitely steep curvature. This means the usual laws of physics cease to function as we know them, and time, as a measurable and meaningful concept, loses its meaning. In the earliest moments of the universe, the density and temperature were unimaginably high, creating extreme conditions unlike anything we experience today. Under these conditions, time no longer flows linearly from past to present to future. Instead, all events seem to merge into a single point, causing our standard ideas of chronology to collapse. Trying to apply conventional time-based thinking to this singularity leads to paradoxes and confusion. Concepts such as before and after lose their usual definitions, revealing the limits of current scientific understanding. While quantum mechanics gives us insight into the behavior of particles on very small scales, it has not yet been fully unified with general relativity, which governs the large-scale structure of the universe. New approaches like quantum gravity seek to bridge this gap. These cutting-edge theories aim to provide a framework for understanding how time and space behave under extreme conditions near the singularity. They hold the promise of eventually unraveling the mysteries surrounding the origin of time itself and helping us grasp the true nature of the universe's beginning. However, these theories remain firmly rooted in the world of theoretical physics, continuously stirring deep questions that push the boundaries of our understanding. The implications of this breakdown in conventional ideas of time and space challenge the very foundations of how we conceive reality itself. They compel us to rethink the fundamental nature of existence, urging thinkers and scientists to move beyond traditional limits and explore not only what happened before the Big Bang, but also what it truly means to experience time and space in a universe born from such extraordinary beginnings. The quest to understand time's role in the cosmos ultimately deepens our appreciation for the complex and delicate fabric of reality. It draws us into the profound mysteries that lie beyond the horizons of current scientific knowledge. One of the most intriguing ideas in this realm is the concept of imaginary time, introduced by the legendary theoretical physicist Stephen Hawking. Imaginary time is a mathematical tool designed to help make sense of some of the most puzzling aspects of cosmology, especially those related to the very early universe. Simply put, imaginary time treats time not as a straightforward, real number, as we usually perceive it flowing steadily from past to future, but rather as a complex number. This shift allows us to visualize time as a dimension similar to space, where the clear divisions between past and future can blur and even disappear. In Hawking's model, this concept plays a crucial role in addressing the notorious singularity at the Big Bang. By transitioning from real time to imaginary time, the infinite densities and extreme temperatures that characterize the singularity become smoothed out. Instead of imagining the universe having a sharp, sudden beginning, a precise edge, this approach allows us to picture the universe's starting point as a smooth, rounded surface. This leads to a revolutionary idea. The universe might be self-contained, without a clear beginning or end, eliminating the need for a singular starting moment. Imaginary time is vital in cosmological models that align with quantum mechanics. When Hawking applies imaginary time, the early universe can be envisioned as a kind of four-dimensional sphere known as the no-boundary condition. This framework invites scientists to consider a universe that did not emerge from a single point, but rather unfolded as a seamless continuum of space and time, expanding from a state of intense energy and density. Exploring imaginary time forces us to question our most basic assumptions about the universe's origins. It challenges the linear, one-directional view of time that dominates everyday experience and encourages a more intricate and subtle understanding of how the cosmos might have begun, its initial conditions, and the very nature of reality itself. This theoretical journey not only illuminates cosmic mysteries, but also enriches our grasp of time's fundamental role in shaping the universe we observe today. Different theories about what preceded the Big Bang approach the idea of time in diverse and fascinating ways, each offering unique perspectives on what might have existed before our observable universe came into being. One notable theory is the cyclic universe model, which suggests that the universe undergoes endless cycles of expansion, followed by contraction. In this view, time is not a straight line but a loop, with each cycle culminating in a new Big Bang and a subsequent era of expansion. This idea implies that time has no ultimate beginning, but is a continuous, ongoing process shaped by the universe's repetitive nature. Another intriguing proposal is the ekpyrotic scenario, which envisions our universe arising from the collision of two three-dimensional brains within a higher dimensional space. According to this model, time may have existed in some form before the Big Bang, evolving dynamically as these brains interact. Here, time behaves as a variable entity that changes alongside the universe's fundamental structures, suggesting a history and shape of time very different from our usual understanding. Quantum gravity theories also provide profound insights into the nature of time before the Big Bang. These theories explore how time and space might behave under extreme conditions where quantum effects dominate, such as at incredibly high energies. In this context, time may lose its familiar linear character and instead emerge as a phenomenon arising from more fundamental elements of the universe. Some ideas within these frameworks propose that at the Planck scale, the smallest scale of the universe, the very notion of time might dissolve into a web of interconnected quantum events, where the distinctions between past, present, and future no longer hold meaning. Together, these groundbreaking theories invite us to reimagine time itself, not merely as a steady progression of moments, but as a fluid, multifaceted dimension deeply intertwined with the universe's origin, structure, and evolution. This journey through the frontiers of physics opens a window into the profound mysteries at the heart of existence, inviting us to contemplate a cosmos far more complex and wondrous than we have ever imagined. Finally, the intriguing concept of timelessness surfaces in speculative debates about the state of the universe before the Big Bang. Some physicists propose that if the cosmos originated from a quantum state, the familiar notion of time as we know it might not have existed at all. Instead, the early universe could be described as a timeless realm, where space and events existed in a superposition of possibilities, an overlapping mix of all potential outcomes rather than a single fixed reality. This idea reveals a complex and mysterious relationship between time and existence, one that challenges our most basic intuitions and everyday experiences. Each of these theories highlights the rich diversity of scientific approaches to understanding time during the pre-Big Bang era. They push the boundaries of our knowledge, urging us to explore deeper into the true fabric of reality, far beyond what we can directly observe. Central to our understanding of time is the concept known as the arrow of time, a term used to describe the one-way direction in which time appears to flow. There are several arrows of time that capture different aspects of this phenomenon. The most well-known is the thermodynamic arrow of time, grounded in the second law of thermodynamics. This law states that in any isolated system, entropy or disorder tends to increase as time progresses. As a result, we observe physical processes moving from states of lower entropy, more ordered, to states of higher entropy, more disordered. This irreversible increase in entropy effectively gives time its unmistakable direction, from past to future. Another key arrow is the psychological arrow of time, which relates to our human experience. It explains why we remember the past, but not the future, as our consciousness is inherently anchored in the flow of experiences moving forward. Then there is the cosmological arrow of time, which aligns with the expansion of the universe itself, indicating that time moves forward in step with the growth and evolution of cosmic structures. When we venture into considering the behavior of the arrow of time before the Big Bang, things become particularly complex and fascinating. If time, as we understand it, began at the moment of the Big Bang, what does it mean to talk about time before that event? Some theories suggest that the arrow of time may not have existed in any conventional sense prior to the Big Bang. The conditions in a pre-Big Bang scenario could have been so radically different that our familiar notions of temporal progression and causality simply would not apply. Speculative models such as the cyclic universe theory propose that the arrow of time could have flipped direction with each cosmic cycle. This would mean that in each iteration of the universe, time might flow in a different orientation, sometimes forward, sometimes backward. This opens up a mind-bending possibility where time behaves in ways utterly alien to our everyday experience, fundamentally challenging what we think time really is. If time did exist before the Big Bang in some form, it might have been characterized by a state of extremely low entropy, which then transitioned into the higher entropy state we observe today. This shift would establish the directionality of the arrow of time, setting the stage for the temporal flow we experience now. Ultimately, the concept of the arrow of time invites profound questions about the nature of reality and existence itself. By probing how time functioned in those earliest moments, or perhaps even before the Big Bang, we deepen our understanding of the forces and mechanisms that govern the cosmos and our place within it. Through exploring these intricate relationships, we gain a richer and more nuanced perspective on the fundamental nature of time. Entropy plays a critical role in shaping our understanding of time's direction, especially in the context of the universe's origins. As mentioned, the second law of thermodynamics states that entropy in an isolated system tends to increase over time. This principle implies a natural progression from order to disorder, meaning systems evolve towards more chaotic and disordered states. Our perception of time is intimately connected to this increase in entropy, as we associate the flow of time with the movement from organized, low entropy conditions to increasingly disordered, high entropy states. Applying these ideas to the concept of time before the universe leads to some intriguing puzzles. If we view the Big Bang as the universe's origin, it is generally understood to represent of extremely low entropy, a highly ordered starting point. This means that prior to the Big Bang, the universe must have existed in a condition even less entropic than this, a concept that defies our usual understanding of cosmic evolution. Speculations about this pre-Big Bang state often involve ideas such as a high-energy vacuum state or other exotic scenarios where entropy is at a minimum. The notion that entropy could have been even lower than at the Big Bang itself provides a foundation for exploring what happens to the arrow of time if time truly began with the Big Bang. The rise in entropy from that point would mark our forward movement through time, like highlighting a transition from a highly ordered state to increasingly disordered arrangements of matter and energy. This raises a fundamental question. If entropy was so low in a pre-Big Bang universe, did time itself exist in a meaningful way? If the conventional arrow of time depends on the progression of disorder, then in such a low entropy condition, the usual sense of time's flow might not apply at all. In this way, our quest to understand time before the Big Bang forces us to rethink not only the origins of the universe, but the very nature of time and existence. It challenges us to imagine realities far beyond our ordinary experience and to push the limits of scientific imagination as we explore the deepest mysteries of the cosmos. Additionally, exploring the concept of entropy within the framework of pre-Big Bang theories opens up fascinating avenues in the ongoing discussions about cyclical models and multiverse theories. In these cyclical models, the universe is thought to undergo endless cycles of birth, evolution, and rebirth, where each cycle might somehow reset or alter entropy. This possibility offers a dynamic framework in which the concepts of time and entropy are not fixed, but continually redefined. Through these deep explorations, scientists and philosophers grapple with the complex interplay between entropy, time, and the very origins of our universe, shedding new light on the intricate fabric of reality itself. Understanding how entropy connects to these primordial conditions invites profound reflections on existence, challenging us to reconsider the fundamental structures that shape the cosmos. Quantum mechanics, in particular, offers a treasure trove of insights that could revolutionize our comprehension of time's nature, especially at the moment of the Big Bang. By bridging gaps in our knowledge, quantum mechanics highlights the extraordinary complexities woven into the universe's origins. At its core, quantum mechanics reveals that on the tiniest scales imaginable, far smaller than atoms, particles and phenomena behave in ways that defy classical intuition. This mind-bending framework compels scientists to rethink how time might have operated under the incredibly dense and energetic conditions surrounding the Big Bang. A key area where quantum mechanics meets cosmology is through the concept of quantum fluctuations. These are tiny, random changes in energy that could have played a crucial role during the early universe's high-energy state, characterized by uncertainty and probabilistic events. In this context, time might not have followed the straightforward, linear path that we experience daily. Instead, it may have manifested in a more fluid and complex manner, where multiple quantum possibilities coexisted simultaneously. This revolutionary idea challenges the traditional narrative of time as a simple, steady progression, and suggests instead that time itself could be an emergent property, shaped and formed by quantum interactions. Further investigations within the realm of quantum gravity strive to unify the principles of general relativity, our best understanding of gravity and large-scale structure, with quantum mechanics, which governs the smallest scales. Theories such as string theory propose that at the Planck scale, the unimaginably tiny scale where the laws of physics converge, space and time might become quantized. This means they could possess a granular, discrete structure rather than being smooth and continuous. If this is true, the implications for how we understand the universe's initial moments and the very nature of time could be revolutionary. The idea of a quantum realm woven into the fabric of space-time hints that near the singularity of the Big Bang, the point where densities and temperatures become infinite, our conventional notion of time may lose all meaning. Time, as we know it, could dissolve into something entirely different in this quantum-dominated domain. Moreover, when we consider time in the context of entanglement and non-locality, two fundamental features of quantum mechanics, new possibilities for understanding the early universe emerge. Entangled particles, no matter how far apart, remain connected in ways that defy classical explanations. This leads to intriguing questions about how events in the primordial cosmos might have been interconnected beyond our everyday experience of space and time. Such considerations suggest a more intricate, deeply interconnected nature of temporal progression, potentially unlike anything we observe in normal life. Quantum mechanics, therefore, invites us to radically re-examine the nature of time at the Big Bang. It urges us to reconsider not only the flow of time, but also its very characteristics. By integrating quantum principles into cosmological models, scientists are striving to unravel the deep mysteries surrounding the universe's origins. This journey pushes the boundaries of human knowledge, offering a chance to uncover profound insights into the fundamental mechanisms that govern reality and the delicate relationship between time and the cosmos. The so-called problem of time in quantum gravity is one of the most profound challenges at the forefront of modern physics. It arises from the struggle to reconcile how time is treated in two foundational theories: general relativity and quantum mechanics. In general relativity, time is woven into the four-dimensional fabric of space-time as a dimension closely linked with space itself. In contrast, quantum mechanics operates under principles where time does not have the same straightforward universal role. This discrepancy creates a fundamental puzzle for physicists attempting to develop a unified theory that can describe both the large-scale structure of the universe and the behavior of the tiniest particles. As this scientific endeavor continues, it forces us to confront and rethink some of our deepest assumptions about the nature of reality, time, and existence. The quest to understand time at the universe's birth is not just about physics. It touches on the profound question of what it means for anything to exist at all. One of the most profound puzzles in modern physics is the nature of time itself, especially when we dive into the strange world of quantum mechanics. Unlike classical physics, where time ticks steadily forward like a universal clock, the fundamental equations governing quantum systems do not treat time as a simple, independent variable. Instead, the evolution of these systems is captured by something called a wave function, which is a mathematical object encoding probabilities for different outcomes. This wave function evolves, but it does not require the familiar, continuous flow of time as we experience it in everyday life. This subtle but crucial difference creates major challenges when scientists try to reconcile quantum mechanics with the theory of gravity, especially when exploring the earliest moments of our universe. Imagine the moment of the Big Bang, a singularity where everything as we know it began. The extreme gravitational forces present then demand a theory that unifies space, time, and quantum particles into a single framework. But this is where our understanding of time gets murky. How do we even begin to describe time near a singularity where, according to conventional models, space and time themselves came into existence? The questions multiply. What does it mean for time to exist before the Big Bang or within the singularity itself? How does time's progression fit with the behavior of quantum states, which do not rely on a classical notion of time? Physicists are intensely debating these mysteries, trying to build models that can bridge these vastly different realms. Among the many ideas proposed, one fascinating hypothesis is that time may not be a fundamental dimension at all. Instead, time could emerge from deeper, more fundamental aspects of reality, possibly from the complex web of quantum entanglements and interactions between particles. Rather than being a fixed stage on which the universe's drama unfolds, time might be a kind of effective parameter that arises from the dynamic relationships within quantum states themselves. This exploration doesn't just push the boundaries of theoretical physics, it challenges us to rethink the very nature of reality. By unraveling the problem of time, scientists hope to unlock new insights into the early universe's workings and the fundamental fabric of space and time. Understanding how time emerges or functions in quantum mechanics could revolutionize how we perceive the cosmos and our place within it, revealing the intricate woven tapestry that makes up reality. Closely tied to the nature of time is the concept of causality, the idea that causes lead to effects in a clear, ordered sequence. Causality is a cornerstone of how we understand the universe. But the Big Bang introduces profound difficulties here as well. If time and space themselves started at this singular moment, then the neat chain of cause and effect we rely on becomes unclear. Did causality even exist before the Big Bang, or does the question itself lose meaning in that context? Some theories, like the cyclic universe model, propose that the cosmos undergoes infinite cycles of expansion and contraction. Within this framework, causality can be seen as a continuous process, with each cosmic cycle influencing the next. However, this raises tricky questions about what before means when time loops endlessly. How do cause and effect transform when each universe emerges from the ashes of the previous one? Further complicating matters, certain quantum gravity models suggest that at unimaginably small scales, around what is called the Planck scale, the traditional notions of time and causality may break down entirely. In this realm, quantum fluctuations reign supreme, and events may occur without clear cause and effect relationships. Particles can be entangled across space and time, or exist in superpositions where many possibilities coexist simultaneously. This possibility hints at a deeply interconnected reality, where influences transcend the classical links of cause and effect. It challenges our everyday intuitions, opening doors to new ways of thinking about how the universe operates at its most fundamental level. In confronting the problem of time, physics is not just probing a scientific question. It is confronting the very essence of existence and the mysteries woven into the fabric of the cosmos. Furthermore, if we delve into the fascinating idea of a timeless state, as proposed by some leading theoretical physicists, we encounter an even more radical break from our usual understanding of cause and effect. In such a state, time and space do not exist in the way we normally think of them. Without these familiar dimensions, the whole concept of causality, the straightforward chain of causes leading to effects, may simply dissolve. Instead of a neat linear timeline where one event causes another, there could be a vast landscape of potential realities. These possibilities are governed not by fixed outcomes, but by the strange and probabilistic rules of quantum mechanics, where events happen according to likelihoods rather than direct cause and effect relationships. This idea challenges our traditional view of the universe's history, especially before the Big Bang, when the usual fabric of time and space might not have existed at all. It pushes scientists and philosophers to rethink or even abandon the old frameworks that have guided us for centuries. By exploring these deep questions, we gain new insight into the universe's origins and the very essence of reality, revealing a complex web of relationships that might shape the cause in ways we have only begun to imagine. One of the foundational laws that frame this discussion is the second law of thermodynamics. This law tells us that in any isolated system, disorder or entropy tends to increase over time. This gradual shift from order to chaos is crucial to our understanding of time itself, providing a clear arrow that points forward. When we apply this law to the universe as a whole, it helps us explore what might have happened before the Big Bang and what that means for time. At the moment of the Big Bang, scientists generally agree that the universe began in a state of extremely low entropy, meaning it was highly ordered. As the universe expanded and evolved, entropy increased steadily. This rise in entropy underpins the very flow of time as we experience it, linking the passage of time to the progression from order to disorder. But what about before the Big Bang? When we try to imagine conditions prior to this event, we encounter intriguing puzzles about entropy. One possibility is that the universe existed in a state of even lower entropy before the Big Bang. But how can we make sense of a state where entropy is close to zero? Theorists speculate about exotic scenarios, such as fluctuations in a high-energy quantum vacuum, where the quantum fields that underlie all matter and energy might have behaved in ways beyond our usual understanding. These pre-Big Bang models suggest that while entropy shot up rapidly after the Big Bang, the initial conditions triggering our universe's birth were fundamentally different from what we see today. This forces us to rethink how time itself functioned or even existed in that mysterious realm before our familiar universe emerged. The second law of thermodynamics also plays a key role in more elaborate cosmological theories like cyclic or oscillating universe models. In these ideas, the universe doesn't just expand once, it goes through endless cycles of expansion and contraction. Each cycle might reset entropy to a low level, creating a universe where time loops rather than marches straight ahead. These concepts push us to consider that the relationship between entropy and time could be far more complex than the simple one-way flow we usually imagine. Ultimately, the second law remains a cornerstone in our attempts to grasp what pre-Big Bang time might have been like. It highlights how entropy shapes the direction of time while encouraging us to explore profound questions about existence, reality, and the fundamental rules governing the cosmos. Through this exploration, we enrich our understanding of how the universe grew from its earliest moments and how our very concept of time could be transformed. Another groundbreaking idea in this realm is the quantum foam hypothesis. This concept comes from quantum gravity and envisions space-time not as a smooth, continuous fabric, but as a turbulent sea of tiny fluctuations at unimaginably small scales, on the order of 10 to the power of minus 35 meters, known as the Planck scale. Proposed by physicist John Wheeler in the mid-20th century, the quantum foam idea suggests that beneath the calm surface of space-time lies a restless, dynamic world where particles and fields flicker in and out of existence in rapid, unpredictable ways. This foamy nature means that at these minuscule scales, space-time behaves radically differently from the stable, smooth continuum we experience. Instead, it is a chaotic, bubbling environment where the geometry of space-time constantly shifts and warps. The quantum foam hypothesis offers a compelling lens for imagining what the universe was like before the Big Bang. Rather than a singular point or a static void, the early universe might have been a swirling storm of quantum fluctuations, regions where space-time and matter were in constant, unpredictable motion. In this view, particles spontaneously appear and vanish, and patches of space-time interact in highly erratic patterns. Such a perspective radically redefines the pre-universe as a vibrant, energetic landscape full of potential. Some theorists propose that these quantum fluctuations could have triggered the Big Bang itself, acting as the seeds from which our universe blossomed. The implications of quantum foam reach beyond cosmology, challenging our deepest assumptions about space-time and reality. If space-time is truly foamy at its core, what does that mean for time and causality? If the very fabric of existence is in constant flux, the flow of time and the cause and effect links we take for granted might not be fundamental features of the universe, but emergent phenomena arising from this restless quantum chaos. This question opens a new frontier in our quest to understand the nature of time itself and the origin of everything around us. Furthermore, this perspective opens a fascinating pathway toward bridging the gap between quantum mechanics and general relativity. By exploring how these two foundational pillars of physics might converge, it offers the promise of uncovering a more unified theory that could fundamentally reshape our understanding of the universe. Central to this exploration is the quantum foam hypothesis, a captivating and imaginative lens through which to examine the conditions preceding the birth of the universe itself. Quantum foam invites us to envision reality not as a fixed, static backdrop, but as a dynamic, fluctuating state, an ever-changing sea of tiny, ephemeral bubbles of space-time. This concept challenges conventional ideas of space, time, and causality, pushing us to reconsider the very fabric of existence. By delving into these profound concepts, we gain not only a deeper grasp of the universe's origins, but also fresh insights into the fundamental nature of reality. One of the most crucial ideas when investigating the state before the Big Bang is dimensionality. It compels us to rethink the essence of space and time, particularly in realms where classical physics struggles to provide clear answers. In everyday life, we experience the universe as having three spatial dimensions combined with one dimension of time, together forming the familiar four-dimensional spacetime described by Einstein's theory of relativity. Yet when scientists attempt to probe conditions prior to the Big Bang, this neat framework starts to unravel. Many leading theories suggest that the universe's dimensional structure in its earliest moments was far more complex and mysterious than what we experience now. For example, string theory proposes the existence of additional spatial dimensions beyond the familiar three, potentially as many as 10 or even 11 dimensions in total. These extra dimensions might be compactified, curled up so tightly that they remain hidden from our direct perception. According to this view, the early universe could have existed within a higher dimensional space, where time, as we understand it, might not have been a meaningful concept at all. Instead, space and time may have formed a unified, multidimensional entity with far more degrees of freedom than our current scientific instruments or imagination can fully comprehend. The idea of a timeless state before the Big Bang leads to even more intriguing possibilities. Some theoretical models propose that space-time itself was not yet established, existing instead as an undifferentiated abstract realm where the familiar notions of distance and time had no meaning. In this primordial phase, the dimensions we rely on to describe reality were undefined, giving way to a more fundamental and elusive substrate. This radical reconceptualization of dimensionality shakes the foundations of traditional causal relationships. If higher dimensions played a role, the interactions and events we associate with three-dimensional space and linear time could have been governed by entirely different rules. Such a perspective may shed light on the profound transition from this primordial featureless state to the structured four-dimensional cosmos we inhabit today. Exploring dimensionality before the Big Bang invites scientists, philosophers, and curious minds alike to grapple with profound questions about the nature of reality and the underlying structure of the universe. It challenges us to reconsider what dimensions mean in a cosmic context, especially regarding the origins of space, time, and the forces that shaped our universe. Through this inquiry, we deepen our understanding of how dimensionality, causality, and existence itself intertwine in the grand cosmic narrative. Another vital concept in this quest is supersymmetry, a theoretical framework in particle physics that suggests a deep and elegant relationship between two fundamental classes of particles, bosons, which carry forces, and fermions, which make up matter. According to supersymmetry, every known particle has a partner particle, its superpartner, with differing spin properties. Although supersymmetry remains experimentally unconfirmed, it offers tantalizing possibilities for understanding the universe's earliest moments and the fundamental structure of reality. One of supersymmetry's most significant implications lies in its ability to resolve complex issues in high-energy physics and the behavior of quantum fields. If supersymmetry is valid, it could stabilize the masses of particles and reduce problematic quantum fluctuations, especially under extreme energy conditions, like those present at the universe's inception or during the Big Bang itself. This potential stability helps construct a clearer picture of the primordial particle interactions and the conditions before the universe's birth. Supersymmetry also plays a pivotal role in cosmological models that seek to explain the universe's rapid early expansion, known as inflation. For example, supersymmetric inflation theories propose that scalar fields linked to supersymmetric particles could have driven this explosive growth, transitioning the universe from a highly energetic and chaotic state to the smooth, expanding cosmos we observe today. This framework helps explain how the universe achieved the low entropy conditions necessary for the Big Bang and set the stage for all cosmic evolution that followed. In essence, supersymmetry weaves together threads of particle physics and cosmology, offering a comprehensive and elegant structure for understanding the universe's earliest phases. By illuminating how the pre-universal state could evolve seamlessly into the vast and complex cosmos we live in, it brings us closer to answering some of the deepest questions about the origins and nature of everything around us. Another profound aspect to consider is the potential connection between supersymmetry and higher dimensional theories, such as string theory. In these frameworks, the very nature of space could include additional dimensions beyond the familiar three, where supersymmetry plays a crucial role. These extra dimensions are not mere abstract ideas. They could actively shape the fundamental physical laws that govern our universe, even before it existed as we know it. Imagine a pre-universe landscape, a realm where these hidden dimensions influence the birth of reality itself. In this view, supersymmetry might dictate the properties of these extra dimensions, guiding the interactions and particles that emerged after the Big Bang. The presence and characteristics of these dimensions could have been decisive in determining the forces and matter we observe today. Supersymmetry, then, offers a rich tapestry of possibilities. It serves as a bridge, potentially unifying all particles and fundamental forces into a single elegant framework. By exploring how supersymmetry operates within these higher dimensional spaces, scientists hope to uncover deep connections woven into the very fabric of reality. This exploration is not just about understanding the universe's origins. It also pushes us toward grasping the fundamental principles that govern existence itself. At the forefront of these inquiries lie theories of quantum gravity, which offer intriguing insights into the nature of space before the Big Bang. These theories challenge the way we traditionally think about space, suggesting that it might not have functioned as a continuous expanse. Instead, quantum gravity attempts to reconcile the laws of quantum mechanics, governing the smallest particles, with general relativity, which describes gravity and the large-scale structure of the cosmos. One leading approach within quantum gravity is loop quantum gravity. This theory proposes that space is quantized, made up of tiny, indivisible loops or chunks rather than a smooth, continuous fabric. Visualizing space as composed of these discrete units leads to a radical reimagining of space-time at its most fundamental level. According to this framework, before the Big Bang, space could have existed in a highly non-classical form, filled with fluctuations and connections that defy everyday intuition. Meanwhile, string theory offers another perspective. It suggests that our familiar three-dimensional space might be embedded within a higher dimensional framework, where additional dimensions are compactified, folded up so tightly that they remain hidden from low-energy observations. These extra dimensions may have been key players in shaping the dynamics of space and time before the Big Bang. The interactions of fundamental objects like strings and brains in this multidimensional arena could have driven the transformations that eventually led to the universe we experience today. Some theoretical frameworks even propose the existence of a timeless or pre-space-time state. In this view, traditional notions of space and time lose their meaning before the Big Bang. Reality, instead, could be represented by fundamental quantum states without spatial or temporal features. Rather than a structured expanse, the pre-Big Bang conditions might resemble a quantum vacuum, a realm filled with infinite possibilities rather than fixed structures. This idea challenges the very foundation of how we understand space and time. It opens the door to a vision of reality as deeply interconnected and dynamic, far beyond our everyday experience. Through these bold theories, scientists seek not only to uncover the universe's beginnings, but also to explore the profound mystery of existence itself, pushing the boundaries of human knowledge into the vast unknown. Furthermore, approaches that draw upon the concept of quantum foam suggest that space itself may be a dynamic, ever-fluctuating medium. Within this medium, countless transient structures constantly appear and vanish, shaping interactions and events at unimaginably tiny scales. This vision helps us understand how, even in a primordial state before time as we know it existed, the very internal nature of space could evolve in profound ways. Such evolution could ultimately set the stage for the conditions that sparked the Big Bang, igniting the universe's rapid expansion and the formation of everything we observe today. Theories of quantum gravity paint a rich and diverse picture of what space might have been like before the Big Bang. These frameworks invite us to rethink our fundamental ideas about space, time, and the essence of reality itself. They suggest that the properties of existence at the universe's origins might defy our current understanding, existing in forms that challenge familiar concepts of geometry and causality. By exploring these ideas, scientists strive to unlock deeper secrets about the cosmic fabric and the fundamental forces that have guided the universe's evolution since its earliest moments. One particularly intriguing idea is the holographic principle. This concept proposes that all the information contained within a volume of space could be fully described by a theory that lives not inside that space, but on its boundary. In other words, what we perceive as a three-dimensional object might actually be a projection stemming from two-dimensional information encoded on a surface. This remarkable idea emerged from the study of black holes, where researchers found that the entropy, or the total information content of a black hole, is proportional to the area of its event horizon, the boundary around it, rather than the volume inside. The implications of the holographic principle stretch far beyond black holes and reach deep into the origins of the universe, especially when pondering the state before the Big Bang. If the entire universe can be imagined as a hologram, then it raises profound questions about whether the pre-universe state itself might have existed on a similar kind of boundary. This suggests that the information and physical laws governing our familiar three-dimensional reality could be encoded on a distant surface, hinting at the possibility that the pre-universe was not a tangible collection of matter or energy as we think of them, but rather a condensation of pure information. From this compressed informational state, the vast and complex cosmos we inhabit could have expanded and unfolded. Such a viewpoint opens thrilling possibilities. What form might this pre-universe information have taken? How could we, in principle, access or understand it? If the holographic principle can be integrated into our current models of physics, it could revolutionize our grasp of space, time, and reality itself. This principle challenges long-standing assumptions and beckons researchers to investigate how the boundaries of our universe might hold the keys to its creation, structure, and the laws that govern it. It pushes the frontier of cosmology and theoretical physics, as scientists work tirelessly to unravel the mysteries wrapped within the universe's very inception. Central to this exploration is the concept of information itself. In modern physics, information is increasingly seen as a fundamental building block of reality, intimately intertwined with the fabric of space and time. This perspective suggests that the pre-universe was not an empty void, but a realm rich with encoded possibilities, patterns of information that would eventually give rise to the universe we know. According to the holographic principle, the universe emerges from information residing on a boundary, meaning that before the Big Bang, all the essential features of our cosmos, its physical laws, fundamental constants, and intrinsic properties, existed in some abstract informational form. These pre-existing informational blueprints likely played a crucial role in shaping how the universe unfolded once space and time came into being. This profound relationship between information and reality challenges traditional views of existence. Instead of seeing the universe as made solely of physical matter, we might come to understand it as a manifestation of underlying information. This new outlook bears a curious resemblance to how information technology works today, where data and code form the basis of complex digital realities. By delving into these revolutionary concepts, scientists hope to reach beyond the limits of current knowledge and glimpse the true nature of the cosmos's origin, where information, space, and time intertwine in ways that stretch the imagination and redefine our place in the universe. Just as data becomes tangible through tools like computers or digital media, the universe itself might have emerged from pre-existing informational constructs that only became real at the moment of the Big Bang. Viewing the existence before the universe purely as a realm of information offers a revolutionary approach to understanding cosmology. If the universe was born from an intricate tapestry of information, then questions about its original conditions, structure, and evolution gain a new depth of meaning. This perspective invites us to explore what the universe truly is at its core, and how the essence of information shapes everything we perceive as reality. Such a viewpoint could lead to groundbreaking discoveries about the nature and origin of all that we observe. Quantum entanglement could be central to unlocking the mysteries of the pre-Big Bang state by revealing a form of connectivity between particles that transcends the familiar boundaries of space and time. Quantum entanglement occurs when particles become linked so deeply that the state of one instantly influences the state of another, no matter how far apart they are. This strange and fascinating phenomenon suggests that beneath the surface of our known reality, local interactions may not fully describe the relationships between the universe's fundamental components. This idea of entanglement becomes even more intriguing when we consider the universe's earliest moments, or what might have existed just before the Big Bang. Imagine a pre-Big Bang state woven from a quantum fabric, where entangled particles form a vast web of interdependence. Each particle could influence countless others, suggesting the cosmos was once in a unified, coherent state before it expanded into the distinct regions of space and time we see today. This interconnectedness hints at a kind of cosmic harmony that governed energy and matter before the universe took on its current form. Moreover, quantum entanglement raises profound questions about the nature of information in this pre-universal context. It is possible that the information encoded within these entangled states holds the blueprint for the universe that emerged after the Big Bang. This idea aligns with theories proposing that the universe began as a highly entangled quantum state, which then underwent a phase transition to become the classical dimensions and structures we experience now. And exploring quantum entanglement's role in the pre-Big Bang state could open new paths toward understanding how the universe transformed from a tightly correlated, energy-dense state into the expanding cosmos with its diverse and distinct regions. As scientists delve deeper into the connections between quantum mechanics and cosmology, entanglement may provide essential insights not only into the universe's origins, but also into the fundamental processes that drive its ongoing evolution. Different theories offer various views on how the fundamental forces of nature behaved or interacted before the universe began its expansion. The four known forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, described by our current physics, may have acted very differently under the extreme conditions of the pre-Big Bang state. In many theoretical frameworks, these forces were unified, operating as a single entity rather than the separate interactions we observe today. One leading idea is the grand unified theory, which suggests that at very high energy levels, the three non-gravitational forces, strong, weak, and electromagnetic, merge into one force. This implies that before the universe expanded, these forces were not distinct, but part of a more fundamental interaction. Experiments in high-energy particle collisions attempt to replicate conditions similar to those right after the Big Bang, providing clues on how these forces might have behaved. Additionally, theories like string theory propose that fundamental forces and particles arise from tiny vibrating strings instead of point-like particles. In this view, the different vibrational modes of these strings give rise to the forces and particles we know. Before the universe expanded, when these strings were compressed into an incredibly dense state, the characteristics of forces might have been very different, potentially merging into a single unified force that governed the primordial cosmos. Theories exploring quantum gravity also suggest that the very fabric of space and time itself could have undergone dramatic transformations near the singularity of the Big Bang. In such models, gravity might have behaved in an unusual way, with quantum effects dominating at incredibly small scales. These quantum gravitational phenomena could shed light on how forces interacted before expansion, providing crucial understanding of the universe's earliest dynamics. By examining these diverse theoretical frameworks, researchers are piecing together a more complete picture of how fundamental forces emerged from an interconnected quantum state. Each theory contributes unique insights into the universe's origins, illustrating how gravity and other forces may have transformed as the cosmos evolved from a singularity into the vast, complex structure we observe today. Symmetry stands as a fundamental cornerstone in unraveling the mysteries of the universe before the Big Bang, offering profound insights into the nature of fundamental forces and particles during the earliest moments of cosmic history. In physics, symmetry refers to a remarkable property where certain aspects remain unchanged or invariant when subjected to specific transformations. These symmetries can appear in many forms, including spatial symmetries related to position and orientation, temporal symmetries connected to time, and internal symmetries that govern particle interactions at a microscopic level. Together, these symmetries form the essential framework that supports our physical theories, especially when examining the incredibly high energy environments that have existed just prior to the universe's explosive expansion. Various theoretical models, notably grand unified theories, propose that before the Big Bang, the fundamental forces we observe today, the strong nuclear force, the weak nuclear force, and electromagnetism, were unified into a single symmetric force. In such extreme conditions, the distinctions between these forces blurred, merging into a harmonious and indistinguishable whole. However, as the universe expanded and cooled, this pristine symmetry was disrupted in a process called symmetry breaking. This process was not merely a cosmic curiosity. It was the critical event that fractured this single force into the distinct interactions that govern the universe today. This transformation from a uniform symmetric state to a broken symmetry state laid the groundwork for the rich diversity of particles and forces we now observe. Symmetry breaking is more than a theoretical abstraction. It is a driving mechanism that shaped the very fabric of our cosmos. The way in which this symmetry fractured influenced everything from the formation of fundamental particles to the large-scale structure of the universe. Diving deeper, the concept of symmetry plays a vital role in quantum field theory, where it helps explain how particles acquire their properties, including mass. One of the most notable examples is the Higgs field, a quantum field tied directly to symmetry breaking. Through its interaction with particles, the Higgs field endows them with mass, a process essential to the formation of matter as we know it. Looking back to the pre-Big Bang universe through the lens of symmetry, one can speculate that the universe began in a highly symmetric and invariant state. Such a condition would have set the stage for the physical laws and constants that govern our cosmos today. The implications of symmetry in this primordial context also offer clues about the mysterious Big Bang singularity itself. Some theories suggest that the universe emerged from a perfectly symmetric state where tiny fluctuations disturbed this balance, giving rise to the asymmetries necessary for the creation of complex cosmic structures like galaxies and stars. Understanding these early symmetry dynamics not only sheds light on the universe's infancy, but also holds the potential to reveal new physics beyond the current standard models. Equally intriguing is the relationship between symmetry and the cosmic dance of matter and antimatter. Our universe presents a puzzling imbalance. Matter overwhelmingly dominates over antimatter, despite the fact that physical processes produce both in equal amounts. When matter and antimatter meet, they annihilate one another, releasing pure energy. This annihilation raises deep questions about the initial conditions before the Big Bang. If the universe began with equal quantities of matter and antimatter, what caused the imbalance that allowed matter to prevail? After the Big Bang, the universe was a hot, dense sea of particles and antiparticles being created and destroyed in a continuous cycle. For matter to dominate today, something must have disturbed this equilibrium. One proposed explanation lies in a phenomenon known as CP violation, where the laws of physics behave slightly differently for matter and antimatter, allowing for a subtle preference for matter to be produced over antimatter during the universe's evolution. This violation is key to understanding why the cosmos contains so much matter and so little antimatter. Exploring the conditions before the universe's birth also invites us to consider the nature of vacuum fluctuations and quantum fields. In some models, the vacuum is not empty, but a seething background where pairs of particles and antiparticles momentarily pop in and out of existence. These fleeting fluctuations could have influenced the dynamics of the early universe, potentially playing a crucial role in tipping the scales toward matter's predominance. By studying these quantum processes, scientists hope to unlock further secrets about the pre-Big Bang environment and the forces that shaped everything we see today. In sum, the concept of symmetry and its breaking is at the heart of our understanding of the universe's origin and evolution. It provides a powerful lens through which to view the earliest cosmic moments, linking the microcosm of particle physics with the macrocosm of cosmology. As research advances, this profound principle continues to guide physicists in their quest to uncover the ultimate truths about the universe's birth, structure, and destiny. Furthermore, the intricate interactions between matter and antimatter hold the potential to greatly deepen our understanding of cosmic inflation, a dramatic and rapid expansion phase believed to have taken place moments after the Big Bang. Imagine different regions of space encountering varying amounts of matter and antimatter. This uneven distribution could have sparked localized zones where these particles annihilated one another. Such annihilations would add layers of complexity to how the universe evolved in its earliest moments. Delving into the connection between matter and antimatter within the conditions that existed before the universe as we know it offers crucial insights into the forces and processes that shaped everything we observe today. As scientists tirelessly explore these fundamental questions, they move steadily closer, not only to uncovering why the universe is dominated by matter, but also to revealing the foundational laws that governed its birth. The quest for observational evidence relating to pre-Big Bang theories is a fascinating journey fraught with complexity. It confronts the profound mystery of the universe's origins itself. Because the Big Bang marks a boundary beyond which direct observation is impossible, researchers rely on indirect clues and theoretical frameworks to piece together a picture of what might have come before. These models either support or challenge ideas about the universe's earliest state. Among the most significant sources of evidence is the cosmic microwave background radiation, a faint yet pervasive glow that blankets the entire cosmos. This relic radiation is essentially the afterglow left over from the Big Bang, providing strong support for the notion that the universe once existed in a hot, dense state before space and time began their ongoing expansion. Careful measurements of temperature fluctuations within this cosmic microwave background reveal rich details about the early universe, information about its density, composition, and how matter was distributed across space. Some pre-Big Bang theories, particularly those involving inflationary models, predict this rapid exponential expansion, and the observational data aligns remarkably well with these predictions, bolstering their credibility. Another vital piece of the cosmic puzzle comes from studying the large-scale structure of the universe, the sprawling distribution of galaxies and galaxy clusters. These massive formations offer clues about how matter coalesced and evolved following the Big Bang. Observations of the universe's expansion, especially through the redshift measurements of distant galaxies, clearly show that space itself is stretching. This confirms that the universe has been evolving from a very different, denser, and hotter state. Certain pre-Big Bang theories even propose specific patterns for how structures like galaxies form, allowing scientists to test these ideas against actual observations. However, not every piece of data fits perfectly with existing pre-Big Bang theories. One particularly puzzling challenge involves entropy, the measure of disorder in the universe. According to the second law of thermodynamics, entropy tends to increase over time. This raises a question. If the universe began in a highly ordered, low-entropy state before the Big Bang, how does that reconcile with the observed progression toward higher entropy today? Some models, like those proposing cyclic or oscillating universes, suggest that the cosmos may go through endless cycles of expansion and contraction, providing an alternative to the idea of a singular starting point. While evidence from cosmic microwave background radiation and the universe's large-scale structure supports certain pre-Big Bang theories, many mysteries remain unsolved, especially those involving entropy and the true nature of the universe's beginning. Ongoing research and refinement of observational data will continue to reshape our understanding of these enigmatic conditions that preceded the Big Bang. The cosmic microwave background radiation itself is a cornerstone of cosmological research. This astonishing phenomenon represents the afterglow from the universe's hot, dense infancy, occurring roughly 380,000 years after the Big Bang. At that time, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms. This recombination allowed photons, the fundamental particles of light, to travel freely through space, marking the moment when the universe became transparent to radiation. This radiation provides critical insights because its remarkable uniformity across the sky reveals that the early universe was astonishingly homogeneous and isotropic, meaning it looked nearly the same in every direction. The transition from a hot plasma state to a cooler, transparent universe set the stage for the formation of stars, galaxies, and eventually the complex cosmic web we observe today. However, slight fluctuations in temperature are also present, revealing tiny variations in density that would later evolve into the magnificent cosmic structures we observe today, such as galaxies and galaxy clusters. These subtle temperature differences imprinted on the cosmic microwave background act like a cosmic fingerprint, providing scientists with invaluable clues about the early universe. By studying these fluctuations, researchers can unlock the secrets of the initial conditions that shape the vast, large-scale structure of the universe we see now. Moreover, the cosmic microwave background offers critical insights into fundamental cosmological parameters, including the density and composition of the universe itself. Careful analysis of its spectrum allows scientists to estimate the relative amounts of ordinary matter, mysterious dark matter, and the enigmatic dark energy that together make up the cosmos. These measurements have revolutionized our understanding, revealing how these components interact and influence the universe's ongoing evolution across billions of years. In addition, the cosmic microwave background radiation carries profound implications for theoretical models, particularly the inflationary theory. This theory proposes that the universe underwent a rapid and exponential expansion during its earliest moments, smoothing out initial irregularities and setting the stage for the formation of structure. The patterns of temperature fluctuations observed in the cosmic microwave background align perfectly with predictions made by inflationary models, offering strong support for the idea that such an extraordinary expansion played a decisive role in shaping the early universe. Thus, the cosmic microwave background radiation stands as a cornerstone of modern cosmology, providing a direct and tangible link to conditions just moments after the Big Bang. As scientists continue to study this ancient relic radiation, they deepen their understanding of the universe's origins, its development, and the fundamental forces that have shaped its vast expanse. At the same time, gravitational waves represent an exciting new frontier for exploring the mysteries of the cosmos, including potential states before the Big Bang. These ripples in the fabric of spacetime are produced by some of the most violent and energetic events in the universe, such as colliding black holes or neutron stars. Unlike light, gravitational waves travel through space largely unimpeded by dust and gas, carrying pristine information about their origins. One of the most intriguing prospects of gravitational wave research is their potential to reveal details about the very early universe, especially during epochs like cosmic inflation. During this brief period, thought to have occurred within a fraction of a second after the Big Bang, the universe expanded exponentially at an incredible rate. If gravitational waves were generated during this time, their unique patterns could provide groundbreaking insights into the energy scales of inflation, the dynamics of the early cosmos, and the fundamental physical conditions that existed even before the Big Bang. Current and upcoming gravitational wave observatories, such as LIGO and the future space-based observatory LISA, aim to detect these primordial waves. Successful detection would not only confirm key aspects of inflationary theory, but could also shed light on the nature of the fundamental forces that governed the universe's evolution during those earliest moments. Gravitational waves might reveal the energy landscape driving inflation, and even hint at hidden symmetries in the laws of physics that prevailed at that time. Beyond this, researchers are exploring whether gravitational waves could provide clues about the transition from the quantum world to classical behavior in the universe's infancy. Understanding how the universe emerged from a quantum state and how space-time itself transformed could help bridge the gap between quantum mechanics and general relativity, two pillars of modern physics that remain difficult to reconcile. In this sense, gravitational waves may hold the key to unlocking the profound mysteries of the universe's birth and the fundamental nature of reality. By studying these ripples in spacetime, scientists hope to answer some of the deepest questions about the origin of the universe, the mechanisms that drove its rapid expansion, and the very nature of the forces that shaped our cosmos. As detection technologies improve, gravitational waves promise to open entirely new windows into the universe's early history, pushing the boundaries of knowledge beyond what current observations allow. However, testing theories about conditions before the Big Bang presents unique challenges. These challenges arise from the very nature of the Big Bang itself and the limitations imposed by the interplay of quantum mechanics and general relativity. Despite these difficulties, the pursuit of knowledge in this field continues to push the frontiers of science, promising transformative discoveries about the cosmos and our place within it. However, scientists employ a wide range of observational strategies, theoretical frameworks, and experimental methodologies to investigate these mysterious conditions that preceded the Big Bang. One of the primary approaches involves studying the cosmic microwave background radiation, often described as the afterglow of the universe just moments after the Big Bang. By carefully analyzing the tiny fluctuations in temperature within this radiation, cosmologists can reconstruct detailed information about the early universe's dynamic behavior. These subtle variations act like a cosmic fingerprint, offering indirect evidence that helps support or challenge different theories about what happened before the Big Bang. For example, researchers use this data to test models of cosmic inflation, a rapid expansion thought to have taken place fractions of a second after the Big Bang, or alternative scenarios that suggest specific pre-Big Bang conditions. The wealth of information gathered from space missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite has revolutionized our understanding of this early cosmic era, greatly enhancing the accuracy and scope of these investigations. Another cutting-edge method involves the detection of gravitational waves, ripples in space-time caused by massive cosmic events. These waves hold the potential to reveal critical insights about processes occurring in the infancy of the universe, including the elusive moments just before or during the Big Bang. If scientists succeed in identifying patterns of primordial gravitational waves, it would provide strong evidence in support of certain inflationary models or other hypotheses about the universe's earliest state. In addition to these observational efforts, theoretical physics plays a vital role in exploring pre-Big Bang conditions. Researchers delve into complex frameworks such as string theory, loop quantum gravity, and the ekborotic model. Each of these proposes different ideas about the universe's origin, suggesting scenarios ranging from multiple dimensions to cyclic universes. These theories produce testable predictions about what signals or phenomena we might observe in the present cosmos, and by comparing those predictions to real data, scientists can assess their validity. Laboratory experiments complement these cosmic observations by replicating conditions similar to those found just after the Big Bang. Particle accelerators like the Large Hadron Collider are instrumental in this area. By accelerating charged particles to speeds approaching the speed of light and causing them to collide, researchers recreate the extreme energy environments that existed in the universe's earliest moments. Observing how particles behave and interact under these conditions allows scientists to gain critical insights into the fundamental forces that shape the universe and to test theories related to pre-Big Bang physics. One of the central quests in this field is understanding the unification of fundamental forces. In today's universe, forces such as electromagnetism, the strong nuclear force, and the weak nuclear force act distinctly. But physicists believe that at the highest energies, present shortly after the Big Bang, these forces may have merged into a single unified force. Experiments conducted with particle accelerators probe these energy scales, providing clues about how this unification might have occurred. Such findings could dramatically improve our understanding of the universe's earliest phases before it expanded and cooled into the cosmos we observe now. While the challenge of studying conditions before the Big Bang is immense due to the inherent complexity and limits of current technology, the combined efforts of astrophysical observations, gravitational wave research, theoretical modeling, and high-energy particle physics offer multiple promising avenues. Through continuous advancements and discoveries, scientists aim to piece together a coherent and comprehensive picture of the universe's origins and the enigmatic conditions that existed before the birth of time itself. Additionally, particle collisions in powerful accelerators create extraordinary conditions that closely resemble the intense energy environment believed to have existed during cosmic inflation. This inflation was a dramatic and rapid expansion of the universe that occurred just moments after the Big Bang. By carefully studying the particles produced in these collisions and searching for any new forces or unusual signatures, researchers can gather vital evidence. This evidence either supports or challenges various theoretical models explaining how inflation happened. For example, scientists might uncover signs of entirely new particles or interactions that hint at the underlying mechanisms responsible for driving this explosive expansion. One key idea is symmetry breaking, where the fundamental forces that were once unified during the earliest moments began to separate as the universe expanded and cooled. These experiments help reveal how such separations might have occurred. Moreover, particle accelerators offer a unique window into other mysterious phenomena related to the early universe, such as the origins of dark matter and dark energy. By understanding how particles behave under these extreme high-energy conditions, researchers can formulate hypotheses about the unseen components that shape the universe's evolution over billions of years. High-energy collisions might also produce exotic forms of matter that no longer exist naturally, like quark-gluon plasma, a state where quarks and gluons, usually confined within particles like protons and neutrons, move freely. Studying this plasma provides essential context for understanding the transitions between different phases of matter in the newborn universe, revealing how it cooled and formed the particles that make up everything we see today. Particle accelerators are absolutely vital tools for exploring the conditions of physics before and immediately after the Big Bang. By recreating the intense energy environments that mimic the universe's formative moments, these facilities allow scientists to test the fundamental laws of nature, explore theories about the unification of forces, and probe the very nature of matter and energy that shaped cosmic history. Through these efforts, researchers are gradually piecing together a clearer, more comprehensive picture of how the cosmos began and the forces that govern its ongoing evolution. The anthropic principle adds a fascinating dimension to these investigations, especially when considering pre-Big Bang theories. This principle connects the fundamental properties of the universe to the fact that conscious observers, like humans, exist to observe it. It comes in two main forms. The weak anthropic principle suggests that the universe's observed properties are simply conditioned by the necessity for conscious beings to exist at all. The strong anthropic principle goes further, proposing that the universe must possess certain properties that inevitably allow for the emergence of life. When applied to theories about what happened before the Big Bang, the anthropic principle pushes scientists to explore how initial conditions and physical constants influence the development of a universe capable of supporting life. Many pre-Big Bang models, including those involving cosmic inflation or string theory, propose that countless possible universes might exist, each with different fundamental parameters. This leads to the concept of a multiverse, where our universe is just one among many, each governed by its own unique physical laws and conditions. Within this framework, the anthropic principle helps explain why we find ourselves living in a universe that appears so finely tuned for life. It might simply be that we inhabit one of the rare universes in the multiverse, where the conditions are just right to support conscious beings. By incorporating the anthropic principle into their studies, researchers can investigate how specific pre-Big Bang conditions might have led to a universe with the necessary properties for life to arise. For instance, scientists might explore how tiny asymmetries in the early universe or slight variations in fundamental constants could create a habitable environment. Such discussions not only deepen our understanding, but also help refine pre-Big Bang theories by pointing to measurable predictions. These predictions can then be tested against observations, bringing us closer to answering some of the universe's most profound mysteries. However, incorporating the anthropic principle into cosmological theories also brings with it a set of profound challenges that spark ongoing debate among scientists. Critics often highlight that the principle risks falling into circular reasoning. In other words, it uses the existence of observers, like humans, to explain the very structure of the universe, which can feel like explaining something by assuming the outcome beforehand. This means that while the anthropic principle can be a valuable conceptual tool guiding theoretical exploration of the universe's origins, it cannot stand alone. Instead, it must be carefully balanced with rigorous scientific methods, grounded in observable phenomena, and subjected to empirical verification. This balance becomes especially crucial when considering theories that seek to describe what happened before the Big Bang. If we use the anthropic principle to inspire models of the pre-Big Bang universe, these models must still be firmly rooted in data that we can observe or test through experiment. Without this, they risk drifting into the realm of speculation rather than science. Engaging deeply with the anthropic principle in the context of pre-Big Bang theories broadens our horizons, inviting researchers to contemplate how the initial conditions of the universe and potential scenarios involving multiple universes or a multiverse might have shaped the fundamental properties we see today. This approach pushes scientists to search for profound links between the fields of cosmology, theoretical physics, and the very existence of conscious life. Yet, despite these exciting theoretical avenues, our current technology limits how far we can peer into the universe's earliest moments. One of the most significant hurdles lies in our inability to directly observe the universe in its infancy, those first fractions of a second after the Big Bang. During that era, the universe was enveloped in an incredibly dense, hot plasma that was opaque to radiation. It wasn't until about 380,000 years after the Big Bang that the universe cooled enough to become transparent to light, allowing photons to travel freely through space. Because of this cosmic fog, scientists must rely on indirect evidence, such as the cosmic microwave background radiation, which offers a faint but valuable snapshot of the universe's state at that time, and the large-scale structure of galaxies and clusters, which emerged from those primordial conditions. Another technical barrier is the energy scale necessary to recreate the extreme conditions of the early universe. Particle accelerators like the Large Hadron Collider provide unprecedented data on high-energy particle interactions, but these energies still fall short of the levels thought to exist just moments after the Big Bang. Phenomena like cosmic inflation, a rapid expansion that smoothed out the early universe, and the unification of fundamental forces require energy scales far beyond our current capabilities. This gap means that while theoretical models can propose mechanisms for these processes, experimental tests remain out of reach. Additionally, the detection of subtle cosmic signals, such as primordial gravitational waves generated during inflation, poses its own challenges. These ripples in space-time could reveal critical information about the universe's earliest instance, but the sensitivity required to detect them, especially at very long wavelengths, exceeds the capacity of current telescopes and detectors. Although upcoming missions aim to improve this sensitivity until they become operational, our ability to probe these signals remains limited. On the theoretical front, ideas such as string theory and loop quantum gravity push the boundaries of our understanding of pre-Big Bang physics. These frameworks offer rich possibilities for describing the nature of space-time and the universe's origins, but remain largely untested. The environments and energy scales they describe are difficult to replicate in laboratory settings or observe directly in space, creating a gap between elegant mathematical models and empirical science. Despite these obstacles, advances in technology and research continue to narrow these gaps. The hope is that, over time, new instruments and techniques will allow us to test these theories more rigorously, providing clearer insights into the fundamental beginnings of the cosmos. Dark matter plays a vital role in this quest to understand the universe's earliest phases. Although it remains elusive and has never been directly observed, its existence is strongly inferred from the gravitational effects it exerts on visible matter, radiation, and the cosmic web's large-scale structure. By studying how dark matter interacts with normal matter, scientists can piece together clues about the universe's formative moments. Shortly after the Big Bang, the universe underwent rapid expansion and cooling, allowing primordial particles to form. These included familiar components like protons, neutrons, and electrons, as well as dark matter particles, whose exact nature remains a mystery. Unlike the ordinary matter that forms stars, planets, and living beings, dark matter is believed to be non-ionic and fundamentally different in its properties. The interaction between dark matter and normal matter likely influenced the earliest density fluctuations in the cosmos. These fluctuations served as the seeds from which galaxies and galaxy clusters eventually grew. Evidence of dark matter's critical role emerges vividly in the patterns observed in the cosmic microwave background radiation. The tiny temperature variations in this radiation represent a snapshot of the universe when it was about 380,000 years old. Analyses show that dark matter's gravitational pull created wells that helped gather normal matter, enabling the formation of the first cosmic structures. This intricate interplay between dark matter and ordinary matter continues to shape the universe's evolution, leaving imprints on the patterns and structures we observe today. Understanding these dynamics not only sheds light on the universe's origins, but also deepens our appreciation of the unseen forces shaping the cosmos. Furthermore, observations of the large-scale structure of the universe reveal that dark matter plays a crucial role in governing the behavior of galaxies and galaxy clusters. This invisible form of matter exerts a powerful gravitational influence that helps explain why galaxies rotate at speeds that seem inconsistent with the amount of visible matter they contain. Without dark matter's presence, the rapid spinning of galaxies would cause them to tear apart, yet they remain stable, pointing to an unseen mass that holds them together. This gravitational effect of dark matter provides essential clues about how matter was distributed in the early universe, offering scientists a window into reconstructing the timeline of cosmic evolution. Dark matter is deeply intertwined with our understanding of the universe's earliest moments, influencing the formation of structures, the variations in density, and the overall dynamics that shaped cosmic development. By studying how dark matter interacts with ordinary matter and shapes the grand architecture of the cosmos, researchers can uncover vital insights into the processes that took place shortly after the Big Bang. The distribution of galaxies across the universe is more than a random scattering. It carries crucial information about conditions before and after the Big Bang. Analyzing the arrangement of galaxies helps scientists infer the hidden structures and forces that governed the young universe. This exploration centers on the cosmic web, an immense network of galaxies, clusters, and filaments woven together by gravity and shaped predominantly by dark matter. One striking feature of galaxy distribution is how it reflects the tiny fluctuations in density that existed just after the universe became transparent to radiation, roughly 380,000 years after the Big Bang. These initial unevenness in matter density set the stage for gravity to pull matter together, forming the first galaxies and clusters. In this way, the cosmic structures we observe today act as a snapshot of the inflationary period and the evolution of those primordial ripples. Beyond revealing early cosmic history, the large-scale arrangement of galaxies offers valuable clues about the universe's expansion over billions of years. By examining the correlation between how galaxies cluster and the shifts in their light's wavelength, a phenomenon known as redshift, cosmologists can piece together the story of cosmic expansion and the mysterious influence of dark energy. Tracing the paths and positions of galaxies allows scientists to model how gravitational forces shape the observable universe and offers hints about the fundamental laws of physics at work in its infancy. Moreover, the study of galaxy distribution sheds light on the role of dark matter halos, massive, invisible structures within which galaxies form. The interaction and merging of these halos dictate how galaxies group and evolve into larger cosmic formations. Mapping where galaxies reside reveals the underlying dark matter framework that orchestrated the birth and growth of cosmic structures, reflecting conditions even before the Big Bang. Overall, the pattern of galaxy distribution acts as a rich tapestry of information about the universe's origins. By transforming the complex history of cosmic evolution into observable patterns, scientists gain crucial understanding of the initial conditions that shape the universe and the fundamental laws guiding its growth. Each galaxy's position is a vital piece of the puzzle, helping to reconstruct the early universe's history and the forces driving cosmic evolution. The remarkable fine-tuning of universal constants raises fascinating questions about the nature of reality before the Big Bang. The conditions and laws we recognize today were not yet established in that primordial state, leaving open profound mysteries about how the cosmos came to be and the rules that governed its earliest moments. However, pre-Big Bang theories dive deep into some of the most profound questions about the universe, suggesting that the constants we observe, those values finely tuned to allow galaxies, stars, and life to exist, might arise from far more intricate origins than mere coincidence. One of the most captivating ideas comes from string theory. Rather than envisioning the universe as made up of tiny point-like particles, string theory proposes that the fundamental building blocks are minuscule vibrating strings. These strings oscillate in ways that depend on the shape and size of hidden extra dimensions, dimensions beyond the three spatial and one-time dimension we experience every day. The way these extra dimensions are configured could give rise to different fundamental constants, creating a vast landscape of possible universes, each governed by its own unique laws and physical rules. Adding to this fascinating picture is the concept of the multiverse. This theory envisions our universe as only one among countless others, each with distinct constants and physical laws. In such a multiverse, the fine-tuning we observe might simply reflect a natural selection process among universes. Only those universes with the right conditions to form stars, galaxies, and eventually life would be capable of hosting observers like us. Thus, the universe we inhabit appears finely tuned not because it is special, but because it is one of many, and only certain universes are visible to beings capable of questioning their origins. Some other models focus on the realm of quantum gravity, which aims to unify the physics of the very large with the physics of the very small. These theories suggest that the universe might have undergone a dramatic transition before the Big Bang, emerging from a deeper quantum reality where classical physics and the constants we know today had not yet taken shape. During such a transition, the fundamental constants could vary, offering an explanation for the precise values we now observe. This view shifts the idea of fine-tuning from a puzzling coincidence to a clue pointing toward a profound underlying structure of reality that science has yet to fully grasp. What makes pre-Big Bang theories especially intriguing is how they challenge our everyday understanding of cause and effect. In our daily lives, events follow one another in a clear, logical sequence. Causes lead to effects, and actions unfold in time. But when we consider the origins of the universe, especially before the Big Bang, these familiar relationships break down. One of the most striking proposals is that of a singularity, a state where the laws of physics as we know them collapse. At this singularity, the normal concepts of time and space no longer exist, making the cause of the Big Bang something fundamentally beyond our experience. Without time, the usual notion of causality loses meaning, complicating any attempt to trace the universe's beginning in a straightforward, linear way. Quantum mechanics adds another layer of mystery. In the quantum world, particles behave in ways that defy classical cause and effect logic. Events may happen without a clear cause, or be influenced by phenomena that elude direct observation. Some pre-Big Bang models incorporate quantum fluctuations, random, spontaneous changes in the quantum field that could have triggered the birth of matter and energy itself. These ideas suggest that the fabric of the universe might be capable of generating events without following the neat causal chains we rely on in the macroscopic world. Together, these pre-Big Bang perspectives invite us to reconsider our deepest assumptions about time, space, and the nature of existence. They open a door to a realm where the universe's birth is not just a simple event, but a complex tapestry woven from the interplay of hidden dimensions, multiple universes, and quantum mysteries. The quest to understand this realm remains one of the greatest scientific adventures, pushing the boundaries of knowledge and imagination as we seek to uncover the ultimate origins of reality itself. Furthermore, when we consider the idea of a multiverse, the entire concept of cause and effect becomes far more complex. If our universe is merely one among countless others, the events that sparked the Big Bang might have taken place in a completely different realm, disconnected from the reality we observe. This possibility pushes the origin of everything we know even further away from our grasp. The multiverse theory suggests that entire universes could spontaneously emerge through quantum processes, mechanisms that do not follow the familiar rules of cause and effect that govern our everyday experience. This radical shift forces us to rethink our most basic assumptions about existence itself, expanding the horizons of our understanding of the cosmos to unimaginable scales. On another front, models of an eternal universe present an equally profound challenge to traditional ideas about creation. Instead of accepting the Big Bang as a singular beginning, these theories propose that the universe has no true starting point. Instead, it exists in a continuous cycle of creation and destruction, endlessly renewing itself. This perspective invites us to reconsider what it means for something to be created at all. If the universe is eternal and self-sustaining, then creation is not a single historical event, but a perpetual process that never truly ends. For example, cyclic models suggest the universe goes through infinite cycles of expansion followed by contraction. Each of these cycles leads to a new phase of cosmic existence, making the universe a dynamic, evolving system rather than a one-time miracle. Instead of searching for a single moment when everything began, these models ask us to view the cosmos as an ever-changing dance, where new stars, galaxies, and even fundamental forces arise repeatedly throughout eternity. These ideas also lead to deep philosophical and existential questions. If the universe is eternal and constantly regenerating, what does that mean for human life, our purpose, and the meaning we assign to existence? The belief in an everlasting cosmos could encourage a more holistic view of reality, one that values interconnectedness and continuous transformation instead of a simple beginning-to-end timeline. This shift might influence spiritual and philosophical beliefs, prompting people to feel a stronger connection to a universe that has always been here, in some form, transcending time and conventional understanding. Scientifically, the theories of an eternal universe inspire new lines of inquiry. Researchers might explore different physical laws that govern an infinitely lasting cosmos, investigating how time, energy, and cosmic structures behave across endless cycles. Understanding the mechanisms behind perpetual cosmic change could unlock fresh insights, not just in cosmology, but in fundamental physics itself. The implications reach beyond science, blending into philosophy and spirituality, as humanity grapples with its place in a universe that may have no end. Pre-Big Bang theories intersect intriguingly with various religious cosmologies, sometimes aligning with, and at other times challenging long-held spiritual views on the universe's origin. Many religions tell stories of creation rooted in a specific moment, often the act of a divine power bringing everything into existence. In contrast, pre-Big Bang ideas suggest the universe existed in some form before what we consider the beginning, embracing concepts like eternal existence or cyclical creation. For instance, certain ancient philosophies and religious traditions, such as Hindu cosmology, describe the universe as eternal, endlessly cycling through phases of creation, preservation, and destruction. These views resonate strongly with cyclic universe models, which see creation as an ongoing process of renewal rather than a one-time event. This similarity opens up a rich dialogue between scientific perspectives and spiritual interpretations, highlighting the universe as a dynamic, living entity. On the other hand, many religious traditions influenced by Judeo-Christian beliefs emphasize a clear beginning, where the universe was created out of nothing, known as creatio ex nihilo. This concept frames creation as a deliberate act of divine will, executed with purpose and design. Pre-Big Bang theories, which imply the universe existed in some way before our current observable conditions, challenge this view. They raise profound questions about the role of the divine in creation and whether the existence of everything depends on a singular initial cause or if it has always been in some form. In sum, these evolving ideas about the universe, whether through the lens of the multiverse, eternal cyclic models, or pre-Big Bang scenarios, transform our understanding of existence, encouraging an ongoing exploration that bridges science, philosophy, and spirituality. They compel us to reconsider our place in a cosmos that may be far more complex, dynamic, and timeless than ever imagined. Additionally, the implications of multiverse theories can lead to significant divergences from traditional religious perspectives. This concept suggests that instead of just one universe, there may be countless universes, each with its own unique laws and constants. Such a possibility complicates the long-held idea of a singular, purposeful act of creation. These ideas often open deep discussions about the nature of divinity and question the uniqueness of human existence in the grand cosmic picture. Exploring models that consider what happened before the Big Bang invites a profound rethinking of classical cosmologies. It encourages an ongoing dialogue between science and faith, showing how our understanding of the universe is constantly evolving and challenging traditional beliefs about creation. The very possibility of a multiverse brings with it a flood of philosophical questions that challenge our basic understanding of existence, reality, and humanity's place within it. One of the most fundamental questions revolves around the nature of reality itself. If multiple universes exist side by side, each with different physical laws, constants, and even separate histories, what does this mean for our concept of what is real? The existence of parallel universes complicates the idea that our experiences and the world we know are unique or original. It forces us to reconsider the importance and meaning of our choices and experiences, knowing that there may be an infinite number of alternative realities where different outcomes play out. Another deeply intriguing question involves the nature of existence and the criteria we use to define life and consciousness. If there are countless universes with varying physical laws and conditions, how can we determine which realities might support sentient beings? This raises the philosophical challenge of whether life is a rare phenomenon unique to our universe or a common occurrence spread throughout many realities. Such a perspective could dramatically alter our understanding of consciousness itself and lead us to consider whether forms of experience in other universes might be completely different from what we know, potentially challenging human-centered views of life. The concept of free will also faces intense scrutiny within a multiverse framework. If every possible outcome of every choice exists somewhere in these countless universes, does that diminish the importance of the decisions we make? Are we simply players in a vast cosmic drama where every possibility is already unfolding in some reality, making our personal agency seem meaningless? On the other hand, supporters of multiverse theories might argue the opposite, that the existence of multiple outcomes actually highlights the significance of each decision. Each choice could be seen as creating a new branch of reality, emphasizing moral responsibility and the weight carried by human actions. Finally, ideas about purpose and meaning take on entirely new dimensions in the context of a multiverse. If our universe is just one among many and life can arise in various forms across different realities, what does this imply about humanity's role in the vast cosmic scheme? Questions about purpose become complex and multifaceted, compelling individuals to consider whether meaning exists on a universal scale or if it arises uniquely within each separate reality. This exploration not only challenges traditional metaphysical beliefs, but also encourages a deeper reflection on our motivations, values, and sense of significance within the broader tapestry of existence. Pre-Big Bang theories play a crucial role in shaping these evolving views of the universe's purpose. Historically, many philosophical and theological traditions have assigned a distinct purpose to the universe, often rooted in the belief that it was created by a divine entity with specific intentions. However, when examining models that look before the Big Bang, which suggest the universe could be eternal or exist in a state of constant change, the idea of purpose becomes far more nuanced and complex. One emerging perspective from these pre-Big Bang theories is that the universe's existence might not depend on a predefined purpose or goal. Instead, the universe may be seen as a dynamic system, governed by natural laws and ongoing processes, where existence itself is a continuous event rather than a goal-oriented outcome. This view challenges human-centered beliefs that place humanity at the center of a grand cosmic design. Within this framework, life and consciousness are not the ultimate aims of creation, but phenomena that arise naturally within an ever-evolving cosmic landscape. Furthermore, cyclic models of the universe propose a fascinating idea, that the cosmos undergoes infinite cycles of expansion and contraction. This perspective transforms existence into a series of continual rebirths, challenging traditional views of a fixed, unchanging purpose. In such a vision, purpose becomes fluid and dynamic, shifting with each new cycle. Each cosmic cycle offers opportunities for different forms of structure, intelligence, and experience to emerge. This complexity complicates the idea of a single, overarching purpose governing all reality. Within this evolving cosmic dance, individuals may be invited to create their own meanings during each cycle, fostering a deeply personal understanding of purpose tied to the human experience. On the other hand, some interpretations of pre-Big Bang theories encourage a renewed sense of wonder and exploration of the cosmos itself. The absence of a clearly defined cosmic purpose does not mean life or existence lacks significance. Rather, it opens a vast space for curiosity, discovery, and intellectual pursuit. People may find meaning in seeking knowledge about the universe, trying to understand its intricate complexities, and forming relationships in the face of an immense and mysterious existence. This perspective offers a sense of agency. Even in a universe without a predetermined teleological goal, individuals have the power to imbue their lives with purpose. Ultimately, pre-Big Bang theories push us to rethink what it means to exist, inviting diverse interpretations of purpose that align with an ever-expanding cosmic view. The implications of these pre-Big Bang models for the concept of free will are both profound and multifaceted. They invite us to reconsider fundamental questions about choice, determinism, and the nature of the cosmos itself. At the core of this discussion lies the relationship between the origins of the universe and human agency. If the universe operates according to laws that emerged from conditions before the Big Bang, then what does this mean for the freedom of our decisions? Are our choices predetermined by these fundamental processes, or does genuine free will exist independently? One crucial consideration involves the nature of causality. If pre-Big Bang models suggest that time and space, as we understand them, did not exist before the Big Bang, then the traditional chain of cause and effect becomes blurred. This could imply that our decisions are influenced by factors beyond our comprehension, painting a deterministic picture in which every action results from prior states. If free will is an illusion created by complex interactions within a grand deterministic framework, then our understanding of personal responsibility and moral agency might be challenged. Conversely, some interpretations of pre-Big Bang theories, especially those incorporating principles of quantum mechanics, offer room for free will within the probabilistic nature of quantum events. At the quantum level, events are not strictly determined, but can occur with a degree of randomness. If the universe is fundamentally indeterminate at its core, this inherent uncertainty could serve as a foundation for free will. It would allow humans to make choices that are not rigidly bound by pre-existing conditions. In this view, individual agency emerges as a complex interplay between deterministic laws and random quantum events, providing a sense of autonomy in decision-making. Moreover, if we consider cyclic universe models, where the cosmos repeatedly expands and contracts, this could suggest a broad spectrum of possibilities for existence and choice. Each cycle might present a new set of circumstances and paths, allowing individuals to make different decisions. Here, free will manifests as the ability to navigate choices within a dynamic cosmic framework, signaling that while universal structures impose constraints, the potential for unique experiences and decisions persists. Ultimately, the interplay between pre-Big Bang theories and the concept of free will invites us to examine the complexity of human experience. As we ponder agency within an intricate and layered universe, we are led to contemplate the delicate balance between determinism and freedom. This reflection touches on the profound responsibilities and capacities that come with making choices amidst a vast and mysterious cosmos. Pre-Big Bang models also deeply influence our perspective on the uniqueness of our universe. They challenge the long-standing idea that our cosmos is a singular, exceptional creation. One significant implication is the idea of a multiverse, a vast collection of many universes, each with its own physical laws, constants, and characteristics. This concept directly questions the singularity of our universe, suggesting that what we perceive as unique might be just one manifestation among countless realities in an immense cosmic tapestry. When considering cyclic models, which describe the universe as passing through endless cycles of birth, growth, decay, and renewal, the question of uniqueness becomes even more intricate. If our universe is just one in a long series of rebirths, then the traits we often regard as special, such as the formation of stars, galaxies, and even life, might be replicated or transformed across infinite iterations. This viewpoint encourages us to reevaluate how we understand significant cosmic events. Instead of seeing our universe's features as rare or one of a kind, cyclic models invite us to consider them as part of a broader, ongoing cosmic process that stretches beyond any single lifetime of the cosmos itself. Moreover, the quantifiable nature of eternal universe scenarios deepens the ongoing conversation about the uniqueness of our existence. Imagine a universe with an infinite timeline, where every conceivable event and outcome could happen. In such a vast cosmic expanse, the singular circumstances that define our life might be just one occurrence among countless possible realities. This broader perspective has the power to challenge the traditional view that our cosmos holds a special, singular significance. Instead, it suggests that many similar or even wildly different versions of existence could be unfolding somewhere else, either right now or somewhere in the infinite stretches of the future. This idea might initially feel like it diminishes the importance of our place in the universe. However, it does not strip away meaning or beauty from our experience. On the contrary, recognizing the possibility of multiple universes or cosmic cycles can heighten our appreciation for the remarkable, perhaps even fortunate nature of our own existence. Understanding that our universe may share characteristics with countless others invites a sense of awe and curiosity about what these connections might reveal. It encourages us to explore not only what makes our cosmos unique, but also what it shares with the vast cosmic landscape. Pre-Big Bang models and other cosmological theories that challenge the notion of a singular universe open the door to profound questions about reality. They invite us to see our universe as part of a grand, intricate cosmic story, one filled with complexity and wonder far beyond our usual perspective. These theories do more than reshape how we view the cosmos. They prompt us to reflect deeply on ethical and philosophical questions about existence itself. For example, certain cosmological models imply determinism, where the conditions before the Big Bang set in motion an inevitable sequence of events. If everything, including our decisions, is governed by physical laws or predetermined cosmic conditions, what does that mean for moral responsibility? Are individuals truly accountable for their actions if every choice can be traced back to predetermined universal causes? Such questions stir essential debates about justice, responsibility, and free will in a potentially deterministic world. On the flip side, models that emphasize randomness and uncertainty, such as those inspired by quantum mechanics, offer a different framework. They suggest that not all events are fixed or predictable, allowing room for personal agency and ethical decision-making. If our choices can arise from fundamentally indeterminate conditions, then we may have genuine freedom to shape our destinies. This freedom raises the stakes for ethical behavior, urging us to consider more carefully the consequences of our actions on both ourselves and others. Recognizing that humans might influence the unfolding of events carries a profound ethical responsibility. It calls on us to act thoughtfully and with awareness in a universe full of countless possibilities. The implications stretch even further when we consider multiverse theories. If multiple universes exist, each potentially hosting different forms of life, how should that affect our moral perspective? Does the presence of other intelligences in these alternate realities require us to extend ethical concern beyond our own universe? While direct interaction with these other beings may be impossible, the very notion challenges us to move beyond human-centered ethics and adopt a broader, more inclusive sense of duty toward any sentient life that could exist in vastly different conditions. In sum, the exploration of eternal universes, cosmic cycles, and multiverse theories does more than expand our scientific horizons. It enriches our philosophical and ethical understanding. It invites us to reconsider our place in a vast, interconnected cosmos and to embrace a deeper, more nuanced appreciation of existence, responsibility, and the mysterious beauty of the universe we call home. Lastly, the exploration of universe models opens a profound conversation about the ethical dimensions of scientific inquiry and technological progress. As our grasp of the cosmos deepens, the moral questions surrounding the use and application of this knowledge become critically important. Should new technologies inspired by these cosmic theories be developed, it is essential that they are handled with care and responsibility, keeping in mind the possible consequences not only for our universe but potentially beyond it. The pursuit of cosmic knowledge cannot stand apart from a strong commitment to ethical principles that place the well-being of our planet, the future of humanity, and even the potential lives elsewhere in the universe above all else. These ethical considerations invite us to rethink how our expanding understanding of the cosmos shapes not only our worldview, but also the moral frameworks guiding our decisions amid the complex and vast universe we inhabit. Delving into pre-Big Bang theories has a striking influence on how we perceive consciousness and its place within the cosmic landscape. These theories push us to reconsider what consciousness really is, inviting us to explore it beyond the traditional idea that it is a unique feature of human beings or life existing in a single universe. If models like the multiverse are accurate, suggesting an infinite number of universes with varying physical laws and conditions, then it becomes plausible that forms of consciousness could arise in ways far different from what we know. This notion expands the conversation about consciousness, opening doors to possibilities that challenge our current understanding and hint at manifestations of awareness beyond our comprehension. Furthermore, if pre-Big Bang ideas propose that our universe is just one cycle in an eternal or repeating cosmic process, questions about the continuity and transformation of consciousness come to the forefront. Cyclic universe models suggest that consciousness might emerge anew with every cosmic cycle, evolving, fading, and reappearing in new forms across time. This perspective implies that consciousness is not just a fleeting phenomenon, but a part of the universe's larger rhythm, subject to the same forces of growth, decay, and renewal that shape all cosmic structures. It encourages us to think of consciousness as interconnected and ongoing, rather than isolated and transient. Adding another layer, the role of quantum mechanics in pre-Big Bang theories introduces the radical idea that consciousness might actively participate in the very fabric of reality. Some interpretations of quantum physics propose that the act of observation can influence the state of particles at the smallest scales. If consciousness affects the behavior of matter at this fundamental level, then awareness may not simply be a biological byproduct, but something deeply woven into the universe's essence. This insight invites us to explore consciousness as a fundamental component of reality itself, elevating it from a passive experience to an active force in the cosmic story. Ultimately, pre-Big Bang theories compel us to view consciousness as dynamic and intrinsically linked to the universe. Through this broadened perspective, consciousness emerges as a vital thread in the vast cosmic narrative, provoking questions about its purpose, evolution, and potential across different universes and experiences. Such reflections deepen our understanding of mind and existence, suggesting a profound interconnectedness and an ongoing cosmic dialogue. Turning to the long-term fate of the universe, pre-Big Bang theories present a range of fascinating and intricate possibilities that reshape how we imagine the destiny of cosmic structures and the fabric of existence itself. Different models propose various futures for the universe, each with unique implications. Cyclic models, for example, describe an endless loop of cosmic expansion followed by contraction, where each cycle ends with a rebound that sparks a new cosmic beginning. This vision portrays the universe not as a place with a definitive end, but as one of perpetual renewal and transformation. In contrast, models that propose an eternal universe raise questions about what infinite timelines mean for cosmic evolution. If the universe has no beginning or end, it may undergo countless phases of transformation over unimaginable spans of time. This scenario invites us to consider how cosmic structures might emerge, decay, and evolve in an ever-changing landscape, continually reshaping the universe's appearance and nature. The concept of entropy plays a critical role in these discussions, especially when we consider an eternal universe. While energy spreads and structures break down over time, new formations may arise from the same fundamental components, suggesting a universe that is endlessly evolving. On the other hand, thermodynamics also introduces the possibility of a heat death scenario, where energy becomes uniformly distributed and no thermodynamic activity can occur. In this bleak vision, the universe reaches a state of maximum entropy, resulting in a cold, dark expanse devoid of stars or any form of life or activity. This inevitable drift toward disorder challenges our ideas about vitality and existence on cosmic timescales and forces us to ponder what it truly means for the universe to sustain life and motion in the face of entropy's relentless advance. Furthermore, the ongoing exploration of cosmological constants reveals the profound uncertainty surrounding the ultimate fate of our universe. Scientists investigate whether the cosmos will continue to expand forever or eventually reverse course and contract. This investigation places immense importance on understanding dark energy and dark matter, mysterious forces that shape the universe's evolution. Their complex interplay could lead to vastly different outcomes. On one path, the universe might end in a big crunch, collapsing in on itself. On another, it could experience a big freeze, where expansion continues endlessly, leading to an increasingly cold and empty cosmos. These possible futures are deeply intertwined with theories about what happened before the Big Bang, sparking profound questions about existence itself, the nature of time, and humanity's place in the vast cosmic narrative. Regardless of how the story unfolds, the field of differential geometry provides the critical mathematical language needed to model the universe's state before the Big Bang. This branch of mathematics focuses on geometric structures and their properties, enabling scientists to express the complex curvature of space and time in precise and elegant terms. Applied to cosmology, differential geometry describes how space-time can warp and bend under the influence of gravity and other forces, creating the foundation for theoretical models that explore the universe's origins. Within the framework of general relativity, which views gravity as the curvature of space-time, differential geometry helps formulate equations that show how matter and energy affect the universe's shape and behavior. These equations allow researchers to investigate extreme conditions, such as the incredibly dense states thought to have existed just before the Big Bang. By studying these models, scientists gain insight into singularities, points in space-time where gravity becomes infinitely strong and our usual understanding of physics no longer applies. Moreover, differential geometry is essential in exploring cutting-edge theories like string theory and loop quantum gravity, which propose additional dimensions or quantum properties of space-time. These exotic models rely on complex geometric structures, and using differential geometry, researchers can analyze how these hidden dimensions might interact or evolve, offering intriguing possibilities for what the universe looked like before the Big Bang. In this way, differential geometry not only deepens our understanding of the universe's birth, but also unites abstract mathematical concepts with physical laws, allowing a comprehensive exploration of the relationships between spacetime, geometry, and the fundamental forces of nature. This synergy between mathematics and physics is vital for advancing our knowledge of the earliest moments of the cosmos and for imagining the states that preceded the familiar universe we observe today. Another powerful mathematical tool, topology, plays a crucial role in describing the properties of space that remain unchanged even when stretched or deformed continuously. In cosmology, and particularly in theories about the universe's pre-Big Bang state, topology helps analyze the fundamental structure and possible shapes of the cosmos. By investigating the topological features of space-time, physicists explore a variety of scenarios regarding the universe's origins and evolution. Topology's strength lies in its ability to classify spaces based on their connectivity and dimensionality. In the context of the early universe, this means considering how different topological structures might give rise to very different types of universes. For example, a universe with a non-trivial topology, such as one shaped like a torus, a donut-like form, could influence how particles move and how spacetime itself is curved and connected. Such configurations could profoundly affect how the universe expands and evolves over time. Understanding these topological possibilities sheds light on the fundamental characteristics of the early cosmos and helps refine models attempting to describe its behavior before and after the Big Bang. Through topology and differential geometry, researchers continue to push the boundaries of our knowledge, opening new windows onto the profound mysteries surrounding the birth and ultimate destiny of the universe. Furthermore, topology opens a fascinating window into the exploration of extraordinary concepts like wormholes and other exotic structures. These hypothetical formations have the potential to create bridges connecting vastly different regions of space-time, or even entirely separate universes. While such ideas remain highly speculative and far from proven, they invite compelling questions when scientists investigate the conditions that might have existed before the birth of our universe. By studying the topological properties of these theoretical structures, researchers can delve into the profound implications for causality, the nature of time's flow, and the quantum phenomena that could shape our understanding not only of the Big Bang, but also of what might have preceded it. Beyond these cosmic bridges, topology plays an essential role in differentiating between the various phases of the universe's evolution. Just as water changes phases from solid ice to liquid and gas, the universe too undergoes phase transitions that fundamentally alter its properties. These topological shifts often accompany changes in symmetry or vacuum states, which in turn influence the fundamental forces and particles that make up the cosmos. By examining these transitions and their connection to the pre-Big Bang environment, scientists can construct intricate models that provide a more detailed and nuanced portrait of the universe's earliest moments, revealing multiple possible pathways that could have led to the cosmos we inhabit today. In essence, topology serves as a vital analytical tool, expanding our capacity to comprehend the enigmatic conditions before the universe's inception and offering insights into the underlying fabric of reality itself. Parallel to topology, quantum field theory stands as a cornerstone in unraveling the mysteries of the universe's origins. This powerful theoretical framework merges quantum mechanics with special relativity, allowing physicists to describe fundamental particles and their interactions under the extreme conditions present shortly after the Big Bang. Quantum field theory is indispensable for probing phenomena occurring at unimaginably high energies and densities, providing a window into the universe's fiery infancy. One of the major contributions of quantum field theory lies in its depiction of fundamental particles as excitations in underlying fields permeating space. At the extreme temperatures of the early universe, all known particles existed in a state of extraordinary energy, with quantum fluctuations playing a critical role in influencing how these particles interacted. By modeling these fluctuations, scientists can trace how the initial conditions necessary for the universe's expansion were established, laying the groundwork for everything that followed. Moreover, quantum field theory introduces key concepts like vacuum energy and spontaneous symmetry breaking, both crucial for understanding the early cosmos. For example, inflationary theory, which proposes a rapid, exponential expansion of space during the universe's infancy, relies heavily on quantum field theory to explain how a scalar field, often called the inflaton field, could drive this tremendous growth. Investigating how vacuum energy, shaped by quantum fluctuations, might have triggered inflation offers deep insights into the mechanisms that fundamentally altered the universe's future structure and evolution. Additionally, quantum field theory enables the exploration of interactions among various fundamental fields during those first fleeting moments of existence. It provides a framework to study the interplay between forces such as electromagnetism, the weak nuclear force, and gravity, which physicists believe may have once been unified at extraordinarily high energies. Understanding these interactions is essential for building unified models that explain the transition from the primordial universe to the diverse cosmic tapestry observed today. In summary, the application of quantum field theory to cosmology offers powerful tools to decode the fundamental processes that shaped the early universe. It illuminates the dynamics of particle interactions in extreme environments, sheds light on inflationary mechanisms, and connects the fundamental forces governing cosmic evolution, thereby enriching our grasp of how the universe emerged from nothingness. To accurately model the transition from the enigmatic pre-Big Bang state to the familiar Big Bang conditions, scientists employ an arsenal of sophisticated mathematical tools and frameworks. These techniques enable the study of complex phenomena that unfold during this critical phase of cosmic history, integrating ideas from diverse areas of mathematics and theoretical physics. One key mathematical framework is differential geometry, which provides the language to describe the curvature of space-time. This is essential for understanding how gravity shapes the behavior of matter and energy throughout the universe's expansion. The famous Einstein field equations forming the backbone of general relativity are expressed through this framework, allowing researchers to analyze how space-time evolves from an incredibly dense singularity into the expanding cosmos we witness today. Another important tool is dynamical systems theory, which examines how systems change over time. This field of mathematics is particularly useful in cosmology for studying the stability or instability of various models. By applying dynamical systems techniques, scientists can explore how tiny fluctuations in the universe's initial conditions might have caused dramatic outcomes, such as phase transitions or the rapid inflationary expansion proposed by leading cosmological theories. This approach helps illuminate the pathways through which the universe may have moved from pre-Big Bang states to the highly energetic conditions marking the Big Bang itself. Together, these advanced mathematical and physical concepts form the foundation of modern cosmological research. They empower physicists and mathematicians to peer beyond the veil of the observable universe, piecing together the extraordinary story of how everything began and continues to evolve. Additionally, advanced mathematical tools derived from quantum field theory are indispensable for unraveling the intricate interactions between fundamental particles that shape the very fabric of our universe. Techniques such as perturbation theory and the path integral formulation serve as essential methods for probing the behavior of quantum fields and their subtle fluctuations during the universe's earliest moments. These approaches allow physicists to simulate quantum processes, including vacuum fluctuations, which played a critical role in creating the conditions necessary for the universe's rapid expansion, known as inflation. Moreover, the field of topology offers profound insights into the types of phase transitions that may have occurred as the universe expanded and cooled. By studying the topological properties of space and fields, scientists can better understand how various forces and quantum fields interacted and transformed, influencing the fundamental structure of the cosmos we observe today. By weaving together these mathematical frameworks, researchers are able to build comprehensive models that capture the complexity of the universe's transition from enigmatic pre-Big Bang states to the dynamic, evolving cosmos born from the Big Bang itself. This integrated approach deepens our understanding of the origins and continuous evolution of the universe. One particularly fascinating area of study is non-commutative geometry, which arises from attempts to describe the structure of spacetime at extraordinarily small scales, where the principles of quantum mechanics and general relativity converge. At these scales, traditional concepts of geometry based on smooth surfaces and points lose their applicability. Instead, non-commutative geometry replaces points with algebraic structures, redefining how space and time are understood. This revolutionary idea has profound implications for our comprehension of the universe's earliest moments immediately following the Big Bang. During these initial phases, the universe was unimaginably dense and hot, with energies so extreme that classical geometry could break down. Non-commutative geometry suggests that spacetime itself may have possessed a fuzzy quality, where the very notion of precise points and distances becomes uncertain, governed instead by quantum fluctuations and uncertainties. This aligns closely with the principles of quantum field theory, offering a new lens through which to view the universe's foundational layers. Incorporating non-commutative geometry allows physicists to explore how fundamental forces behaved under such extreme conditions. It also provides elegant theoretical pathways toward unifying quantum mechanics with gravity, reimagining the fabric of reality at its smallest scales. This geometric perspective has been pivotal in inspiring frameworks like string theory, where non-commutative features are often essential to bridging the gap between gravity and other fundamental forces. Furthermore, non-commutative geometry contributes to models explaining key cosmic phenomena, such as cosmic inflation and the large-scale distribution of galaxies. These models offer fresh insights into the cosmic microwave background radiation and gravitational waves, enabling us to peer back into the universe's formative epochs beyond the reach of classical physics. Complementing these insights, group theory plays a vital role in understanding the symmetries underlying pre-Big Bang physics. This branch of mathematics provides the language to describe how physical systems behave under fundamental transformations, revealing deep constants of nature and guiding the development of theories about the universe's earliest conditions. In scenarios where the classical concepts of time and space become blurred, such as in pre-Big Bang models, group theory helps physicists map the intricate relationships between forces and their corresponding particles. A fundamental principle of group theory is that every symmetry correlates with a conservation law. For example, rotational symmetry implies the conservation of angular momentum, a concept that extends to the interactions governing the fundamental forces of nature. When applied to the early universe, group theory allows scientists to analyze the symmetries of particle interactions and their crucial role in cosmic structure formation and evolution. This is especially significant in models proposing a universe existing prior to the Big Bang, including cyclic or ekpyrotic theories. In these frameworks, group symmetries elucidate the complex behaviors of spacetime and energy as they evolve. These transformations, characterized by group symmetries, may even provide mechanisms driving cosmic evolution without the singularities traditionally associated with the Big Bang. The interactions mediated by these symmetries offer tantalizing clues about possible pathways through which the universe transitioned into the expansive, structured cosmos we inhabit today. In sum, by blending mathematical tools from quantum field theory, topology, non-commutative geometry, and group theory, scientists are piecing together a richer, more detailed picture of the universe's earliest moments and its ongoing evolution. This multidisciplinary approach not only advances our grasp of cosmic origins, but also pushes the boundaries of fundamental physics itself. Additionally, understanding these symmetries plays a crucial role for physicists striving to build models that bridge the gap between quantum mechanics and general relativity. By harnessing the power of group theory, researchers dive deep into the unification of fundamental forces, pushing the boundaries of what we know about the universe. This journey not only sheds light on how these forces might merge, but also opens doors to comprehending conditions that could have existed before the Big Bang itself. At the very core, it offers a glimpse into the underlying structure of the universe in its purest form. Mathematically capturing the idea of infinite density at the Big Bang singularity requires the use of general relativity and the complex equations that describe the cosmos's behavior. When physicists investigate this singularity, they face the stark reality of the limitations within our current scientific models. Under such extreme conditions, the equations of general relativity cease to function reliably. A common approach to model the early universe is through the Friedmann-Lemaitre-Robertson-Walker metric, which depicts a universe that is uniform and the same in all directions, a concept known as homogeneity and isotropy. As scientists rewind time toward the Big Bang, these models reveal that all matter and energy collapse into an infinitely tiny point. This is what we refer to as the singularity, a state where density is considered infinitely large. From a mathematical perspective, calculating this density involves dividing mass by volume, but both values shrink toward zero, causing the equations to fail dramatically. Instead of yielding meaningful finite results, the equations produce infinities. This signals a profound breakdown in our understanding, marking a frontier where the known laws of physics no longer hold, and new theories are needed to describe the fabric of reality. Additionally, physicists delve deep into the intricate world of quantum mechanics to develop theories that extend far beyond the classical boundaries set by general relativity. These pioneering ideas aim to bridge the vast gap between the cosmic scale and the quantum realm, especially when exploring the earliest moments of the universe. One fascinating avenue of research is loop quantum gravity. This theory suggests a revolutionary concept that space-time itself might not be a smooth, continuous fabric, but instead composed of tiny, discrete loops. According to this model, the infamous singularity, an infinitely dense point traditionally thought to exist at the beginning of the Big Bang, does not actually occur. Instead, loop quantum gravity proposes a minimum length scale, preventing the density from ever reaching infinity. This profound insight offers fresh perspectives on the structure of space-time and the nature of density during the universe's birth. While classical mathematics predicts an inevitable singularity due to infinite density, these more advanced frameworks provide a sophisticated way to describe the extreme conditions that existed at the universe's inception. By integrating the principles of both quantum mechanics and general relativity, scientists are making strides toward a unified understanding of the cosmos at its very origin. The quest to reconcile quantum mechanics with general relativity, especially when applied to the universe's earliest moments, remains one of the most formidable challenges in modern theoretical physics. Researchers employ various mathematical frameworks, each offering unique insights into the fundamental forces and particles that shape the early universe. One prominent contender is string theory. Unlike traditional views that consider fundamental particles as mere points, string theory envisions them as tiny, one-dimensional vibrating strings. This elegant idea naturally unifies quantum mechanics with general relativity by embedding all fundamental forces within a higher dimensional space. String theory opens the door to a universe filled with extra dimensions beyond the familiar three of space and one of time. These additional dimensions might explain how gravity connects to electromagnetism and the nuclear forces, potentially resolving issues like singularities by weaving a complex tapestry of interactions at the smallest scales. On the other hand, loop quantum gravity takes a different route. It does not depend on the existence of higher dimensions, but treats space and time as discrete quantized units. In this picture, space-time resembles a finely woven network of loops that eliminate the infinite quantities predicted by classical theories. This approach offers an alternative lens for understanding the early universe's evolution without resorting to singularities, providing a quantum description of gravity itself. Quantum field theory also plays a vital role in the search for a quantum theory of gravity. By extending quantum mechanics to include gravitational effects, physicists aim to create a self-consistent framework that can describe how particles and forces behave during the universe's rapid expansion. Techniques such as effective field theories focus on low energy limits of quantum gravity, offering predictions about cosmic phenomena like inflation, the dramatic and rapid growth spurt of the early universe, and the creation of particles in this expanding cosmos. Through exploring these diverse frameworks, physicists strive to build a comprehensive narrative of the universe's origins. Each approach, whether it's string theory, loop quantum gravity, or quantum field theory, contributes essential pieces to the puzzle, advancing humanity's pursuit of a unified theory that harmoniously blends quantum mechanics with the geometric beauty of general relativity. Moreover, applying ideas from information theory to pre-Big Bang scenarios brings an innovative angle to our understanding of cosmic evolution before expansion began. Information theory provides tools to study how information is stored, transmitted, and transformed within physical systems. This perspective moves beyond viewing the universe purely in terms of matter and energy, instead emphasizing information itself as a fundamental component shaping cosmic events. One key concept from information theory is entropy, which measures disorder or uncertainty within a system. Physicists examine how entropy behaved under the extreme conditions preceding the Big Bang. Some pre-Big Bang models suggest the universe may have started in a state of very high entropy, a condition of maximum disorder or complexity. From this complex informational structure, a more uniform and isotropic universe emerged. Understanding entropy's role allows scientists to track how the universe evolved from a high entropy state to the lower entropy states we observe today as it expands. This transformation is critical in explaining the formation of large-scale cosmic structures like galaxies, stars, and planets. In sum, the ongoing exploration of quantum gravity theories, coupled with insights from information theory, illuminates the profound and mysterious conditions that gave birth to our universe. This multidisciplinary approach continues to push the boundaries of knowledge, bringing us closer to answering some of the most fundamental questions about the cosmos and the very nature of reality itself. Moreover, in theoretical frameworks like loop quantum gravity, information theory emerges as a powerful tool to describe the transformation of quantum states throughout the evolving universe. This approach suggests that the universe's information content is not lost, but conserved, fundamentally intertwined with the very geometry of space-time itself. By viewing the fundamental laws of physics as intricate information processing algorithms, scientists gain a fresh perspective on how quantum fluctuations may have influenced the dramatic shift from a mysterious pre-Big Bang state to the observable universe we see today. This perspective places a spotlight on how quantum states encode crucial information about the universe's underlying structures, providing a novel lens through which to understand cosmic evolution. Expanding this line of thought, applying information theory to broad cosmological models opens the door to profound insights. It encourages researchers to consider that the laws of physics themselves might arise from deeper informational principles. Concepts like the holographic principle illustrate this idea vividly, proposing that all the universe's three-dimensional information could be encoded on a two-dimensional surface. Such a notion reshapes our understanding of gravity and quantum mechanics, suggesting that the fabric of the universe is woven intricately from threads of information. This framework allows physicists to hypothesize about the behavior and evolution of the universe before the Big Bang, hinting at a reality where information is the fundamental building block. Alongside information theory, chaos theory plays a compelling role in unraveling the emergence of our universe. It provides critical insights into how complex systems evolve from seemingly simple or uniform initial conditions. At the core of chaos theory lies the concept that tiny variations in initial states can lead to drastically different outcomes, a phenomenon famously known as the butterfly effect. When applied to cosmology, this principle becomes vital in understanding the universe's infancy. The moments following the Big Bang were marked by extreme temperatures and densities, setting off a chain of highly sensitive processes. As the universe expanded and cooled, minute fluctuations in density acted as seeds for the formation of galaxies, stars, and the vast cosmic web we observe today. Chaos theory not only helps model how such diverse and intricate cosmic structures could emerge from an initial homogeneous state, but also plays a critical role in explaining cosmic inflation, the rapid expansion of space immediately after the Big Bang. During inflation, quantum fluctuations generated slight density variations, essential for shaping the large-scale structure of the cosmos. The chaotic dynamics underlying these fluctuations allow scientists to trace how randomness at the quantum level influenced the distribution of matter across the universe, offering a bridge between disorder and the remarkable order visible in the cosmos. Researchers are also exploring fascinating connections between chaos theory and quantum mechanics, aiming to unlock a deeper understanding of how quantum uncertainties might contribute to chaotic behavior on a cosmic scale. This intersection highlights the extraordinary complexity of the universe's development, where seemingly random interactions give rise to stable, robust structures. Through the lens of chaos theory, the birth and evolution of the universe emerge as a story of unpredictable interactions and complex behaviors, illustrating both the delicate balance and profound laws that govern cosmic evolution. Understanding the physics before the Big Bang holds transformative potential, particularly for the future of energy technologies. By delving into the universe's fundamental nature, its energy, matter, and deep structures, scientists hope to uncover unified theories that reconcile quantum mechanics with general relativity. Such breakthroughs could revolutionize our approach to energy, revealing new principles that govern energy interactions and unlock innovative ways to harness and utilize power more efficiently. One promising avenue involves studying quantum field theories and their implications for energy production. Insights gained from the dynamics of quantum fluctuations and vacuum energy during the early universe might inform cutting-edge methods for energy extraction. For example, a better understanding of these fluctuations could lead to technologies that tap into zero-point energy, the mysterious energy present even in a perfect vacuum. Successfully harnessing zero-point energy would mark a revolutionary leap in power generation, potentially transforming the future of energy as we know it. In this vast cosmic narrative, the interplay between information theory, chaos theory, and quantum mechanics not only deepens our grasp of the universe's origins, but also fuels hopes for technological advancements that could redefine humanity's relationship with energy and the cosmos itself. Exploring the physics of the universe before the Big Bang offers a thrilling frontier that may revolutionize how we understand materials and energy. By studying the extreme conditions that existed in those earliest moments, scientists are uncovering possibilities for entirely new materials and energy systems that could reshape our technological landscape. Imagine materials designed with properties so exceptional they defy current limitations. Superconductors that allow electricity to flow without resistance, or energy storage devices that vastly outperform today's batteries. These advancements, inspired by high-energy physics insights, could lead to lossless energy transmission and breakthrough improvements in battery technology, paving the way for cleaner, more efficient energy use across many industries. Delving deeper into the dynamics before the Big Bang also sparks innovative ways to understand nuclear fusion, a process that powers stars and promises virtually limitless sustainable energy here on Earth. By examining how matter behaved under the radically different conditions of the early universe, researchers hope to discover new pathways to achieve fusion reactions more efficiently. Understanding fundamental interactions at these extraordinary energy scales could guide the design of future fusion reactors, enhancing their performance and bringing us closer to energy independence. Through these groundbreaking avenues, knowledge gained from pre-Big Bang physics may extend far beyond cosmic understanding, profoundly influencing technological progress and practical applications. Humanity's search for clean, sustainable energy stands on the cusp of transformation by harnessing the subtle phenomena of quantum vacuum fluctuations. These fluctuations are brief, spontaneous changes in energy that occur even in seemingly empty space, a consequence of the inherent uncertainty of quantum mechanics. Mastering these fluctuations could unlock revolutionary technologies across multiple fields: energy production, telecommunications, and advanced materials, to name just a few. One of the most tantalizing possibilities lies in tapping into zero-point energy, the baseline energy present in the vacuum of space. If effectively harnessed, zero-point energy could provide an almost inexhaustible power source. Although the technical challenges are enormous, the impact of such a breakthrough would be monumental. Clean, efficient power generation from zero-point energy could eliminate our dependence on fossil fuels and other finite resources, offering a critical tool in the fight against climate change and helping promote global sustainability. Quantum vacuum fluctuations also play a crucial role in the emerging field of quantum computing. These tiny energy variations can influence qubits, the quantum equivalents of classical computer bits, affecting their behavior and stability. By learning to control these fluctuations, researchers may enhance the power and reliability of quantum computers, accelerating progress in solving complex problems from cryptography to optimizing logistics and financial models. This could usher in a new era of computation, where quantum algorithms solve tasks far beyond the reach of today's machines. Beyond computing, the principles behind vacuum fluctuations open doors to creating novel materials with unique electromagnetic properties. By engineering materials that exploit these quantum effects, scientists could develop superconductors and sensors that operate with minimal energy loss or significantly greater sensitivity than current technologies allow. This would have sweeping applications, from improving energy efficiency in electronics to creating cutting-edge telecommunications devices. Speaking of telecommunications, understanding and harnessing quantum vacuum effects could revolutionize data security. Quantum key distribution, which leverages quantum principles, offers nearly unbreakable communication channels that make eavesdropping virtually impossible without detection. By integrating vacuum fluctuations into these protocols, researchers aim to build ultra-secure networks essential for safeguarding information in our increasingly digital world. In essence, the potential technologies emerging from the study and control of quantum vacuum fluctuations stand at the fascinating crossroads of theoretical physics and practical innovation. They promise to transform energy production, computing, materials science, and secure communications in profound ways. Finally, examining the nature of time itself before the Big Bang could have far-reaching effects on computing technologies. Current research into quantum time challenges and expands classical notions of time, revealing new frameworks that might redefine how information is processed. An improved understanding of time's behavior at the quantum level could lead to the development of faster, more efficient quantum computers that surpass today's limits. If scientists can decipher the temporal dynamics of pre-Big Bang conditions, they may unlock novel quantum algorithms that utilize these time-related phenomena. This would enable computations performed in ways classical systems cannot achieve, opening an exciting new chapter in the evolution of computing technology. Additionally, delving deeper into the concept of time as an essential and fundamental aspect of the universe holds the promise of inspiring revolutionary models of computation. Imagine computational systems designed to harness nonlinear or even higher dimensional representations of time, rather than relying solely on the straightforward linear flow we experience in everyday life. In such models, time may behave in ways that allow computations to occur across multiple states simultaneously, opening the door to processing methods that far surpass our current capabilities. This shift could ignite entirely new paradigms for handling data. Processing and storage systems could leverage these complex temporal frameworks to access and manipulate immense volumes of information with drastically reduced delay. By embracing the continuity of time or exploring its potential cyclical nature, networked computing systems might evolve in unprecedented ways. Systems connected across distributed networks could collaborate by drawing on data from numerous nodes over varying time frames, synchronizing their operations more effectively to enhance scalability and resilience. This would significantly bolster frameworks in cloud computing and decentralized networks, ultimately driving improvements in both efficiency and security. Furthermore, as scientists continue to explore the profound connections between time, entropy, and information theory, they could uncover groundbreaking insights into error correction and reliable information transmission. Integrating ideas from cosmology into the core principles of computing might lead to more robust systems capable of withstanding disruptions and maintaining data integrity under a wide range of conditions. An advanced understanding of time, especially what might have existed before the Big Bang, could fuel transformative advances in computing technologies, inspiring new approaches to quantum information processing, temporal computing architectures, and networked systems. These developments could redefine the very nature of computation, both in theory and practical application. Pre-Big Bang theories also carry intriguing implications for space exploration and propulsion. By shedding light on the fundamental nature of space-time and the universe's fabric, these ideas can inspire innovative strategies for traveling beyond our solar system. Understanding the conditions and dynamic processes that may have occurred before the Big Bang could lead to groundbreaking propulsion technologies. For instance, the study of vacuum energy and quantum fluctuations, topics already deeply investigated within cosmology, holds potential keys for manipulating space-time itself. If researchers learn how to harness vacuum energy or control the behavior of space-time based on pre-Big Bang physics, revolutionary propulsion systems could become a reality. One fascinating concept is the Alcubierre warp drive, which theoretically enables faster-than-light travel by contracting space in front of a spacecraft while expanding it behind. With a more profound comprehension of how space behaves under extreme conditions, this speculative idea might edge closer to feasibility. Alongside this, advances in understanding gravity and gravitational waves could lead to technologies that use gravitational effects for propulsion. By mastering gravitational field manipulation, scientists might develop entirely new methods for spacecraft propulsion, making interstellar journeys more attainable than ever before. Moreover, pre-Big Bang theories that propose a cyclical universe offer another layer of insight that could impact long-term space mission planning. If the universe's energy environments or gravitational anomalies follow repeatable patterns, they might provide natural shortcuts or stable pathways through space. Such discoveries could revolutionize navigation and exploration strategies, optimizing routes for missions to distant planets or even far beyond. In summary, the exploration of time as a fundamental cosmic dimension and the mysteries surrounding the moments before the Big Bang could spark a renaissance in both computing and space travel. These ideas challenge current boundaries, potentially unlocking new technologies that reshape how humanity computes, navigates, and ventures into the vast unknown. Finally, breakthroughs in understanding dark energy, the mysterious force driving the accelerated expansion of the universe, could revolutionize technology and space exploration. Scientists are beginning to unravel how dark energy interacts with the cosmic fabric, especially by studying dynamics that may have existed before the Big Bang. If researchers succeed in decoding these pre-Big Bang phenomena, they might develop innovative technologies that can harness or counteract dark energy's effects. Imagine spacecraft equipped with systems designed to stabilize their trajectories despite the universe's relentless expansion. Navigating through this ever-stretching cosmic landscape could become feasible with new methods inspired by pre-Big Bang theories. These insights promise to open entirely new pathways for humanity's journey into the farthest reaches of space, fundamentally transforming our approach to interstellar travel and exploration. Beyond space travel, understanding the very fabric of existence before the universe's birth could profoundly impact material science. By investigating the extreme conditions and energetic states that might have prevailed prior to the Big Bang, scientists are uncovering clues about the fundamental nature of materials under extraordinary pressures and temperatures. These discoveries could lead to the creation of novel materials with remarkable properties capable of performing in environments far harsher than anything we experience today. For example, materials engineered to endure temperatures and pressures similar to those inside stars or produced during high-energy collisions could revolutionize fields like aerospace engineering, energy storage, and electronics. Laboratory experiments that replicate such extreme states could reveal substances with unparalleled durability, resilience, and thermal resistance, qualities that would redefine the limits of material performance. Insights from quantum fluctuations and vacuum energy, the subtle energy present even in empty space, could further reshape material science. By understanding how vacuum states interact with matter, researchers may unlock new ways to harness quantum effects, leading to the development of materials with extraordinary electrical conductivity or magnetic properties. This could pave the way for superconductors that operate with almost zero resistance, enabling highly efficient electrical transmission, ultra-fast computing, and advanced medical imaging technologies. The implications don't stop there. Pre-universe theories also provide fertile ground for designing smart, adaptive materials, those that can dynamically change their properties in response to environmental stimuli. Such materials could revolutionize soft robotics, allowing machines to flex, stiffen, or morph based on need, or produce responsive coatings that protect surfaces from wear, corrosion, or other damage. Moreover, the exploration of space-time dynamics and the interaction of fundamental forces may inspire the creation of metamaterials, engineered structures that exhibit unusual properties not found in nature. These materials could manipulate light, sound, or electromagnetic waves in entirely new ways, offering groundbreaking applications in optics and communication technologies. Overall, deepening our understanding of pre-universe existence stands to ignite a cascade of innovations in material science. This progress will drive the development of superior materials with enhanced capabilities, ultimately transforming multiple industries and amplify technology's positive impact on society. In the realm of medicine, this fundamental physics knowledge carries immense promise. Bridging physics and medical science, researchers are poised to develop advanced diagnostic tools, treatment methods, and healthcare technologies. For instance, quantum mechanics and particle physics have already paved the way for imaging techniques such as positron emission tomography, PET, and magnetic resonance imaging, MRI. As research continues, a more profound grasp of particle interactions at the subatomic level could lead to even more precise imaging technologies. Such advancements would allow doctors to detect diseases like cancer earlier and monitor treatments more accurately, dramatically improving patient outcomes. The fusion of fundamental physics with medical innovation stands to reshape healthcare, offering hope for earlier diagnosis, better therapies, and overall enhanced quality of life. Moreover, gaining deeper insights into the fundamental forces and interactions that govern the universe holds tremendous potential for transforming medical science, especially in the realm of radiation therapy. By exploring how high-energy particles interact with biological tissues, researchers are pioneering innovative techniques that precisely target cancer cells. These advanced methods aim to destroy malignant cells more effectively while sparing the surrounding healthy tissues, which traditionally suffer collateral damage during treatment. This refined approach to radiation therapy could revolutionize patient care, delivering improved outcomes with significantly fewer side effects, offering new hope to countless individuals battling cancer. Quantum mechanics, the cornerstone of modern physics, also plays a pivotal role in developing cutting-edge drug delivery systems. By harnessing the principles of quantum information science and material science, Scientists are engineering drug delivery mechanisms that dynamically respond to specific physiological cues. Imagine nanoparticles designed to release medication only when they detect certain biomarkers linked to disease, maximizing therapeutic effects while minimizing harmful side effects throughout the body. Such precision not only enhances treatment efficacy, but also paves the way for personalized medicine, where therapies are tailored to an individual's unique biological environment. Furthermore, fundamental physics contributes to biophysics, enriching our understanding of complex biological systems. Applying physics-based modeling to biological processes allows scientists to probe deeply into phenomena like protein folding and cellular interactions, which are critical to health and disease. The insights gained from these studies could lead to breakthroughs in targeted therapies and personalized treatment strategies, aligning medical interventions with the distinct biological makeup of each patient. Advancements in physics also drive innovation in biomedical devices. Improved knowledge of materials, quantum phenomena, and thermodynamics is fostering the development of more sophisticated sensors for monitoring vital signs, advanced prosthetics that more closely mimic natural movement, and innovative diagnostic tools providing real-time feedback to healthcare providers. Together, these technologies promise to enhance patient monitoring, improve the quality of life for individuals with disabilities, and accelerate the diagnostic process, ultimately transforming the healthcare landscape. The convergence of fundamental physics and medical applications opens a vast realm of possibilities. This fusion promises to revolutionize healthcare, enhance diagnostic accuracy, refine treatment methodologies, and enable the creation of next-generation biomedical technologies that were once thought impossible. Beyond medical science, pre-Big Bang theories offer intriguing possibilities for the future of quantum computing. By investigating the conditions that might have existed before the Big Bang, researchers uncover novel concepts that challenge and expand our understanding of quantum mechanics and information processing. These early universe models often describe extreme high-energy physics environments where quantum fluctuations play a crucial role. Studying how quantum states behaved under such conditions can reveal new insights that may improve the fundamental building blocks of quantum computers, known as qubits. Informed by these theories, future qubit designs could achieve longer coherence times and lower error rates, which are critical challenges in the development of reliable quantum computers. This could lead to more efficient quantum operations and more powerful computational capabilities. Moreover, pre-Big Bang concepts deepen our understanding of quantum non-locality and entanglement, two phenomena central to quantum computing. Exploring how quantum information might have been processed or transferred in the early universe inspires new protocols for quantum communication, enhancing secure information transfer and advancing quantum cryptography. Additionally, the search for a unified framework connecting gravity and quantum mechanics, as suggested by some pre-Big Bang theories, could inform the development of quantum gravity models. Success in this area would bridge the gap between Einstein's general relativity and quantum principles, opening new pathways for constructing quantum computers capable of operating under principles not yet considered. These innovative architectures might surpass current designs, ushering in a new era of quantum technology with unprecedented power and versatility. In essence, the interplay between fundamental physics and emerging technologies holds the promise of reshaping both medicine and computing in profound ways, unlocking advancements that could redefine human health and technological progress for generations to come. Moreover, the investigation into the concepts of time and space during the conditions before the Big Bang opens the door to groundbreaking possibilities in quantum computing. Researchers are exploring how multidimensional time or alternative temporal frameworks might revolutionize the way quantum computers operate. These innovative ideas could completely transform quantum algorithms and drastically increase computational speeds, enabling processing of information in ways classical systems simply cannot match. The dynamic relationship between pre-Big Bang theories and quantum computing holds the potential to drive transformative breakthroughs. By deepening our understanding of quantum states and refining computational techniques, scientists could develop entirely new paradigms that harness the principles of quantum mechanics far more effectively. This exploration might eventually make quantum computing technologies more practical and accessible across a variety of applications, from scientific research to everyday technology. Delving into fundamental physics, especially insights drawn from pre-Big Bang scenarios combined with quantum mechanics, also carries profound implications for the future of communication technologies. These advancements promise to reshape how information is transmitted, secured, and processed over vast distances, leading to significant improvements in both efficiency and security. One of the most exciting frontiers lies within quantum communication. By leveraging core principles such as quantum entanglement and superposition, researchers are developing quantum key distribution systems. Unlike classical encryption methods vulnerable to hacking, these quantum protocols rely on the laws of quantum mechanics to detect any attempt at interception, offering unprecedented security. This capability could revolutionize sensitive sectors like banking, national security, and data privacy by enabling ultra-secure communication networks. Beyond security, insights from quantum mechanics are paving the way toward quantum networks, interconnected systems of quantum bits or qubits functioning similarly to classical networks. These quantum networks could enable information transmission at speeds exponentially faster than current technologies allow, ushering in a new era of telecommunications. Imagine real-time communication across previously insurmountable distances, fostering global interconnectivity on a scale never before possible. Furthermore, the exploration of time itself from pre-Big Bang perspectives may inspire entirely new concepts in temporal communication. If scientists find ways to manipulate the dimensions of time, it might become possible to send information backward, challenging our traditional understanding of cause and effect. Although still speculative, this idea highlights how fundamental physics could provoke radical shifts in how we communicate. In addition to communication methods, fundamental physics could drive the development of advanced materials used in communication technologies. Innovations like quantum dots, photonic crystals, and other cutting-edge materials, designed with principles from fundamental physics, could greatly enhance the efficiency and durability of optical fibers and telecommunications equipment. This would result in systems with clearer signals and longer lifespans, improving connectivity worldwide. The impact of these advancements extends beyond mere technology. It touches the core of how humans interact and connect. As communication technologies evolve under the influence of quantum mechanics and fundamental physics, they may redefine personal interactions, enable smarter networking systems, and enhance our collective ability to share information in an increasingly interconnected world. Overall, the future promises secure, instantaneous, and revolutionary ways to connect. Moreover, the insights emerging from fundamental physics, particularly those derived from pre-Big Bang theories and quantum mechanics, could have a profound influence on environmental and climate sciences. By deepening our understanding of the universe's fundamental principles, these theories may inspire innovative approaches to tackling climate change, optimizing resource management, and developing sustainable technologies. One promising area of impact is energy generation and storage. By applying concepts from fundamental physics, researchers might unlock new energy technologies that harness unconventional sources, such as vacuum energy generated by quantum fluctuations. Successfully tapping into these sources could lead to clean and sustainable power generation, significantly reducing reliance on fossil fuels and lowering greenhouse gas emissions. This breakthrough would play a critical role in mitigating climate change and accelerating the transition toward a sustainable energy future. In summary, the fusion of pre-Big Bang theories and quantum mechanics is not just a theoretical pursuit. It holds the promise of reshaping multiple facets of technology, from quantum computing and communication to energy and environmental solutions, potentially transforming our world in ways we are only beginning to imagine. Furthermore, the deep knowledge gained from studying the fundamental interactions between particles and forces under extreme conditions holds incredible promise for advancing carbon capture and storage technologies. Understanding how gases behave at the quantum level could unlock new, highly efficient methods for capturing carbon dioxide directly from the atmosphere or industrial emissions. These breakthroughs could significantly enhance global efforts to reduce atmospheric carbon levels, playing a crucial role in combating climate change. In addition, exploring the physical principles that govern complex systems has the potential to transform our understanding of ecological interactions and climate dynamics. By applying physics-based models to natural environments, scientists can create more accurate climate simulations. These models allow for detailed predictions of how various factors like temperature, humidity, and atmospheric pressure interact within the Earth's climate system. With improved climate forecasts, policymakers and researchers gain invaluable tools to design effective strategies for both adapting to and mitigating climate change impacts. Moreover, advancements in material science, fueled by insights from fundamental physics, promise to revolutionize environmental technologies. Researchers are developing new materials with superior properties that can dramatically improve applications such as solar energy. For example, cutting-edge materials could increase the efficiency of solar panels, boosting energy conversion rates and making solar power a more practical and sustainable primary energy source. Additionally, these novel materials could reduce waste in manufacturing by enabling more sustainable production processes, supporting a circular economy that lessens the environmental footprint of industry. Lastly, lessons learned from fundamental physics about the deep interconnectedness of systems can guide more holistic approaches in environmental and climate science. Recognizing the intricate links between ecological, atmospheric, and human systems enables the development of integrated strategies that tackle multiple aspects of environmental challenges simultaneously. This holistic perspective ensures that efforts to address climate change consider social, economic, and ecological dimensions, promoting sustainable solutions that balance the needs of both people and the planet. By integrating theories from fundamental physics into environmental and climate sciences, we open the door to groundbreaking innovations and strategies that greatly enhance our ability to confront and adapt to the urgent challenges posed by climate change. This fusion of knowledge supports sustainable development and strengthens resilience in the face of environmental threats. At the same time, technologies inspired by physics theories from before the Big Bang offer transformative potential, but also bring significant risks and ethical dilemmas. As researchers push the boundaries of these complex theories to develop new applications, it becomes crucial to carefully consider the broader implications. One major concern is the potential misuse of advanced technologies, especially in areas such as quantum communication and energy generation. For instance, if quantum encryption methods fall into the wrong hands, they could enable levels of secure communication so advanced that malicious actors might exploit them for cyber warfare, espionage, or other illegal activities. Awareness of these risks is essential as society navigates the promises and challenges of these powerful emerging technologies. Additionally, harnessing vacuum energy or similar concepts without careful consideration could lead to unexpected dangers that might destabilize established energy systems. This disruption could have far-reaching consequences for our power infrastructure, making it unpredictable and potentially vulnerable. One significant ethical concern centers around equity and access. As technologies inspired by fundamental physics continue to evolve, there is a real risk that the benefits may not be shared fairly among different populations. For example, innovations in energy generation often require substantial investment to develop and implement. This financial barrier could widen the gap between wealthy nations and developing countries, creating disparities in who gains access to these breakthroughs. Ensuring that technological progress serves social good rather than deepening existing inequalities is a vital ethical priority. Moreover, the potential environmental impact of these emerging technologies demands thorough scrutiny. While many innovations aim to tackle environmental challenges, their unintended consequences can sometimes be serious. Energy extraction methods based on quantum mechanics, for instance, might affect ecosystems in ways we do not yet fully understand or could contribute to the depletion of natural resources. Conducting comprehensive assessments of ecological risks is essential to avoid harm and ensure that technological advancement aligns with principles of environmental sustainability. Furthermore, the rapid pace of development in technologies inspired by pre-Big Bang physics raises important questions about regulatory frameworks and governance. Current policies might be insufficient to address the ethical and safety challenges posed by advanced quantum technologies or novel energy systems. Therefore, establishing robust regulations that emphasize safety, ethical use, and accountability is critical to managing the risks associated with these new technologies. At a deeper level, research into fundamental physics touches upon profound concepts related to the nature of reality, consciousness, and the origins of the universe. As scientists push the boundaries of knowledge, philosophical and ethical questions about existence itself may emerge. These questions have the potential to shift human perspectives and beliefs significantly. Engaging in interdisciplinary conversations that connect science, ethics, and philosophy becomes essential for thoughtfully and respectfully navigating these complex debates. In conclusion, while exploring technologies inspired by pre-Big Bang physics offers extraordinary potential, it is crucial to address the associated risks and ethical issues. Doing so ensures that these advancements contribute to human well-being, promote fairness, and protect the environment. Drawing from biology, particularly the idea of emergence, provides a captivating lens through which to understand the universe's origin. Emergence refers to the process by which complex systems and patterns arise from interactions among simpler components. This principle sheds light on how the universe evolved from an extremely dense, uniform state into the vast and intricate cosmos we observe today. In cosmology, the early universe is often described as a high-energy, highly uniform state. As it expanded and cooled, tiny fluctuations occurred at the quantum level, causing slight variations in density. These small differences can be compared to components within biological systems, where individual interactions lead to the formation of larger, coherent patterns. The concept of emergence helps explain how such minute quantum fluctuations eventually gave rise to galaxies, stars, and planetary systems, illustrating a journey from simplicity to complexity over time. Understanding emergence in biology also informs the study of self-organization within the universe. Just as biological systems, such as flocks of birds or cellular structures, can develop intricate patterns without central control, the universe exhibits similar self-organizing behavior on a cosmic scale. Gravitational forces among matter lead to the formation of vast structures like galaxies and galaxy clusters from primordial chaos. This process highlights how fundamental forces and simple interactions can produce highly sophisticated systems in both biology and cosmology. Additionally, biological concepts of emergence provoke fascinating questions about life's nature and its place in the universe. If the universe is viewed as a complex system, then the emergence of life can be seen as one of its many natural outcomes. Studying complex adaptive systems in biology, including ecosystems and evolutionary processes, provides insights into how life's emergence reflects deeper physical laws and cosmic dynamics. Moreover, when we bring together perspectives from biology, physics, and philosophy, we open doors to a far deeper understanding of both the origin of the universe and the rise of consciousness. By investigating how behaviors, both individual and collective, emerge across different contexts, scientists can unlock new insights into the profound connections between conscious beings and the cosmos. This interdisciplinary approach suggests that the universe itself might harbor forms of information processing or consciousness existing at various scales beyond our usual perception. Take the concept of emergence in biology. It shines a light on the complex interactions of fundamental processes that give birth to intricate structures and living systems. This idea transforms how we view the universe's beginning, painting a picture not just of simple particles, but of an evolving, interconnected web where life and cosmos are intertwined. Such a perspective invites exploration across scientific disciplines, encouraging a holistic view that seeks to understand existence in all its complexity. Neuroscience adds another vital layer to this exploration by helping us grasp how humans comprehend abstract ideas, such as nothingness and the early universe. The brain's mechanisms for processing complex concepts, constructing understanding, and interpreting experiences play a crucial role when we try to wrap our minds around these profound philosophical and scientific questions. One fascinating area of research focuses on how the brain handles the idea of nothingness, a concept that challenges our everyday understanding of existence. Scientific studies reveal that the human brain is naturally inclined to resist the notion of absence. Instead, it tends to fill in gaps with rich, context-based interpretations drawn from sensory experiences. This tendency likely stems from our evolutionary history, where making sense of the physical world and anticipating outcomes was vital for survival. Because our brains rely heavily on context, grappling with the concept of nothingness often pushes us toward abstract thinking, which can bring about feelings of uncertainty or discomfort. Furthermore, understanding how our brain manages abstract thought sheds light on how people conceptualize the early universe, vast in both time and space, and filled with conditions far removed from everyday human experience. Neuroscience has identified specific brain regions, like the prefrontal cortex and parietal lobes, that become active when we try to create mental models of cosmic phenomena or imagine timescales far beyond what we experience daily. These areas help us visualize and reason about phenomena that exist only in theory or deep abstraction. The brain's remarkable ability to generate and manipulate abstract representations fuels our capacity to form hypotheses about the universe's origins, even when those ideas remain beyond direct observation. This cognitive flexibility, sometimes called cognitive elasticity, is essential in adapting our understanding of complex topics like the early universe. Neuroplasticity, the brain's capacity to reorganize and grow in response to new learning, allows individuals to update their mental frameworks as scientific knowledge in physics and cosmology advances. In this way, we constantly reshape how we think about the cosmos and its initial conditions, embracing ever more sophisticated models and theories. Philosophical reflections within neuroscience further enrich this dialogue by connecting ideas about nothingness and cosmic origins to deeper existential questions involving consciousness, perception, and reality itself. These explorations may lead to profound insights about the human condition, illuminating how we relate to existence and non-existence. In doing so, neuroscience helps bridge the gap between cognitive science and philosophy, offering a framework to investigate some of the most mysterious aspects of the cosmos. Additionally, psychological concepts related to perception play a crucial role in shaping our theories about what might have existed before the Big Bang. Our perception is fundamentally shaped by the way our brain interprets sensory information, grounding our experience of reality in a three-dimensional world. When scientists try to theorize about the pre-Big Bang state, potentially involving dimensions or conditions beyond our sensory reach, they must rely on abstract reasoning and analogies. This reliance influences how theories about the early universe are formulated. Often, these ideas are framed in terms that resonate with our perceptual experiences, which can make them more relatable, but may sometimes steer interpretations away from purely scientific precision. This delicate balance between human cognition and scientific rigor underlines the complexity of understanding phenomena that lie far beyond direct observation, pushing us to constantly question and refine our view of the universe's beginnings. In summary, the convergence of biology, physics, philosophy, neuroscience, and psychology creates a rich tapestry of knowledge that deepens our understanding of the universe's origins and consciousness. It highlights how human cognition shapes and is shaped by our quest to unravel the deepest mysteries of existence, encouraging ongoing dialogue across disciplines that broadens our grasp of reality itself. And yet, how we think may shape what we see. In the vast halls of theoretical physics and cosmology, it's not only the equations and telescopes that guide discovery, but also the subtleties of the human mind. Cognitive biases, often hidden beneath layers of intellect and training, can profoundly influence how scientists grapple with the most abstract and elusive questions in the universe. Take, for instance, the mystery of what existed, if anything, before the Big Bang. It's a question that lies far beyond the reach of conventional measurement, demanding an interplay of logic, imagination, and speculation. Yet even here, human psychology enters the equation. Our brains are naturally wired for teleological thinking, the inclination to see purpose or intent behind phenomena. This tendency, a legacy of our evolutionary need to make sense of our environment, can subtly color how researchers interpret the origins of the cosmos. We may unconsciously impose narratives of direction or intention onto the birth of the universe, stories that reflect not physical law but psychological comfort. Such biases can shape more than just individual interpretations. They influence which theories feel intuitively right, affecting how research communities build consensus. A model that aligns with our cognitive expectations, one that tells a tidy, deterministic story, may gain traction not solely on its merits, but because it fits more comfortably within the mental frameworks we've inherited. The danger here lies in the potential marginalization of alternative models, equally valid, yet cognitively foreign. At the heart of this challenge is our relationship with uncertainty. The human mind often recoils from ambiguity, favoring clarity and closure. In the realm of pre-Big Bang cosmology, where uncertainty isn't just common but fundamental, this discomfort can lead scientists toward theories that offer the illusion of control. There's a psychological pull toward models that bring order to the undefined, toward neat equations over nebulous realities. Yet, progress in cosmology demands a delicate balance, embracing the complexity of the unknown while resisting the urge to oversimplify it. Furthermore, science is not practiced in a vacuum. It is a deeply collaborative process, one shaped by social dynamics as much as solitary insight. Theories are shared, debated, revised, and either accepted or set aside. In this exchange, psychological forces again play a role. The need for consensus, the power of group validation, and the influence of dominant voices can all steer the direction of inquiry. The result is a landscape where some theories rise to prominence not strictly due to empirical superiority, but because they resonate within the shared cognitive and cultural frameworks of the scientific community. This interplay of psychology and science is not confined to cosmology. In fact, striking parallels emerge between cosmic evolution and biological evolution, offering further insight into the mechanisms that govern complexity itself. Both domains tell a story of transformation, from simplicity to intricate structure, not in leaps, but through gradual change. In the grand chronicle of the cosmos, the universe began with a singular event, the Big Bang. From that point forward, it expanded, cooled, and passed through successive stages of development. Elementary particles gave way to atoms, then stars, galaxies, and eventually entire planetary systems. This unfolding did not happen all at once, but through incremental steps, each building on the last. Biological evolution follows a remarkably similar trajectory. Life on Earth emerged from simple chemical beginnings, evolving over eons through genetic mutation and natural selection. Small, random changes accumulated generation by generation, gradually shaping the immense diversity of life we see today. Both cosmic and biological evolution demonstrate how complexity arises not by design, but through the accumulation of changes guided by underlying rules. Crucially, both stories also embrace randomness and chaos as essential ingredients. In cosmology, quantum fluctuations in the early universe played a pivotal role in the distribution of matter, influencing everything from the formation of galaxies to the structure of the cosmic web. In biology, genetic mutations occur unpredictably, introducing variation into populations. Some of these variations offer adaptive advantages, which are then preserved by natural selection. In both domains, randomness injects diversity, while law-like forces provide structure, a dynamic dance between chance and necessity. Then there is the concept of self-organization, where order arises not from an external designer, but from the interactions of simpler units. Gravity pulls matter together, forming stars, galaxies, and clusters in a cosmic ballet of mutual attraction. In living systems, single cells coordinate and specialize, forming tissues, organs, and entire organisms through complex biochemical signaling. These are systems where the whole becomes more than the sum of its parts, where new properties emerge that could not have been predicted from the individual components alone. In this light, the universe and life itself share a common thread. They are both self-assembling systems. driven by interplay between randomness and rule, between chaos and order. And yet, our understanding of these processes is always filtered through the lens of human cognition. Ultimately, the way we perceive the universe, its origin, its structure, its fate, is deeply entangled with the architecture of our own minds. Every theory, every model, every cosmic metaphor reflects not just the universe as it is, but the universe as we are able to imagine it. Recognizing this does not diminish science. Rather, it makes it more honest. It reminds us that the search for truth in cosmology is not just a journey outward into space and time, but also inward into the workings of our own perception. And yet, both realms, cosmic and biological, reveal a profound truth. Nothing exists in isolation. Across the vastness of the cosmos and within the intricate webs of life on Earth, the principle of interdependence reigns supreme. Galaxies drift through space, not as solitary islands, but as members of a gravitational ballet. Their interactions, collisions, mergers, tidal distortions reshape their destinies, triggering star formation and altering galactic architecture. These gravitational relationships are not mere background noise. They are the sculptors of cosmic evolution. Within galaxies, stars burn with nuclear fire, forging elements in their cores, hydrogen into helium, helium into carbon, and onward up the periodic table. These elements are scattered into space through supernovae, enriching the interstellar medium with the raw materials for planets, oceans, and eventually life. Thus, the birth of a star plants the seeds for biology. Zoom in billions of light years from the swirling galaxies to the delicate equilibrium of a rainforest, and the same principle holds: interconnection. Organisms don't evolve in a vacuum. They coexist, compete, and collaborate. A predator shapes its prey's behavior, a pollinator and a flower co-evolve in mutual benefit. The trajectory of life, like that of galaxies, is a story told in relationships. Every species is both an actor and a consequence within its ecological stage. This symmetry between the cosmic and the biological is more than poetic. It is a mirror that reflects shared principles: gradual change through incremental steps, the influence of random events, the emergence of complexity from simple rules, and the self-organizing nature of systems driven by interaction. Together, these themes speak to a unified narrative. Evolution, whether among stars or cells, is a process guided by connection. By drawing parallels between stellar nurseries and coral reefs, between galactic mergers and ecological invasions, we do more than entertain metaphor, we open the door to interdisciplinary understanding. Cosmology and biology, once viewed as distant intellectual territories, now appear as neighboring provinces within a grander territory of knowledge. Together, they invite us to explore deeper truths about existence, emergence, and the scaffolding of reality itself. But even as we uncover these parallels, our ability to comprehend them is shaped, perhaps even constrained, by the very language we use. Language is not merely a tool for communication. It is the lens through which we perceive reality, the architecture upon which we build concepts, especially when wrestling with the most abstract ideas known to science and philosophy. Take the notion of nothingness. It might seem simple, a lack of something, but delve deeper, and the cracks in comprehension begin to show. In many languages, nothing is defined by negation. It is not this, it is not that. Such binary opposition, something versus nothing, anchors our thought to dualistic frameworks. The human mind, shaped by language and experience, finds it nearly impossible to conceptualize a true void, a state of absolute non-being. Instead, we cling to metaphors, analogies, and half-truths that domesticate the idea into something we can manage, even if it's not entirely accurate. This linguistic limitation becomes especially problematic when we venture into theoretical physics and early universe cosmology. How do we describe the state before the Big Bang or the nature of quantum vacuums that teem with potential yet contain no matter? Our vocabulary often lacks the nuance necessary to capture these ideas in their raw form. Scientists invent terms: singularities, zero-point energy, quantum foam, but even these are bounded by the constraints of language shaped in a macroscopic material world. Moreover, the evolution of scientific thought may depend on how effectively we name and describe the ineffable. New discoveries often hinge on the invention of new words, new mathematical frameworks, or new ways of thinking. Without them, our progress stalls, limited not by imagination, but by expression. Cultural context deepens the complexity. Different languages and traditions harbor varied ways of interpreting nothingness. In some Eastern philosophies, for instance, the void is not absence but potential, pregnant with possibility rather than barren. In contrast, Western traditions have often framed nothingness in terms of lack or death. These divergent conceptions shape not only spiritual and philosophical beliefs, but can influence the kinds of scientific questions a culture finds worth asking. Language, then, is both a bridge and a boundary. It connects minds across time and space, enabling the collaborative pursuit of knowledge. But it also fences in our understanding, limiting what we can see and say. To better explore the mysteries of the universe and life itself, we must become aware of the linguistic frameworks we rely on and be willing to transcend them. In this light, the study of cosmology, biology, and even linguistics becomes a unified quest to understand not just the content of the universe, but the means by which we perceive and interpret it. The story of existence is not only written in the stars or the strands of DNA, it is told through the words we use to describe them. And perhaps by expanding our language, we expand our universe. And yet, cognitive linguistics reminds us that language is not merely a vehicle for conveying thought, it is a powerful force that shapes the very contours of our thinking. The way we craft our sentences, the metaphors we lean on, and the spatial relationships we embed in our expressions all play a role in how we perceive and interpret the world around us. Language is not neutral. It frames, filters, and even forges the ideas we consider possible. Consider, for instance, how metaphor-rich languages open the door to imaginative, layered conceptions of reality. When a language habitually speaks of time as space or emotion as temperature, it fosters a way of thinking that blends the abstract with the tangible. In the realm of cosmology, where much of what we discuss lies beyond sensory experience, this flexibility can be transformative. A linguistic framework that embraces narrative complexity and abstract fluidity may encourage individuals to entertain unconventional theories about the origins of the universe. On the other hand, languages with rigid grammatical rules or limited conceptual metaphors may constrain imagination, limiting how we articulate the nature of existence itself. This linguistic scaffolding becomes especially significant when grappling with one of the most elusive notions in physics and philosophy: nothingness. The early universe, an arena dominated by absence before the birth of matter, time, and space, challenges the expressive capacity of any language. Our words are drawn from a world of experience, yet we are tasked with describing a state in which experience, as we understand it, did not yet exist. The richness or sparseness of our language profoundly influences not just how we describe that primordial void, but how we theorize about it. In this way, language becomes both a lens and a limitation. Recognizing the reciprocal relationship between language and thought invites us to refine how we communicate complex ideas. If we aim to reach deeper insights about the cosmos, then developing more expressive, nuanced linguistic tools is not merely helpful, it is essential. Amid this linguistic exploration, complexity theory emerges as a scientific framework that mirrors the dynamism of thought itself. Rather than reducing the universe to a catalog of isolated components, complexity theory views it as a web of interrelated elements, constantly shaping and reshaping one another through interaction. From the first infinitesimal moments after the Big Bang, simplicity gave way to structure, and randomness gave rise to order. A cornerstone of this theory is the idea of emergence, the phenomenon by which simple rules or interactions among basic units lead to the spontaneous formation of new, more complex behaviors or properties. In the early universe, this played out as fundamental particles like quarks and electrons followed the basic laws of physics, gradually combining to form atoms. Those atoms in turn formed stars, galaxies, and eventually the intricate cosmic architecture we observe today. It is not enough to look at quarks and electrons in isolation. Only by understanding their interactions can we appreciate how the universe has unfolded. This view challenges the reductionist model that has long dominated scientific thinking. Rather than dissecting the cosmos down to its smallest parts in search of answers, complexity theory calls on us to look at the patterns, feedback loops, and systemic dynamics that arise from interactions. For example, the way galaxies cluster, or the manner in which dark matter shapes the large-scale structure of the universe, cannot be fully explained by examining components in isolation. These are the emergent properties of a system in motion. Crucially, the theory emphasizes nonlinearity. A small difference in initial conditions, say a fraction of a degree in temperature or a minuscule fluctuation in quantum energy, can cascade into vastly different outcomes over time. This sensitivity to initial states, familiar to us from chaos theory, plays a pivotal role in cosmic evolution. It suggests that predictability is often an illusion, and that the universe's story is one of contingency as much as inevitability. Furthermore, complexity theory invites a broader, interdisciplinary approach. The behavior of the universe may share surprising parallels with biological systems, social networks, or computer algorithms. Studying how ecosystems evolve or how digital networks grow can provide insights into how cosmic structures take shape. The formation of galaxy clusters, for instance, might be better understood through the lens of ecological network theory, where balance, competition, and cooperation dictate system behavior. Another compelling aspect of this theory is its focus on resilience and adaptability. The universe has endured cataclysms, stellar explosions, gravitational collapses, and more, yet structure persists. From the delicate chemistry of the first atoms to the emergence of conscious life, cosmic evolution has shown a remarkable ability to adapt and reorganize. This mirrors what we see in biology. Systems that survive are those that respond dynamically to change. By identifying these patterns, we may also uncover insights into how life arises and endures in an ever-changing cosmos. In the end, complexity theory does not just explain how the universe is. It tells a story about how the universe becomes. It reveals that from the simplest of beginnings, shaped by the laws of physics and nudged by minute fluctuations, emerged the vast, intricate cosmos that cradles us. Through its emphasis on emergence, interconnection, adaptability, and nonlinear evolution, complexity theory offers a framework that honors the richness and mystery of the universe's origin. And when this scientific lens is coupled with a linguistic one, we gain a more profound understanding not only of the cosmos, but of our place within it. Together, they remind us to explore the universe is to explore the boundaries of language, thought, and imagination itself. And yet, in the quest to understand the origins of our universe, a new frontier is quietly unfolding, one not solely grounded in physics or astronomy, but born from the union of diverse disciplines. This frontier beckons thinkers from across the academic spectrum, championing an interdisciplinary approach that seeks to unravel both cosmic mysteries and biological complexities. It is a convergence of thought where computer science meets cosmology, and the abstract beauty of information theory begins to illuminate the dark unknowns of the universe before time began. At the heart of this exploration lies a powerful idea that the same principles guiding how we store, transmit, and interpret data in machines might also describe the behavior of the cosmos itself in its most primal state. Particularly compelling is the concept of entropy, a measure of uncertainty or information content, which plays a central role in both digital systems and cosmological models. In the realm of information theory, entropy quantifies the unpredictability within a message or system. Similarly, in cosmology, entropy becomes a key to understanding the conditions that existed before the Big Bang. According to many models, the universe was once in a state of remarkable uniformity, a low entropy equilibrium where matter and energy were evenly distributed. But why? And how did this highly ordered state give rise to the astonishing variety of structures we observe today, from galaxies and stars to the vast cosmic web that stretches across the observable universe? To answer these questions, researchers are turning to information theory as a conceptual bridge. By analyzing how minor fluctuations in that early uniform state could evolve into complex formations, physicists are uncovering new ways to think about the origins of structure in the cosmos. These fluctuations, tiny though they were, may have encoded the seeds of everything we see now, suggesting that the universe's early development was not unlike the transmission of data across an imperfect channel, where noise and variation spark new forms of order. But information theory is more than just a metaphor. It offers tools, rigorous mathematical frameworks that can be applied to pre-Big Bang physics. Consider the encoding and transfer of information. Just as digital systems compress, store, and relay data, the early universe may have been governed by analogous processes, where energy and matter were encoded in a primordial state, setting the stage for everything that followed. These ideas invite us to rethink the role of information not just as a property of communication systems, but as a fundamental ingredient of reality itself. One of the most provocative connections comes from the holographic principle, a theory suggesting that all the information contained in a volume of space can be described by information encoded on its boundary. This is a radical notion, one that implies the three-dimensional universe we experience may be a projection of data encoded on a two-dimensional surface. In such a universe, concepts from computer science, like data compression, information redundancy, and encoding efficiency, suddenly acquire cosmological significance. Could the complexity of space-time emerge from simple rules operating on a lower dimensional surface? If so, the universe may be far more algorithmic in nature than previously imagined. Meanwhile, insights from quantum information theory are deepening this picture. The strange phenomena of quantum mechanics, entanglement, superposition, decoherence, are not just abstract curiosities. They are modes of information behavior at the most fundamental level. Quantum entanglement, in particular, is now being viewed as a thread that might stitch together the fabric of space-time itself. These developments hint at a universe where information is not only a passive descriptor, but an active agent in the unfolding of reality. As these scientific paradigms shift, sociology enters the frame with a critical lens. Scientific knowledge does not arise in a vacuum. It evolves through human networks, social, institutional, and cultural. Theories about the early universe are subject to the same pressures, biases, and collaborative dynamics that shape all human endeavors. Sociologists of science study how research communities form, how ideas gain momentum or face resistance, and how consensus is built or broken. In cosmology, where empirical data is sparse and interpretations are often speculative, these social factors play a particularly powerful role. The collaborative nature of modern science means that breakthroughs often emerge from diverse teams working across disciplines and continents. The acceptance of radical new ideas, such as the role of information in cosmic origins, depends not just on mathematical proofs, but on dialogue, openness, and a willingness to challenge entrenched paradigms. Thus, our understanding of the pre-Big Bang universe is not just a scientific endeavor. It is also a story of how humans, driven by curiosity, guided by theory, and shaped by culture, strive to comprehend their place in a vast and mysterious cosmos. Through the fusion of computer science, physics, and sociology, we are beginning to see that information may not only describe the universe, it may be the universe. Furthermore, the path to scientific consensus is not a straightforward journey through data and logic alone. It is a nuanced, deeply human process shaped by the intricate web of social structures, professional hierarchies, and institutional power. Within the scientific community, the acceptance of new theories often hinges not only on empirical validation, but also on the endorsement of respected authorities, those whose voices carry weight due to their status, publication history, or institutional affiliations. This gatekeeping, though sometimes subtle, can be a powerful force. It determines which ideas are fast-tracked to prominence and which are quietly sidelined. Sociologists have long studied how these dynamics operate, uncovering the unwritten rules of professional validation that influence the life or death of scientific hypotheses. These mechanisms of influence are particularly salient in fields like cosmology, where theories about the early universe often push the boundaries of empirical testability and rely on complex interpretations of indirect data. Cultural context plays an equally vital role. Science does not evolve in a vacuum. The development and reception of cosmological theories are deeply entangled with the prevailing cultural beliefs and societal values of the time. In societies fascinated by the mysteries of origin and existence, theories about the birth of the universe receive a disproportionate share of attention, funding, and prestige. Public curiosity about the cosmos, reinforced by educational media and popular science narratives, can steer both public and private investment towards certain research areas. As a result, some models of the early universe are nurtured into maturity under the spotlight, while others languish in the shadows. not necessarily due to their scientific merit, but because of cultural resonance. This interplay between culture and science offers a window into the sociology of knowledge. It reveals how national identity, religion, media representation, and even political ideology can shape scientific priorities. For instance, a society that values technological innovation may favor cosmological models that align with experimental physics, while another more philosophical culture might embrace theories rooted in metaphysical implications. Public engagement is not merely a peripheral concern. In fact, it is central to the life cycle of a scientific theory. The way scientific concepts are communicated to the broader public through documentaries, educational programs, social media, and public lectures can dramatically influence public perception and, in turn, institutional support. When the public embraces a narrative about the early universe, it can create a feedback loop in which popular enthusiasm drives funding, which enables research, which yields further discoveries, all reinforcing the initial narrative. This symbiotic relationship between scientists and society has historical precedents. Sociologist and historian Thomas Kuhn, in his influential work on scientific revolutions, illustrated how science progresses not linearly, but through paradigm shifts. When existing theoretical frameworks become burdened with anomalies, observations they cannot explain, scientific communities enter periods of crisis. It is in these turbulent intervals that new paradigms emerge, often championed by outsiders or marginalized thinkers, and slowly gain traction until they replace the old guard. Kuhn's insights are particularly relevant to the study of the cosmos. Theories about the early universe, such as the Big Bang, cosmic inflation, and quantum gravity, are constantly evolving. As new data from deep space telescopes and particle accelerators reveal unexpected phenomena, the scientific community is forced to reevaluate its foundational assumptions. Sociology helps us understand this process, highlighting the role of community consensus, generational shifts, and even intellectual fashion in determining which theories prevail. But the sociology of science is not the only lens through which we can examine the origins of the universe. Economic theory offers a compelling parallel. Consider the distribution of matter and energy in the early universe, a process that can be intriguingly compared to the allocation of resources in economic systems. In both domains, we are dealing with limited quantities dispersed across a dynamic, evolving system. Just as economies wrestle with the challenge of distributing finite goods and services, the early universe faced the cosmic task of distributing matter and energy across the fabric of space-time. In the aftermath of the Big Bang, the universe existed in a state of near-perfect uniformity, with matter and energy spread almost evenly. But quantum fluctuations, tiny, random irregularities, introduced minuscule variations in density. These microscopic differences became the seeds of structure. As the universe expanded and cooled, gravity amplified these initial irregularities, pulling matter together to form the stars, galaxies, and clusters we observe today. This process mirrors the way economic systems evolve. Scarce resources are rarely distributed evenly. Initial advantages, no matter how small, can lead to significant accumulations over time, a phenomenon known in economics as cumulative advantage or the Matthew effect. Similarly, regions of the early universe with slightly more mass attracted even more matter, becoming the cosmic equivalents of economic centers of wealth. Furthermore, just as market forces determine the rise and fall of industries, the gravitational dynamics of the universe determine which regions collapse into dense clusters and which remain sparse. These parallels underscore how principles of distribution, competition, and growth apply across both physical and social systems. By examining the early universe through the dual lenses of sociology and economics, we gain a richer understanding of how scientific ideas are born, nurtured, and transformed. It reminds us that science, for all its rigor and objectivity, is a profoundly human endeavor, shaped not only by observation and experiment, but also by culture, consensus, and the stories we tell about where we come from. And yet, the vastness of the universe may be more intimately connected to earthly systems than we ever imagined. Drawing unexpected parallels between the cosmos and economics reveals strikingly similar dynamics, an interplay of forces, competition, growth, and entropy that bind two seemingly unrelated realms together. In economics, the invisible hand of market dynamics and competition drives innovation, efficiency, and the emergence of complex structures. Agents, whether individuals, firms, or nations, compete for limited resources, shaping markets through a feedback-rich landscape. Surprisingly, this mirrors the gravitational ballet playing out across the universe. Just as businesses seek dominance through strategic positioning, matter in the cosmos clusters in regions of higher density, attracted by gravitational pull. These dense pockets become the seeds of galaxies, stars, and planetary systems. This gravitational competition mimics economic rivalry. Dense matter accumulates more mass, deepening its gravitational well and drawing in even more material. Similarly, in an open market, success often breeds success. Profitable entities attract investment, expand operations, and widen their reach. In both cases, competitive processes do not always lead to equal outcomes. On the contrary, they frequently result in uneven distributions. But from this imbalance, growth, stability, and complexity often emerge. Feedback loops offer another fascinating cross-disciplinary connection. In economic systems, feedback manifests through reinvestment, market signals, and resource depletion. A company that reinvests profits into research and development may enhance its future prospects, while overuse of a resource can drive scarcity and collapse. In cosmology, feedback is no less critical. The process of matter collapsing into a galaxy doesn't end with formation. It triggers ongoing gravitational reinforcement. Galaxies pull in nearby gas, prompting new star formation and altering their environment in a continual cycle of self-influence. Understanding these feedback loops, whether they occur in the swirling disks of proto-galaxies or the shifting sands of global trade, allows us to see how tiny fluctuations can evolve into monumental changes. Seemingly minor alterations in conditions can cascade over time, resulting in the birth of stars or the fall of economies. Moreover, the concept of entropy ties the cosmos and economics together through thermodynamics. In both fields, the second law of thermodynamics, entropy's steady rise, guides evolution. In the economic sense, entropy can represent market saturation, resource depletion, or the inevitable movement toward equilibrium in supply and demand. Meanwhile, in the early universe, as matter expanded and cooled, entropy increased, guiding energy into ever more complex structures. Galactic formation from a hot, chaotic early universe parallels the structuring of an economy from raw materials and labor. Over time, what begins as disorder transforms into intricate systems, an organized galaxy here, a modern economy there. In both cases, the journey from scarcity to organized stability is shaped by distribution, competition, and the harnessing of energy. Now, shift your attention to an entirely different domain, music theory. Surprisingly, it too offers a powerful lens through which to view the cosmos. At first glance, the orderly progression of a musical composition may seem far removed from swirling galaxies or quantum fields. But dig deeper, and the parallels are profound. Music, like the universe, thrives on structure, symmetry, and resonance. Harmony, for instance, refers to the blending of distinct tones to produce a coherent and often beautiful whole. Similarly, the universe achieves a kind of cosmic harmony through the interaction of fundamental forces: gravity, electromagnetism, and the nuclear forces. These forces, despite their differing roles, coalesce to form the rich tapestry of reality. It is through their precise balance that stars ignite, atoms hold together, and life can exist. Think of them as cosmic instruments, each playing its part in a universal symphony. Symmetry, too, plays a starring role in both music and cosmology. In a musical context, symmetry might be found in the repetition of motifs, mirrored phrases, or balanced chord progressions. These patterns lend structure and beauty to compositions. In physics, symmetry underlies the laws of conservation, of energy, momentum, and charge. It dictates how particles behave and interact at the quantum level. Gauge symmetries and group theory inform the standard model, just as musical scales and time signatures shape a composition. These symmetrical patterns in the universe are not mere aesthetic flourishes. They are the foundation of physical law, the scaffolding on which the cosmos is built. Just as composers use symmetry to craft emotional arcs and resonance, the universe employs it to maintain order amidst chaos. Even the concept of musical scales offers a window into cosmic relationships. A scale is essentially a framework, a set of intervals that governs the creation of melodies. The universe, too, operates through intervals, though in a different language: space, time, mass, energy. Redshift and blueshift, for example, represent changes in light frequency due to cosmic movement. These shifts, observable in the light of distant galaxies, echo the rise and fall of musical tones, telling stories of expansion, motion, and the fabric of space-time itself. Consider gravitational waves, ripples in space-time caused by violent astrophysical events. These waves, once detected only in theory, are now measured and studied. Their oscillations are, in a sense, musical. They have frequency, amplitude, and rhythm resonating through the universe, much like a note rings through air. By tracing these parallels, market competition and gravitational pull, feedback loops in economics and cosmology, thermodynamic entropy and resource scarcity, harmonic structures and physical laws, we begin to see the underlying unity and complexity. The economy, the cosmos, and music are all systems in flux, evolving through interaction, structure, and change. In recognizing these connections, we not only deepen our understanding of each field individually, but also enrich our broader view of the universe. The patterns that shape a symphony, the rise and fall of civilizations, and the birth of stars may all, in the end, follow similar rules. And through this lens, we glimpse something truly profound, that across disciplines, scales, and dimensions, the universe sings a singular, intricate song. Moreover, the role of rhythm in music mirrors the majestic cycles observed across the cosmos. In the grand expanse of space, celestial bodies, planets, stars, and galaxies move in rhythmic harmony, guided by the invisible hand of gravity. Their orbits form repeating patterns, elegant in their predictability, much like the steady beat of a drum or the measured tempo of a symphony. These cosmic rhythms, looping through time and space, echo the pulse found in musical compositions, where beats and measures establish a framework of order. Just as a composer crafts structure from sound, the universe arranges its own patterns through motion and gravitational interplay. Each planetary orbit, each rotation of a moon becomes part of a vast ongoing cadence, one that we, with keen observation, can decipher. Understanding these celestial rhythms not only enhances our grasp of astrophysical systems, but also provides a window into the dynamic forces shaping our reality. Music theory, with its concepts of harmony, symmetry, scales, and rhythm, offers more than aesthetic pleasure. It becomes a metaphorical key to unlock the architecture of the cosmos. When we draw parallels between the structured elegance of a fugue and the orbital resonance of distant worlds, we begin to see an underlying unity. The laws that bind notes into chords are not unlike the laws that tether planets to stars. In this way, music and astronomy converge. The universe, vast and silent to the ear, pulses with a rhythm all its own. By tuning into these rhythms, both musical and celestial, we enrich our understanding of existence itself. It is in this shared structure, this mutual order, that we find a deeper connection between the human experience and the ever-expanding cosmos that surrounds us.